Te zoom accountod van meg?
Igen. Okay, so we are gonna get started in a minute. Let us get prepared. So first, I'd like to invite Christoph Ivan, the Dean of our faculty, to give a short welcome, and then we are going to get started with Daniel Balogh.
Thank you, István. I'd like to extend a warm welcome to everyone present in the room and present in the stream or as an attendee on this event on our next conference called From Data Analysis to High Performance Computing. Difficult to remember all of these cool titles. And from the point of view of the Faculty of Information Technology and Bionics, Pázmány University, I would like to express our welcome here on the conference. I hope that this will be another successful conference for all our attendees. And I think that for quite some time in the next year, maybe for at least a year, we will have to accommodate and accustom ourselves to these sort of hybrid conferences, which might be cumbersome in some ways, but definitely has its positive sides in terms of we can join into conversations with presenters really either far away or in a lockdown country, which we had yesterday, and that gives us the opportunity to really have a very high quality and good conference. And I accept the same thing from this conference as well, and I'm looking forward to all the presentations. Thank you very much and welcome all.
Thank you, Christoph. So first off, we have Daniel Balogh from Pázmány Péter University, who is going to tell us about adjoints in a domain-specific library called OPS. Danny, you should be able to share your screen now and unmute yourself.
Hi, okay, I try to share my slides.
Yeah, we can hear you, okay.
Okay, can you see?
Everything looks good. Not sure if this is your first slide, but yeah, we can see you and hear you.
Really.
Okay, you can go ahead.
So hello everyone, my name is Daniel Balogh, and I will talk about algorithmic differentiation of structured mesh applications in the scope of the OPS domain-specific language. So first of all, algorithmic differentiation is a set of techniques to evaluate derivatives of a function which is defined by a computer program. But why do we need that? So a lot of numerical methods require derivatives, and there are three main ways to compute those derivatives. The first is finite differentiation, which is a quite common way to compute derivative information, and it might be easier to implement, but for high dimensional problems it's quite slow and doesn't offer exact derivatives to us. So another way is to use symbolic differentiation, which is will give us the exact derivatives, but it cannot handle all programming constructs that are given in some languages. So, for example, it cannot handle unbounded loops. And to address all of these problems, algorithmic differentiation is promise us that it will give us the exact solution and it give us the solution fast, which means that the evaluation of the derivatives will be, I mean, the cost of the evaluation will be some multiples of the evaluation of the original function. At least that's what AD promises us. So the trick is that we take our function, our program, and so this function basically just generates some output from some input variables. And we want to compute the Jacobian of this function. Well, at least a part of the Jacobian, where each element of the Jacobian is the derivative of some output with respect to some of the inputs. But the question is how to get those derivatives. So the trick is that we want to decompose the f function into some subfunctions. So let's assume that the f function is a composite function with k subfunction. This way, the Jacobian of the f is basically just the product of the Jacobians of the subfunctions. And from this point, we can take two routes. The first is we can use forward mode AD, which computes the action of the Jacobian to some vector in the input space. And the backward mode AD will compute the action of the transpose of the Jacobian to a vector in the output space. And we will do backward AD, and we will see why. So backward mode computes the action of the transpose of the Jacobian to some vector in the output space. And if we choose the this W vector to be a nice vector for us, then we will get quite a big chunk of the Jacobian. So we choose the W in such a way that it has only one non-zero element, which is 1, and all the other elements are 0. And if we compute the action of the transpose of the Jacobian to this vector, we will get a single row of the Jacobian. So the advantage of the decomposition of our function is that we only need to evaluate the function, so a single Jacobian of the decomposition. So we will evaluate the last Jacobian, and we will evaluate the action of the last Jacobian to the W vector, and then we can go backwards in the chain. So the advantage is that we only need one sub-Jacobian at a time. But the catch here is that to get a Jacobian inside the chain, we will need to evaluate that Jacobian at the point where the original function was evaluated. So we will need to store all the intermediate steps, but we will get back to this problem soon. So yeah, backward mode AD or adjoint mode AD usually implemented with operator overloading. So we will, in this case, what they do is they wrap the primitive types into wrapper functions and wrapper types and overload their operators. This way, the backend kind of gets a notification each time an operation is performed on those types. And if we have a single addition or multiplication, the Jacobian for that operation is quite easy to compute. So the idea is that we have really simple sub-Jacobians which are trivial, and then we can chain them to get the whole Jacobian of the program. But this way, we need to store the order and the intermediate states for every variable at every single operator or elementary operation, which is quite inefficient in some way. So it will produce enormous enormous chains of operations. So we will try to improve this technique in that point. And about our background, we are doing domain-specific languages for HPC applications, and the motivation there is that we have newer and newer hardware each year, and it is not really clear how to program the next generation of hardware, and it's infeasible for an application developer to always port their application to the newest hardware. So basically, we want to code our application once and then get quite good performance on each hardware that we want to try on. And we use embedded domain-specific languages, which mean that we embed our domain-specific language into C++, and then the application developer call high-level functions to describe the application, and then the domain-specific language will deal with the hardware-specific implementation details. So the application developer doesn't have to deal with these problems. And for this specific talk, we will talk about OPS, the Oxford Parallel Library for Structured Mesh Solvers, which is embedded in C++, as I mentioned. And basically what it does, it will wrap the high-level constructs like grids and datasets and loops over these datasets into high-level API calls. And then from those API calls, especially for loops, we will generate the hardware specific implementation, and we will deal with the parallelization of that. So we will deal with structured meshes like in the right-hand side, where the neighboring grid points can be computed easily. I mean, the indices of these neighbors can be computed easily. So in OPS, each step of the computation must be a loop over some set of the grid. So each such step must be a call to OPS par loop, and the developer must feed this call a function pointer to the body of the loop and some descriptors to describe how we will access the datasets on the grid. So an example to such a call is here, where we will pass the mean kernel to the OPS par loop. We will give a name to that, then we will have the grid that we will operating on. We will have the dimension of the loop and the range of the iteration. And then we will give for each access dataset a descriptor, where we write the access pattern, and we will write the stencil which we will use to access the dataset. In this example, we will use 2D stencil with 4 points. So we will access the 4 neighboring points for each iteration, and we will read for the dataset U, and we will write the center point for U2. So OPS has all of these information, and OPS already generates the parallel implementation for each loop. So from these information, the question is that can OPS do AD only from this information? And basically, OPS generates the loops, which will call some backend functions. So kind of OPS already has control over the sequence of loops. So we can build these directed graphs for the control of the application. The thing that we are missing is the function that will compute the action of the Jacobian for that loop to the vector from the output space. So if we assume that we can get our hands on such function, then we can, in theory, do AD. So we assume that either the application developer will write a derivative function for the loop bodies, or we can generate the derivative function for the loop body with some external tools like Tapanade. And if we have these, we have the idea that we can do AD on a loop level, and we can also generate parallel implementation of the backward loops as well. So the missing features to do that is that we need to store each intermediate state, and this is the point where we get back to the problem that I mentioned earlier, that we need the state of the program at the point where the subfunction was evaluated to evaluate the Jacobian at that point. So we will need to store each intermediate state of the program. And the other problem that we will have to solve is we have to reverse the data flow inside loops. And I will show what I mean by that. So the first problem is that we need to store each data set that we are overwrite. So we introduced a new data structure in OPS, so-called tape, where each generated parallel loop will register itself to the tape, so we can build the chain of the loops. And then inside the loops, we generate code to save all data before it's overwritten into the tape. And then in the backward sweep, which is the right-hand side of the figure, we have the OPS interpret adjoints call, which will traverse the chain from the end towards the beginning, and it will load all the intermediate states from this tape and perform the adjoint loops, basically. So, okay, we have this one, but what about the reversing of the data flow? So this is an example of what primal kernel look like and the corresponding adjoint kernel looks like. So on the left-hand side, we have a really simple kernel, which will compute the mean of the neighboring points of each point, basically. So we will access 4 points from U, and we will write the mean of those 4 points to U2. And if you want to compute the Jacobian of this function, it will basically just multiply. So it will be, each element will be this constant factor here. So if we want to compute the action of this Jacobian, then we will write the derivatives of the input variables, and we will read the derivatives of the output variables, which means that while in the left-hand side we have 1 write and 4 reads, and we have a gather operation just like in the left-hand side here. When we do the adjoint loop for that, we will have a scatter operation where we read the center of the stencil, and we will write for each node that was read in the primal code. So the problem is with this is that while OPS forces the developer that we will have only gather operations in the primal code, which mean that there is no race conditions and we can trivially parallelize each loop, we will have scatter operations in the backward loop, which mean that no 2 neighboring iteration can be run parallel. since they will write the same data. So there will be a race condition. So to avoid this race condition, we have two approach. The first what we use for CPUs is that we use the red-black coloring of the iterations. So we'll divide the whole iteration space between threads, and then for the domain, we will color the domain of each thread with red and black. We will color the first stripe of each domain for a thread as black, and we will have a red stripe at the end of the domain in such a way that the stencil does not collide with the stencil from another thread. So we will avoid race conditions this way. And we will have a synchronization point after we computed all the black iterations, and after the synchronization point, we can do the red iterations in parallel. And the other technique that we used is we used operator overloading with CUDA in a way that we use atomics for the increments with CUDA. That way we don't need coloring, but we will deal with the overhead of the atomic operations. Okay, so what we get as performance, so we evaluated our application on a code from finance, and so we have typical mesh sizes from finance. Well, the 1000 times 1000 is quite big in that domain, which will be a problem with GPUs, but we will get there. So for CPUs, we have shown that we can do AD, and the cost is at most 6 times the cost of evaluating the original application or the primal, which is a really good result for us. As far as I know, the theoretical computation cost of the derivatives is around 4 times of the primals, so we will have a little bit of overhead to that, but we are really close to that, so it's quite good. And on GPUs, we kind of get the same results. So for the SLV application that I mentioned, the example application from finance, we do AD under 4 times of the time of the primal, but this is a bit of a cheat because we have some external functions which the derivative is basically the same for them, and this hides the overhead of the primal parallel loops, which can be 10 times, or even some cases we have 40 times of overhead for some loops. So that we have some overhead here, and it's initial results. So we need to look into that and get some better performance, but the starting point is promising. Yeah. So the problem with the current solution is that we store each intermediate state. So we will save each data that will be overwritten, which quite a lot. In this table, we see that for the largest example that I shown previously, the primer uses 200 megabytes of memory, and if we run 200 iterations, then we will get up to almost 30 gigabytes of stored tape data, which is really a lot. So we need to address that. And our plans to address that is that we want to save only checkpoints for the data, and therefore we will recompute the intermediate states from these checkpoints, which will drastically reduce the memory pressure of the AD, but of course it will increase the runtime. But we will look into that, how it's so how can we do this in an efficient manner. So in conclusions, we extended OPS with an adjoint aware API, and we successfully implemented parallel implementations for the adjoint loops for both CPUs and GPUs. And we showed promising runtime performances, and we will have some more improvements, especially for GPUs soon, I hope. Yeah, so, but the problem of the current implementation is that we use too much memory, and we will reduce this memory pressure with checkpoints. And thank you for your attention.
Okay, thank you, Dani. So now we are gonna have questions. In the Zoom system, you have a Q&A as well as a chat setup tab, so you can use either to ask questions. Please go ahead and use them. I can see a bunch of people already
Q&A.
online. Yes.
This is not merged yet to master OPS. We have a branch feature/AD. So I think it's a bit lagging behind the current implementation, but I will push everything to that branch soon. I'm not sure when we will be able to merge that branch, though.
So for those who use this, it's fairly obvious in finance. You can look at the sensitivities, what affects the end results the most. I think Fabio, who just asked this question, who work in seismic imaging, they also use adjoints a lot, although slightly differently, and I think they'll talk about that. I'd be interested to hear if this happens in weather. So maybe Michael, if you are online, you can comment.
Well, yeah, we run very large adjoint models in weather. Yeah, there's definitely a lot of large adjoints, but they are very much embedded in the systems themselves. So it's not just about the adjoints, but it's also how to get the tangent linear from the nonlinear system and things like that, that we need to worry about. In terms of storage, I can't really say much because I'm not an expert on adjoints, but they are very, very important. And I'll kind of mention it briefly, I think, in my talk, where they are important.
Okay, thank you. So if there are no further questions, we are just in time. So we're going to move on to Michael Lange from the European Center for Medium. Who say that again? I don't have it in front of me. You're gonna have to help with me. Can you share your screen? Let me promote you to co-host. Yes. So I believe you should have, yes, control of everything now. So great. He's going to tell us about weather simulations and how they use DSLs to support this.
Planning to use. Yeah. Hi, everybody. My name is Michael. I work at ECMWF, and I want to talk a little bit today about a big old weather prediction code known as the IFS, the Integrated Forecast System that we use, maintain, develop, and run at ECMWF. And I want to have a bit of a look at how these novel programming models like DSLs and source-to-source translation hopefully can help us future-proof these systems. because they're actually quite old. So, but before I kind of start with the technical bits, let me quickly introduce ECMWF, which is short for the European Center for Medium Range Weather Forecasts. And we are basically an independent intergovernmental organization that was established in 1975 with headquarters in Reading in the UK. We are governed by a council of 22 member states and 12 cooperating states, and we produce global numerical weather forecasts. In particular, as it's in the name, we focus on global weather prediction at the medium range. So medium range is defined as a 15 days forecast. And the reason for that is that basically in weather prediction, if you want to have a high accuracy, high resolution weather prediction system for a local range, say for global, a local region, say Central Europe or the UK or something like that. If you want to have one of those models, you will, once you get to a forecast of more than a few days, basically you quickly will realize that the boundary conditions that you need to feed into this model, due to a phenomenon known commonly as the butterfly effect, actually span almost the entire globe. So you need a global model as well as a local high-res model to kind of do good weather prediction at local scales. And so the idea was that in the 70s, people decided it'd be a good idea to pool resources and expertise and create a dedicated center to just run these global weather prediction systems that then works very closely with national Met services on things like early warning and the kind of day-to-day weather prediction that you see on the telly each evening, etc. And one of the sort of hero stories at ECMWF that we like to tell is to do with early warnings for severe weather systems, which is this little story about Hurricane Sandy, because the IFS, the code that we're going to talk about, is actually pretty good at tracking hurricanes. And what happened in 2012 was that this hurricane, after it devastated large parts of the Caribbean, was kind of drifting out to sea and just running along the Atlantic here. And most storms that take that track kind of just go east and kind of just go over the sea. But Sandy decided to take a sharp left turn and intensify and really hit badly the regions of New York, New Jersey, and parts of Canada. And the IFS, the code that I want to talk today about, actually had predicted this left turn 8 days in advance, which caused the evacuation to start about 6 days in advance of the storm actually hitting the coast, while some of the American models only confirmed that trajectory later. So it shows that this really makes a real difference in people's lives, and it saves lives and all of that, but it also shows the incredible predictive capabilities that these modern weather predictions have. And a lot of things play into this sort of thing, a lot of factors in terms of the science, how these systems have grown. But one very important component of that is the computational power that we have available these days. So here's a chart of the on-site HPC system that we've had at ECMWF ever since the IFS went live. So the same code that we're talking about went live in 1979 on an old Cray 1. Well, I say old because that was the best machine at the time. And we can see a very, very strong and linear increase in computational power due to Moore's law that has also powered a very, very predictable increase in grid resolution, which with other things like increasing complexity of the individual components modeled, has really fueled this increase in capabilities of weather prediction. So we started at 200 kilometer resolution, 210 even, and the current operational suite runs at 9 kilometer resolution. To me, as a software engineer, it's also very, very exciting to kind of look at the kind of systems that they had along the time, and to compare the actual code that we have in front of us still from that has gone through all these systems, and how individual software paradigms have impacted it. So, for example, we started on Cray vector machines, and we had an incredible utilization of these. The second Cray vector machine actually had like 50% of theoretical peak. Could you imagine that in nowadays machines? But when we came to 1997, we switched from Cray to Fujitsu machines, which had distributed memory systems. So we had to, so people had to add MPI to the system. And in 2003, we switched to IBMs, which had hardware multi-threading. So OpenMP was added to the IFS and all of that. So we stuck with the IBMs for a while, and now we're running on Cray. The current system is a Cray XC40, and we've just kind of started. We're getting a new one next year, hopefully. But the key thing to note is that we're utilizing this gray system at around 4 to 5% of peak. And the one thing that I also wanted to highlight is that one of the first optimizations they put in for the original vector machines was this particular memory blocking design, which is basically just known by a variable name that for historical reasons known as nprom. And I'll refer to this later in my talk again. That was put into the very first instance of the IFS. And it meant that we could basically dial up and down the memory requirement of the system and ensure efficient vectorization on these grays. And that has actually fueled a steady performance increase on deep cache CPUs as well, because when you can dial up and down the memory requirements due to blocking, you can also do the same thing, not just for memory, but also for caches, which means the IFS has continuously done really, really well on deep cache CPUs over the years, and still to this day does. So now, as I said, the scientists are getting really, really excited about the kind of increase in computational capabilities and predictive capabilities, and they've kind of gotten used to this. But we've all heard also about Moore's law kind of slowing down or stagnating, and we're not entirely sure how we're actually going to guarantee that this kind of growth is going to be supported, which is a bit of a shame, because on top of the kind of operational runs, our scientists are actually experimenting with much higher resolution already. And in particular, this 1 kilometer resolution that we kind of are predicting here, or that was predicted in this paper, is really interesting because the science actually changes quite drastically. So processes like convection actually become resolved rather than have to be parameterized, which gives another massive boost in accuracy and predictive capabilities and skill, and also requires the science to be kind of reconfigured and recalibrated, all the parameterizations and components to play well with each other. Now, because we mentioned data assimilation or adjoint-based methods, what we actually also have with operational weather models is this operational window where all the compute has to happen in a particular short time frame. We have an operational window of 1 hour. So what happens is that we get all the data from the satellites and kind of aircraft and different meteorological stations into the system. Then we run what is known as data assimilation, which is basically an adjoint-based inversion algorithm that establishes the initial condition of the model. And after we have the initial condition of the model, we then run the high-res forecast as well as ensemble forecast and things like that. That's an amazingly large amount of compute that all has to fit into an hour, because that's when the data then goes out to our downstream users at the National Met Services, etc. And because we have this kind of tight time restriction, we can make some kind of extrapolation and conjecture about what kind of increase in computational power we actually need to make this magic 1K resolution really reality in the day-to-day forecasts. And this is in this paper from Schultz et al., where they predict basically that we need a computation improvement of around 250x over current capabilities to achieve this. Now, Moore's law is slowing down. Accelerators are popping up everywhere. We have heterogeneous architectures, but we have a system that over decades has been highly tuned to CPU architectures. So we can kind of see that it is not just going to be hardware increases that will fuel this. We need to actually look at software and infrastructure alongside hardware upgrades to hopefully get to this level. So one final kind of show-off slide from to showcase the science of the IFS. This is another little kind of eye-opener of what predictive capabilities we have these days in weather prediction. The concept of a digital twin. So on the left-hand side here is a photograph actually taken from space on one of the NASA Apollo missions in 1972, showing very nice and clearly weather patterns over the Earth. And on the right-hand side, we have a run of the assimilation of the current 9K resolution of the IFS model, run with the forecast data from that very same day. We can see that we're actually matching these patterns rather well already. And this is already at 9K resolution. So it's quite exciting to get to this kind of magic new resolution where things will be even more accurate and even more kind of on point. And this is the idea of a digital twin that has recently taken shape as part of a big European project. It's known as Destination Earth, and with some of our partners, ECMWF is taking a major role in this, which is meant to bring together all the kind of scientific and software infrastructure capabilities from data assimilation and Earth observations, systems modeling, and software engineering to really make this idea of a high resolution digital twin a reality that can create socioeconomic impacts for various sectors. There's also a bunch of artificial intelligence in there. So AI is everywhere, and obviously it feeds into this as well. Although I'm not going to say much about AI today. So what I instead want to focus on in my talk today is give a kind of rough overview of some of the most important components of the IFS and see how DSLs and kind of similar techniques can be used to prepare this code for heterogeneous architectures and accelerators, and where we can actually, what are the software steps that might unlock some of the computational gains that we require to get to this next scientific step change. Before then, I'll talk a little bit about the more bespoke things that we do for the IFS, and hopefully, if I have a bit of time, maybe even talk about FPGAs, which will be cool. So yeah, so the first point I want to make when talking about the IFS or complex NWP models, and in particular the IFS, this might be different for some other ones, is that these models, while we talk about them as one model, the IFS, it actually is made up of several components. These have complex interactions with each other. So we model the atmosphere, we model the land surface, some of the waves, sea ice and ocean. And all of these different components actually have very unique and individual performance and scalability and characteristics. So for example, our ocean sea ice model is community model MIMO, which scales very differently than kind of atmospheric components that we use. I'm not going to say much about oceans today either. I wanted to focus on the atmosphere. But the point I'm making is that we have a wide range of computational patterns, and we need to actually be very mindful that these scale differently, exhibit different characteristics at different scales, and on different types of hardware. The other core thing is that, especially within the components like the atmosphere, there's usually a flat performance profile. These codes have been optimized literally over decades for the architecture they're running on. So the kind of one-shot optimization of, oh, I'm just going to find this one routine, which is this one solver routine, which everything calls, and if I can speed this up by a factor of 2 or 3, everything's going to be much faster. That trick doesn't work. Every component sort of has reasonably good spread of the things that it needs to do and the way it does it. So in order to fully utilize heterogeneous architectures for future HPC, we need to look really at the big picture and the interplay of the individual components. We need better abstractions to separate the science from the performance engineering, and we need more flexibility inside the codes. This code is older than myself. We need to kind of look at different programming models and other things to make this really a reality. And this point was actually realized a few years ago, and we started a project known as Escape, which is now in its second instantiation as Escape 2, where people try to break down this entirely big and somewhat monolithic software stack of NWP software into algorithmic building blocks, or they call them dwarfs in the paper and in this project. But what they really are mini apps to allow investigation of alternatives to the current programming models, as well as alternatives to the current hardware, or even look at this holistically, alternatives to numerics. Do we even need to do everything the way it was done, or can we change numerics to better align with hardware needs, etc.? And the hope is that down the line, we can reassemble a better and improved NWP system from these individual components. So I want to look at a few of those today, and keeping in mind the idea of separation of concerns and where can we use DSLs to help this, so to separate the scientific definition from the architecture specific stuff. And at least want to ask the question and kind of look at in parts of what is the underlying domain of variability? Are DSLs the universal catch-all solution to separate science from architecture, or are there other methods? Can we abstract away computational patterns? Can we go as far as numerical abstractions? And in which components can we do so? And if we want to look at computational patterns, which ones do we want to look at? Halos, parallelism, stencils. And so this is kind of the idea. And we start off with the very core of the system, because the IFS, unlike many other NWP codes and numerical weather prediction codes, is actually quite special in the way in the choice of numerics for its dynamical core, and as weather people like to call it, the die core. And it's based on the spectral transform method, where while a lot of computation is done in normal grid point space, like the semi-Lagrangian advection schemes or the various physical parameterizations, but then the prognostic variables for each time step are transformed via into Fourier space via FFTs and via what's known as the Legendre transform into spectral space, where other components of the core system are done: horizontal gradients, semi-implicit calculations, etc., and the diffusion terms, before it is all transformed back into grid point space. Now this has advantages and disadvantages. The advantages is a very, very stable method for global weather prediction, because it has no CFL condition attached, which means we can actually run with very large time steps. I think we're running something like 7.5 minutes in operations at the moment. The downside of it all is, though, and I'm just going to touch on this briefly, is that these transforms, the FFTs and the Legendre transforms, they are global. So they actually require global communication across the entire system in the longitudinal and meridional directions. So during one time step, every node in the HPC system has to talk to every node. And that has a potential scalability bottleneck. Now, can we really help here with DSLs? Well, that's actually a really tricky one, because things like FFTs and the Legendre transform really boils down at its essence mostly to things like degems and matrix calculations, are things that even on modern accelerator architectures are usually taken care of by math libraries. And the optimization that we really need to do is clever communication scheduling, but nothing that really exhibits the wide domain of variability to kind of even warrant the effort of writing a bespoke language for Lagrangian, for spectral transforms. So I'm not saying it's not impossible. I don't think it's really worth the trade-off and building a dedicated DSL for this. There might be some point to leveraging parallelization abstractions, but in total, it's not obvious that this is a good idea. Instead, good library work and good APIs might just achieve the effectively same thing. Now, the next point I want to make is, as I said, there has been some concern about the long-term scalability of this, especially as we're approaching exascale, where we really have super wide machines. It is unclear how long this will scale. And the good news first, so far the spectral transform method is good and well at scaling all right. We have not seen any problems. But in case this does become a problem, we do want to be prepared, which is why a few years ago, we've actually started work on an alternative dynamical core based on a finite volume method. So there's a new non-hydrostatic finite volume dicore. It's still very much in the prototype stage, but it's coming along. So people are doing the first little hurricane tracking experiments, as you can see here on the right. I think this is Hurricane Irma from 2017. And I'm not going to go into kind of the deep numerical and mathematical details on it. There's a paper that describes it very well. But from a computational point of view, the core point here is that this alternative formulation of the dynamical core exhibits the complete opposite characteristic. It has local low volume communication, basically halo exchanges, which are neighbors only, do not span the entire machine. But as a trade-off, it doesn't quite run with the massive time steps. It has variable time stepping, super and sub-time stepping, but it genuinely requires shorter time steps because it does have a CFL condition attached. And now the current prototype, as I said, is coming along and it's nice, and we can do like real science with it and kind of evaluate it as an option and prepare. But because it's also a new development, it is currently still written in Fortran and MPI and OpenMP. But it also seemed like a very good idea, because this is a new development, to actually make sure this is future-proof on construction. So the idea is that the first experiments, the first kind of prototypes are being built to actually port this to a dedicated DSL. And this is the Grid Tools DSL, or GT4Pi. It comes by many names, but it's from this Grid Tools ecosystem. I think GT4Pi is the current latest front end. And the idea is, and we're kind of exploring this internally, the idea is to build first prototypes of this on certain structured grids, and because FVM also works on structured as well as unstructured grids, to eventually in a few years port the full global system to this DSL. And this is possible because FVM has much more of the kind of traditional computational DSL patterns. It's based on halo exchanges. It's based on basically stencil-like computations, even though they're structured and unstructured. So things are much more predictable and fit much more into the kind of standard patterns that allow us to then abstract away the performance optimization through various backends through the Grid Tools infrastructure. So Grid Tools can do C++ and CUDA and accelerators and all of that. And the idea is that we then don't actually have to rewrite that new die core, hopefully for a few years, whilst we can adapt it quickly to new architectures if we feel the need to do so. So again, software flexibility, algorithmic flexibility is the main theme here. But in order to hold this all together, so we have two very, very different formulations of our dynamical core, we need one more ingredient. This is Atlas. So I've had the name on the previous slide, apologies for that, but Atlas is kind of a library built especially for numerical weather prediction codes as a new foundation with future HPC challenges in mind. So the idea is that we need smart and elegant data structures to really achieve the separation of concerns of the technical layer from the science layer. So Atlas is a C++ library with a bunch of modern Fortran object-oriented interfaces, and it encapsulates all these kind of high-level constraints, so a grid, a mesh, halos, partitionings. It supports multiple function spaces, finite volume, finite element, and very importantly for us, of course, spectral transform, the spectral harmonics. It provides other readily available operators, importantly interpolation and remapping. And it basically means that we can abstract away the memory usage and storage of a field from the actual application. So rather than dealing with raw Fortran and raw Fortran arrays everywhere, we actually have these objects that sort of set up and manage memory more intelligently. So they're aware of parallelization, they're aware of accelerators. So things like sync between host and device can be encapsulated now in an API, and we get more control. And again, more flexibility in the software and in the technology layers. So point here being, DSLs are good and well, and we really want them to optimize our kernels for modern accelerators, but we need more than that. We need good libraries and good APIs to kind of complement these, to kind of build coherent systems and move existing systems forwards in a kind of non-invasive manner. So I've talked about the dynamical cores, the kind of central pieces of these models, but actually atmospheric weather model and atmospherics model, there's a second component, and that has, again, slightly different characteristics, and that's the idea of physics, which is short for the physical parameterizations, because there's a wide range of dynamical processes happening in the atmosphere that we need to account for, and that we need to actually get good predictions of the weather. And they have been developed over years and years to come. So as I said, the model complexity has increased as well as the computational power behind it. And that means the physics actually now forms a very, very large part of the code base. So we're dealing with hundreds of subroutines over hundreds of thousands of lines of Fortran code. And there's, again, no clear kind of standout solver routine that we can optimize and that everything just goes super fast. And there's no kind of so clear performance profile. There's no kind of unifying numerical method or kind of hotspot performance issues that we can just use to improve the situation. So there's a mixture of implicit and explicit methods, and every parameterization is kind of slightly own take on the solvers. And I'm not saying this is necessarily true for all NWP models, but it's certainly true for the IFS, and it's a big challenge for us because we cannot therefore go at this from kind of high-level numerical DSLs, at least not in the current state in a kind of migratory fashion. But we do have one common pattern among all of them, and that is basically the fact that these are subgrid scale parameterizations. By design, they have no data dependencies between two columns. So all the processes, all the important stuff happens up and down these columns, which means two neighboring columns never communicate. They have no dependency on each other, which is important for two reasons. One, the scientists actually can write a simplified version of the kernels where they just deal with one column. They can investigate the interplay between the different parameterizations. They can configure and tune and try new things, and they typically only run on one or like a handful of columns for representative cases during the development cycle. And that is fast. That you can do on a normal workstation. It doesn't require an HPC system necessarily. Once you get into play with the entire rest, that's when it gets trickier. But a large part of development can be done in these, what's known as a single column model, where you just write the code that actually deals with the vertical interactions of these points. Now, the second point is why this is important is that the fact that we have no data dependencies means we have a lot of parallelism. So this is a massive, trivially parallel problem because of this. And we've already seen how we can use this to really accelerate HPC, because this is this vector optimization that I showed in one of the first slides. The variable is known as nproma, and it basically means that these columns are stored in dedicated blocks of variable size in memory. So with the block struct, so we have memory blocking, which means we're splitting this one-dimensional space of free data parallelism into two. We're using it for two reasons. One, between the blocks, we can just add OpenMP thread parallelism to basically treat OpenMP intra shared memory parallelism the same way that MPI does. It's perfectly, there's no break conditions, there's no fault sharing, anything like that. We just have pure parallelism. And inside the block, we get free vectorization. All we need to do is make sure that the block size is a multiple of the SIMD width. Data is nicely aligned to cache lines and to pages, and etc. And this is at the heart of the CPU optimization of the IFS, as this memory blocking scheme. Now, the other thing about this is we do have a massively parallel system. So in theory, this should also be really good for GPUs. And this comes down to this one paper here by Valentin Clément et al. And our colleagues at MeteoSwiss, who a few years ago used this idea to demonstrate that physics can actually run very well on GPUs as well. And they start from this idea that the single column model, the simplified code that the scientists so much like, even though it's pure Fortran, can be in a very systematic way changed to insert the right loop level and the right loop nests to basically write bespoke backend code for CPUs as well as GPUs that utilize this free level of parallelism in the right way. So rather than then vectorization, title vectorization loops around most of the kind of logic blocks and the arithmetic, you insert a high level, widely parallel loop for the GPUs to promote offload. And they demonstrate that this can actually work really well with just the source-to-source compiler. They built it, and it's called the Claw, and it's really great. And we want to obviously use this. We have code that our scientists like. Yeah, it's Fortran. They don't have to change their ways completely from scratch, but we still have code generation elements that allow us to target architectures individually. So that's great. But we have one problem, because as I said, we have a very large code base, which has already been discretized into the CPU only mode. So the specialization has been done. If you think of the single column as a higher level of abstraction, we have already lowered the abstraction to an architecture specific format of the code. And we have hundreds of thousands of lines of that code. So we actually need to back out to a higher level abstraction from something that is already lowered. And that is a very different problem. And that problem, in order to solve that, we built our own source-to-source system for the IFS. And that's what I'm going to talk about now. And it's called Loki. It's based on roughly the same ideas as partially the Claw source compiler, as well as different DSLs. Because I've worked on other DSLs before. And it's the idea of a freely programmable source-to-source translation tool. The idea being that if it's freely programmable, we can actually use assumptions and knowledge of the code base that is in front of us that a general purpose compiler, even the DSL level, high level compiler, could never know and could never assume. And this we can use to inject or recover domain-specific assumptions that have been lost when this code was specialized for a particular architecture over time. So by being able to actually encode the transformation that we want to do ourselves using assumptions about the IFS and the IFS only, we can then also facilitate a kind of nice working practice where we can encode every change that we would usually apply to the model that would be detrimental to CPU performance. Because the one thing in this kind of evolution rather than revolution way of modernizing code is that you cannot sacrifice current CPU performance. So anything that would harm this needs to be encoded rather than committed. So so this idea of single column code basically is slower because it kills CPU vectorization, right? And if we can dress all this up in scripts and kind of nice little infrastructure, we actually make this available in bulk through large parts of the code base. And to the scientists who don't really care that much about the technical specificity of GPUs and accelerators, this looks as just another preprocessor. So we're starting to separate out the kind of science from the technological aspects again. Also, by not committing, we can explore things like we can create demonstrators for different downstream tools and systems, like in this case, the Claw source-to-source compiler, or other DSLs, other programming models like SYCL, etc. All of these are things that we can now play with and explore without having to commit the bespoke changes to our kernels in order to feed this. And this gives us a certain leeway with experimentation. So the key point here being that this tool that we've built, we didn't actually want to generate a kind of optimizing compiler, but rather a tool that can feed better optimizing compilers downstream and just makes and basically backs out our very bespoke coding styles to make all of this accessible. And there's also something about actually dealing with Fortran, because the way we built it is sort of like you build the DSL style compiler, at least kind of on the conceptual high level layer. So it's a front end that basically takes the Fortran codes and sort of goes through one of many several front end choices and distills it into a sort of internal representation. And all of this happens in like a Python programmatic fashion. So you have source objects that represent source files or modules or subroutines. And you then have a bunch of visitor and transformer patterns and mapper patterns that allow the transformation to actually be encoded bespokely for particular subcomponents of the model, for particular models, etc., by the user, who kind of can make their own assumption, and they can use their own assumption to make improvements or changes to the code in a programmatic fashion. And there are different backends to again spew out Fortran code, or we can even spew out C code or other ones. This is a kind of an extendable infrastructure. And this is where the kind of experimental Fortran to Fortran thing comes in, because we can change things. We can also use this as a kind of general code hygiene tool, a linter with an autofix option. But that kind of changes the spec. So this is kind of just targeted at the DSL compiler engineers in this meeting. This gives a new dimension to kind of the things that you need to be careful about, because it requires a very extremely conservative parse-unparse cycle. So from this file down to this file, you have to be able to basically do an almost zero character change. That's actually quite hard. But yeah, that's just a kind of point on the side. So under the hood, what does it look like? As I said, I worked on Python-based DSLs before, something like the DeVito system that we're going to hear about tomorrow, I think. And the one idea from this is this that I've taken with is this kind of idea of a two-level internal representation, the two-level IR. So under a subroutine in the kind of module sits a two-level IR, where the outer level is the control flow. So this deals with loops and conditionals, assignments, and all of these sort of code constructs. But it can optionally skip over things that are expressions. So it doesn't necessarily, the visitor and traversal methods don't actually go into the expressions unless you tell them to. So you can have things like find all the nodes that are assignments in your code in this particular routine body, and it will run through the entire tree, and we'll find these assignments, which are these two lines here, and the code on the right. But it will skip all the expressions that are blue here, so the kind of a equals 0 or the I or the 1 and n, which are just symbols. And then there's a second level of kind of visitors and mappers that basically traverses the assignments in themselves, because the trees under complex arithmetic expressions can become quite large, and this is just dealing with complexity, really. Again, points for kind of compiler engineers or kind of DSL engineers. So here we find all the variables, so it'll run through this, and we'll find the left-hand side is a variable temp, and the right-hand side is a product of a and xi, where x is a variable and I is a variable, etc. All of these. The expression tree is based on Pimbolic, which is a bit, which is kind of meant to be a bit more conservative than other things like SymPy, which is very important because of this very conservative parse-unparse cycle. We can enrich our internal representation. So the idea of carrying metadata around about and doing interprocedure analysis, for example, to carry around things like dimension information from the caller to the callee down the deep trees for certain variables, that sort of thing can be done. And that's sort of the thing that we need to do clever little tricks that a general purpose compiler would otherwise not be able to do. And then with basic visitors and mappers to transform the code in a programmatic way, as I said. And this gives us the opportunity to encode certain changes and transformations. And the idea is here that we create this two-step transformation to GPU code from optimized CPU code. The idea is that we auto-extract this single column code that the scientists already like, that is slow but validatable via Loki. And the API is something like this. So in order to remove a certain type of loop, so there's hundreds of these little vectorization loops that just basically span a few assignments and the inner dimension, so that it vectorizes nicely inside the block. And you get a routine at the dimension. The dimension here just needs to be a string, really, that tells me the variable name. What you can do is you run through all the loops in a particular routine body, and if the loop variable matches that string, you then map the loop to its own body, thus effectively deleting the loop when you apply the transformation to the subroutine body, something like that. The key thing that we've done here, though, is that we've used highly bespoke knowledge of the IFS code, and the fact that all the vectorization loops innermost across these hundreds of subroutines always use the same variable name, which is kind of in our code. Just a feature of the code. And this will not generalize beyond the IFS. In fact, this will not even generalize beyond parts of the IFS physics because conventions change in different components of the code. So we can make this highly specialized to back out this high level single column code, then feed it into the claw. And this gives us this toolchain where we have original CPU code, go front end, internal representation of Loki, apply a transformation, put it back out. And because the debugging question always comes up, how do you debug this for a system that is so new and kind of all the code generation magic? You can then say this code still needs to validate. You still need to get the right answer. Even though it might be slow and it's basically devectorized and not as fast on CPU, this still needs to get the right answer. You can then feed it into basically any downstream tool that you like. In this particular case, we've written code explicitly annotated for the claw that can then use its domain-specific assumptions to generate CPU and GPU code. Now, what have we done? We've basically mapped this sort of looping scheme. So, as I said, we sit behind a kind of clever memory blocking scheme that runs in thread parallel over the blocks, then uses Fortran subroutine association mechanisms to kind of rescope everything so that a subroutine of parameterization only sees a single block. And it then walks the sequential loop direction, which has a lot of data dependencies and loop carrier dependencies. And this is the vertical. We walk through the vertical of the levels. And then we have many of these vector loops with various expressions. This results in stride 1 SIMD data accesses, which is fast on CPUs. What we actually, after this complete toolchain that we've just described, get is conceptually at least something slightly different, where we again use the blocks, but we make the blocks really big, and we use them to offload to a GPU device. And we then put the parallel dimension of Improma, the block parallel dimension, outermost, and use OpenACC from the claw. Or we can even switch to OpenMP, it's either really, to make this thread parallel on GPUs. And internally, we will walk sequentially because that's how OpenACC works. We've basically switched the loop nest to go from vectorized from vectorized SIMD to coalesce memory accesses via SIMT. That's all it is. But it's fun in games to do this for 1 or 2 kernels, but we have to do this for hundreds, literally hundreds. So I'm just showing one parameterization here. There's many, and the parameterization has a deep call hierarchy. So this is the root call, which actually sits in the original. It sits under the OpenMP. But we're kind of working on kind of the integration into the main pieces. Then goes really wide with all the different components. So this is the turbulence parameterization. It then has various components that come from the surface model, which actually sits in a different SO, in a different compiled part of the binary, which really is meant to highlight that we spent a lot of time just really honing the integration with the build system. So it's all fine to kind of flip IRs and and change code, but you need to do this for complex build systems of complex code as well. So we have very fine-grained, so we have a kind of mini build system with Loki that knows about things like module dependencies for Fortran and has configurable subtree source injection. So we can basically really at a fine granularity configure which source trees in a big binary of hundreds of files get actually replaced with certain transformations here and other transformations here. So there's very fine level control for experimentation basically. And a lot of work goes into this, but it's possible and can be made to work. And that is basically the part on the GPU. So now I do have a little bit of time. So I want to talk a little bit about FPGAs before hopefully leaving a few minutes for questions and discussion. So this entire idea about source translation and the Loki software actually comes out of a project known as the EuroExa project. And this is a pretty cool European project, which is mainly a hardware and a co-design project that is centered around the idea that we want to build a HPC architecture based on FPGAs, accelerators, and cost-efficient modular ARM CPUs, but not just kind of bolt an FPGA PCIe card onto a host, but actually build an entire node design, entire board around a centerpiece FPGAs to really facilitate a puristic kind of FPGA system and to see how this could scale to peak performance and how this would work. And there's a large software component to that as well, which is where ECMWF comes in. And apart from the obvious kind of benchmarking our main code on the ARMs, etc., one of the key things that we want to do is we wanted to explore this automated source-to-source translation for aiding the porting efforts of going from kind of legacy Fortran, there it is, I said the L word, big legacy Fortran to kind of really exotic novel accelerators like FPGAs. So the parameterization that was chosen, because we can't do with a whole code, is again one of these physics parameterizations that was extracted in the ESCAPE project that I mentioned earlier. And it's this idea, this is Cloud SC, the Cloud Microphysics parameterization, which computes the 5 prognostic variables of 5 constituents of humidity or water. So water vapor, cloud water, cloud ice, rain, snow, and all these things. And it's a really complicated parameterization, which is why we usually use it as a kind of proxy to highlight the complexity of the physical parameterizations in the IFS. It has nonlinear terms and computes many fluxes between these different kind of prognostic variables. There's slow terms, explicit, and fast terms, implicit, etc., which ultimately results, and I'm kind of just glossing over the numerical detail here. There are dedicated papers to kind of look at the science for this, but it results in a very large kernel. Unlike the one that I just showed with the many small kernels in a deep nest, we have one very large kernel with some very expensive loops. So I said before, we have kind of flat performance profiles. Well, that's the one thing that occasionally stands out depending on the configuration you're running in, because basically the implicit terms mean there's a large loop carrier dependency across the vertical. Just seeing the outer loop is on the CPU implementation is the vertical, so we can't actually split it or parallelize across it. And inside that loop, we have many of these vector loops and 250 local variables and more than 2,500 lines of Fortran code. That's kind of really the acid test for any kind of automated transformation tools, because this is kind of the point where it becomes really tough for humans to do this, which isn't to say that it can't be done, as I'll show you in a second. So what we try to do is basically, we wanted to port this to an FPGA, and the platform chosen for the FPGA is the Maxeller data flow environment, which is basically an FPGA or traditional PCIe kind of card. But it comes, so these are known as DFEs, data flow engines, which have a VU9 FPGA in here. And it basically comes with its own programming model, its own programming environment, which is known as MaxJ is the language, and there's a compiler, and there's an OS, etc., which basically is a kind of variant of Java, but it's much more high level than things like HLS to program the FPGA. So if you know a little bit about a FPGA, it's a low level language, it's HLS. But this is actually much nicer. It's much closer to kind of general purpose programming. And it also comes with a compiler and a suite, and it gives this SLIC interface here, which basically dresses up your invocation of compute on this reconfigured FPGA just as a C function call, which is kind of nice. And I'm kind of having to speed up here a little bit, because basically what we did is we took our complicated Fortran code, we ran it through kind of the first prototypes of Loki to get a C version where we treated all the kind of weird little Fortran corner case conventions that we use in the IFS and for these complicated kernels to kind of generate much more accessible C from it, and gave this to one of our collaborators, a guy called Jamie Target at Imperial, who was an actual, who was a PhD student at the time, and he's a real expert in MaxJ and FPGAs and data flow programming. And I don't think I'll go through too much of the kind of technical details, but he figured out many things about how to actually do this by hand and actually gave us a recipe. So he figured out how to basically block the iteration space so that you can kind of saturate the FPGA pipeline whilst not using too much while not using too much local memory. So the idea is because it's hard to explain without kind of going into detail on FPGAs. So basically FPGAs kind of reconfigure the gates on the chip to mimic the code and the arithmetic that you've given it, rather than having a kind of general purpose arithmetic unit that gets invoked over and over. So the actual chip encodes the logic and the arithmetic that you give it, and you feed data into it at the top. And this encoding, this design has a pipeline depth, and this pipeline depth needs to be filled. And the best method to do this is basically to get to a blocking scheme, much like the Improma scheme that we have above. So basically we kind of feed in on the order of 1,500 columns, kind of in almost parallel, tick by tick. We feed in one of these grid points, he calls them cells, until we fill the pipeline of this entire chip. So the entire chip, so every level in this pipeline has a grid point in flight. And then we have enough buffering, and then we buffer the partial results of these 1,500 columns rather than all of the millions of them. Go through next. And this allows us to actually work quite efficiently at the kind of, because we have a deterministic way to get the optimal block size, because pipeline depth of the actual data flow graph that underpins this design of the FPGA. A bunch of other things that are necessary: breaking up the kernel through fission and fusion, aligning vector IO, bit identity was a big thing, etc. I'm not going to go into much of it. I hope the paper comes out very soon and you can read up on the kind of technical details. But what it allowed us was to do a single chip performance comparison, because we actually got to validate this kernel. So I'm saying explicitly single chip performance comparison because we're comparing the CPU to GPU to FPGA. But on the GPU and on the FPGA, it's very important to discount the PCIe overheads, because Cloud-SC is actually ripped out of a large integrated set of physics. So a lot of the data comes in and out of it, which we now read from file, actually would, in a realistic porting of the physics to any accelerator device, would actually be device local and would never leave the device. So there's a lot of kind of PCIe overhead that's just unrealistic for real systems, and it just completely kills performance on all accelerator architectures. But if you discount that, you can actually just assess the pure potential of the raw chip and the computing paradigm behind it. And we're comparing this to basically a single socket of our operational Cray, which is a Broadwell chip, NVIDIA Volta, and this Max 5 DFE, which is a Xilinx VU9P. We're actually getting some really impressive speed ups in terms of throughput. So between 2 and 3 double single precision over GPU and CPU, add a factor of 4x better energy efficiency over GPU and a factor of 8x over CPU. So that is really impressive. And whilst it's really, really hard to program these things, and the stuff that Jamie did is not easy to generalize even with the infrastructure that we have. I believe this warrants greater research into data flow architectures as such, FPGAs, CGRAs, and similar, for the kind of long-term planning, because the high degree of hardware specialization that these architectures can give you can actually be quite valuable, I believe, personal opinion. So yeah, obviously we have a code generator, so we're trying to generalize this. We're currently, all I can show off here is kind of the simple kind of textbook cases. So here's a 1D moving average, translated on the right-hand side from, this is raw Fortran with a kind of low-key annotation, translated into MaxJ. Here's the conditions, and here's the kind of masking that you have to do instead of being able to do real conditions, etc. Here's the boilerplate for all the streams in the data, and the same thing can be done for the 5-point Laplace operator. And at that point, in the interest of time and discussion, I'm going to finish. I'm going to let you read the conclusion yourselves. And I'd like to thank you all for your attention and take questions. Thank you.
Okay, thank you. Very interesting talk. So while the questions come in, I have a bunch myself. So with this FPGA, you mentioned, you have to stream in the data and out. Is there parallelism in terms of, while the FPGA works, what does the CPU or, all the other components of the system do?
Okay, yeah. So as I said, sorry, I didn't have too much time to go deep on kind of CPU and generally CPU, GPU are von Neumann architectures. So you have a general purpose accelerator unit, the CPU they're really big and on the GPU they're very small, and many of them, and it's reasonably simple, that do instructions over and over and over again. And all you need is data parallelism to kind of make this happen in parallel. FPGAs work differently because you actually expose a different level of parallelism. You expose pipeline parallelism, which means in a complex pipeline of things that need to happen in sequence, every point in the pipeline can be occupied by a different data point. So this is the pipeline depth that I try to very briefly show here. So basically, the actual computation of the kernel, the thing inside the loop body, is about 1,500 logical and arithmetic operations deep in terms of the pipeline. So at any point in time, once the chip is filled, 1,500 independent data parallel points are in the chip in flight, which means once the chip is full, for every processor cycle, a complete result comes out, tick, 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 because you've changed your data parallelism into pipeline parallelism. That's sort of the core essence of all data flow accelerators, which is why they're interesting. So I'm saying explicitly not just FPGAs because they have some very real world limitations like compile times are nuts, but there are other things that potentially could mitigate this, hybrid architectures like CGRAs that could bridge this gap and make this a bit more realistic over the kind of long-term future. So not the next year or two, but longer term. They're interesting. Hope that answered it.
Yeah, Fabio, please do go ahead and speak.
Hi, Fabio.
If you can. I might have to promote you. Hold on. Okay, now you should be able to talk, Fabio.
You hear me?
Yeah, hi.
Hey, hi, Michael. So thanks for the talk. It was great. We have too many questions probably for the time we have, but so the first one. So you were talking about the 3 visitors.
Yeah.
The system. So first thing. So how many compilation passes do you have based on those 3 visitors?
Oh.
How many transformations do you do with these infrastructure? Like, is it just 1, 2, 3, or are we talking like tens? So.
We're talking small number because basically the idea is that unlike a kind of full-blown compiler, the user writes them, and we're talking at a much higher grained, much higher granularity. So we really are talking about semantic things like stripping indices from arrays, and kind of so the internal representation that we have stays super close to the actual source code. There's no kind of high compiler level abstraction in the sense that kind of other systems like the Vito do. We are not an optimizing compiler. We allow semantic transformations to be encoded by people and to kind of chain them. So the SCA stuff that I have, the actual passes are like 3 or 4. Some of them are fairly overloaded where I'm just doing like, okay, flip out this, flip out this, flip out this, flip out this. Yeah. And you have these kind of like, where is it? These sort of loops like 5, 6, 7, 8 of them in like just one pass. You just do this over and over and over, and you take care of this corner case, take care of this corner case, take care of this corner case, until stuff works. It's by no means as theoretically sound or kind of as well defined as the stuff that you do in the Vito. But it's a practicality thing of kind of, can I feed my very bespoke code into more general abstractions?
Yeah, no, that answers the question. So my next question was more about, so I guess you tend to run low order methods. So most of the optimizations you do, guys, are memory optimizations. Is this correct?
Yeah.
Like
Ish.
memory blocking, whatever.
The generalization is really hard because there's no common method. Every parameterization is its own thing, in a sense. The one thing that is crucial for these codes, because they were built a long time ago, vectorization, memory safety, and kind of threading efficiency, and yeah, memory optimization. Even cache locality, it's hard to say if we're good or bad at it. We're not too bad at it because otherwise the thing wouldn't scale that bad. But I believe there's potentially room for optimization. But it's the sheer volume of code is just too much to kind of do this analytically in the kind of single, because you're dealing with hundreds and hundreds of which is effectively low order kernels, but they're all chained and fused by hand and kind of, but with function calls between them, etc. There's no one answer to this. And that's only the physics. So the other parts then are very different. So FVM is fairly low order, spectral transform has no order, and
Yeah, no, that makes sense. So, okay, I don't know if there's anyone who wants to talk. I can't see it, or maybe can I? Istvan, tell me. I mean, I can go on forever, so just.
Yeah, we do have another question here.
Yeah. Hello. So I would like to ask a question about the intermediate representation, because I didn't understand, first of all, if it's a separate IR for data flow and control flow, or it's like a combined one. It's like SSA in regular compilers. And in either case, do you need this, or why it is useful to have a so-called two-level IR? Thanks.
Oh, yeah. So the IR is, we haven't got data flow analysis in the IR. It's something I would like to do at some point, but it's hard, and it's not like, we have many more pressing issues first. And the IR is very simple. It really, the high-level control flow IR is very simple. It really sticks to programming semantics. So you have the concept of a loop, a conditional, an assignment, and those sort of things, and then all the kind of quirky Fortran-y things. The transformation into the data flow stuff is all, again, very semantic. The actually complicated data flow stuff happens in the max.j. The kind of semantic mapping that you can do is that you can basically, you need to replace real if statements with compute both branches and then do a ternary masking. That's a sort of semantic level that you can do. And then the ternary masking actually within the max.j compiler, that's where the actual data flow stuff, the data flow graph get generated, and the kind of FPGA design comes from. So you're very much still working on the kind of user level programming language semantics. That's why it needs to be so bespoke. There's no generalization. We're not a real compiler. We're a front end for real compilers that deals with legacy code in a very simplistic way. But we are using compiler technology to do this. And the idea of the IR is simply that it makes it easy to program for large code. So if I have 2,500 lines of Fortran code inside a big loop body with a few hundred vector loops, and I want to flip them all out, then instead of kind of grepping and SEDing through my source file, I can encode this with 5 lines of Python, or 4 even. That's sort of the point of the high-level IR. It's nowhere near kind of the low-level compiler theory stuff. We use a few tricks from compiler theory, front ends, back ends, some analysis steps, but it's kind of what you can encode with the stuff that you have in front of you that you can do. It's more about the automation of code porting, if you will, because we're dealing with large legacy code.
So kind of connected to this, I'm going to ask a question that would probably take an hour to explain, and you have about 1 minute. Still, so how, technically, and sort of convincing people that the source-to-source translation works and it gives you valid results. How did you convince people?
So Well, first of all, that convincing process is work in progress. So we're still working on this. We're kind of rolling this out. Like this is not done. This is kind of as work as we do it now. And there's a lot of kind of actually doing this for real now, happening behind the covers, so I can't say too much. But the idea of basically the standard development test, we run a particular test case, we check that the answer is right, that the answer is, in fact, most of the semantic transformations that we do need to be neutral. If you don't actually get the right, like the exact bit reproducible answer at the end, it becomes really hard to check. In fact, there's a lot of this stuff going on, where basically your basic tech level testing is either a bit reproducible, or you have to run a full weather suite and start to look at the science, which makes things a bit complicated. So there's a lot of effort in this kind of conservative mode, where don't change the order of that plus because it will actually change round off type thing. And the expressions that we have are big, exponentials, and we've had certain front ends that just think they know better and flip, and all of a sudden the actual result is off in like 10 to the 18, and you know, things go downhill from there. So it's just really about being conservative and encoding things that you know and are provably the exact same code as before. They're just more amenable to kind of downstream tooling. So it's encoding the stuff that you'd otherwise do by hand for porting, basically. Same point.
Okay, thank you, Michal. Unfortunately, we ran out of time. Sure. So thank you again for the talk, and we are gonna move on to Benjamin Weber and Carlos Oshuna from MeteoSwiss. I have given you the co-host, so you should be able to share your screen now.
All right, hi guys. Let me just get this screen sharing started. Okay. So I need to quickly do something. Okay, there's a funny glitch with my system, but I hope you can see my.
Yes, we can
now.
see the desktop. Yeah, all good.
Okay, that's great. Yeah. First of all, actually, I would like to say thank you to my previous speaker. That was a really interesting talk, and also I'm very glad that about this nice content that he presented before, because I think my presentation, it's in a very similar kind of context, but also it's on a kind of, we take a bit of a different angle, and I kind of want to touch on this nice phrase that was mentioned before, so kind of evolution versus revolution. And I think here we're gonna see more the revolution approach. Also, I think my talk takes a bit of a different angle, but I think that's something on a higher level. This phrase is something where we can kind of contrast these two approaches together, and I think that's, in my opinion, a very interesting, question, and kind of a big a problem that we need to solve, at least in this climate and weather forecasting domain. But I'll think I'll come back to that at the end of the talk, and yeah, I think we'll just get right into it. So I'm presenting MeteoSwiss, the Swiss National Weather Service. I want to give you an introduction and an overview to two tools called Dusk and Dawn, and basically this is about a high-level DSL toolchain for weather and climate models on icosahedral triangular meshes. So that's quite an interesting sentence, and the goal of this talk is to kind of untangle this and give you a more concrete feeling of what this actually means. So I want to first start off with the Icon model. So we've seen the model from ECMWF, in my opinion, very interesting. And then the Icon model is another very big model. It's for physical simulation of weather and climate forecasting. So this is obviously very interesting for MeteoSwiss, since we want to do weather forecasting. It stands for Icosahedral non-hydrostatic model. We're going to look at what icosahedral means in this context later on. It's a joint development with the Max Planck Institute and the German Weather Service, the DWD. There's a whole bunch of other institutes involved as well. It's a fairly big collaboration. It has over 1 million lines of Fortran code, so this is also a very massive model. And I mean, it's a bit hard to say how many lines of code it has, because it consists of many components. There's a component for the ocean, there's a component for the atmosphere, and they don't necessarily live in the same repositories. And then there's different branches being developed at different institutes, and they also don't live in the same repositories necessarily. So it's rough to put a single number for the lines of codes, but I can tell you it's an absolutely massive model with many international collaborations and many institutes involved. It uses both finite differences as well as finite volumes in the die core and some finite elements in some configurations of tracer fluxes. So kind of our work here is mostly on the stencil-based things, but we will see this. Okay, so I want to talk a little bit about the mesh here. So Icon is a global model. It tries to simulate the whole globe, and basically what it does it first does an initial subdivision. Can you see my mouse, by the way? I think in Zoom it's fine.
Sorry, it takes a bit to answer. Yes, we can see the mouse.
Ah, awesome. Yeah, that's great. So if we look at this sphere on the left side, kind of what happens is first there's this initial subdivision into these red lines. So we kind of subdivide the whole sphere into triangles. That's the first subdivision. And then once we have the initial subdivision, we can divide it further into more triangles. So one triangle can be kind of recursively subdivided into more triangles, and then we just keep adding triangles until we have the resolution that we're looking for. And so, for example, if we want to have a 13-kilometer global resolution, we need roughly 3 million triangles. So that's a lot of triangles. And so the initial subdivision, these red lines, the shape of those red lines, that's called an icosahedron. So that's where the whole icosahedral keyword comes from. And this mesh is called an unstructured mesh. And I want to elaborate what this kind of means. So if we look at this triangle, at this vertex here in this subdivision, then we can see the number of neighboring cells is exactly 1, 2, 3, 4, 5, 6. So it has 6 neighboring cells. And this is true for all the next level of subdivision, and this is also true for this level of subdivision. So it's always 6 triangles. So that's mostly very, very structured. There's a very regular structure in there. But if we look at these red lines here, then for this vertex we will see that there's 1, 2, 3, 4, 5 triangles surrounding, and there's exactly 12 points in these in these red. There's 12 points in this first initial red subdivision where we have this irregularity where the vertices, they only have 5 neighboring triangles. And then basically the other roughly 3 million triangles, for those points, there will be always 6. So that's kind of where the name unstructured comes from, right? There's, even though like the most points will be completely structured, there's these 12 points that have the exception. And that's kind of where the unstructured stuff comes from. And kind of the other interesting thing is that we use triangles here because we build this on the icosahedron, and this has some advantages versus other meshing approaches. So kind of in the predecessor model called Cosmo, we used kind of a longitude latitude rectangle subdivision, and the issue is that as you go to the poles, you will kind of get a singularity, which makes it really hard to run global models with like, let's say, the straightforward rectangular meshes. But then there's some other approaches, like, for example, doing an initial subdivision of a cubes and then of a 3-dimensional dice onto the sphere. But then you have you also have some irregularities. But that's kind of, that's where the icosahedral, we have the initial subdivision, and then we use a whole bunch of triangles. And then there's one last thing I want to add here as well. So we've seen this before as well. So kind of here we subdivide the initial surface into this 2D. We subdivide the 2D flat surface into triangles, but the sphere is kind of 3-dimensional because the clouds are very high up in the sky, and when it rains, the drops, they fall for quite a while. And how we solve this is kind of, we just keep stacking layers on top of each other. So kind of the sphere gets subdivided in triangles, and then we kind of like an onion add these layers on top of each other. And that's kind of how we reach the vertical, how we add the vertical domain on top of the horizontal surface that we started off with this mesh. And then we have a volumetric atmosphere that we can simulate in the weather. So that's it for the mesh. And I want to kind of give you a motivation here. And basically, in our model software, we start off with the numerical discretization of our equations. So let's take this very simple numerical discretization where we take the difference between two fields and then we divide by this L-hat term to get this approximation of this physical quantity. So if we code this in Fortran code, it's fairly straightforward. We have a K loop. So K, I'm sure most of you are aware. So X, Y, Z coordinates are in Fortran loops usually called IJK. So K means that we loop over up into the atmosphere, and J here kind of means we loop over the whole globe, over the whole surface, right? And with these two loops, we cover the whole volume. And then in here we have this we can kind of see these equations, right? We have this difference here as well, and then we do the division by this L hat, and then we store this into this this field. And that's kind of, well, that's kind of the initial or the naive first implementation, and that's nice and good. And the problem is this will run only on one single node, right? And we want to kind of be able to run this on thousands of nodes on really big HPC machines. So that's definitely not enough. Our simulations will not be able to do a very high resolution of the globe. So we need to be able to run this on multiple nodes. And then we kind of add blocking. So we kind of subdivide the whole sphere into separate domains, and each of these domains is going to run on a different node. So we add another loop interaction here. So we do blocking here. We get another loop, and also we need to kind of take care that the indices are correct for each single node, that we don't compute outside of our compute domain, and we add a bit more complicated things. So that's nice and good. But it runs now on multiple nodes, but it's not able to use multi-cores efficiently, right? So one single CPU node will have multiple cores. And these multiple cores, they have access to the same main memory. So we could run more MPI ranks on the same node to use the additional CPU cores, but then we will do MPI exchanges on the same node, basically on the same main memory, and that makes no sense. So we kind of want to be able to use the shared main memory for all of the CPU nodes that have access to this shared main memory. So we add OpenMP directives here, right? We add them in here, and then kind of we get multi-threading on multiple nodes, and our performance starts to kind of look better, and we kind of have a nice CPU implementation here. But the thing is, at MeteoSwiss we have GPU machines. I think GPUs are very attractive these days. They're very widespread in some of the fastest HPC centers. They give very good floating point memory bandwidth performance per dollar, basically. And they also give very good performance per energy. So they're quite, their carbon footprint is pretty good. So with MeteoSwiss, we have GPUs, and this thing runs really well with on CPUs, but we want to run this on GPUs. So we add OpenACC directives. Here's one and here's another. And then we need some ifdefs to change between CPU mode or GPU mode. And it turns out on GPUs, we kind of want to have a different memory layout. And to have the different memory layout, well, I mean, we want this so we get better performance, right? So, but then we need a different loop order, and we add this ifdef here so that we can swap these two loop orders so that it works better either on GPU or CPU. Yeah, that's kind of like what we end up with right now. And it kind of started off really simple with this kind of high-level equation. And you can still see it in there, right? There's still this difference, these fields, and then there's this division. It's still in there, but there's a lot of noise around it. There's a lot of verbosity, right? There's like all these indices, all these indirections, and all these kind of directives and loops around that. And the thing is, well, what if our requirements change? So, for example, someone that did the approximation might decide that maybe we want to do a higher order approximation. And basically we have to change this part in here, but kind of this is all dependent on like all the loops around here, and you have to make sure that it's correct, right? And I mean, maybe you run this on your CPU machine, but you should also run this on a GPU machine, right? Because otherwise you're breaking the code of the GPU people, and you might not have access to that, or that might not be so easy, or you might not know all these directives so well, right? So basically the domain scientist kind of is interested in what's like indirectly visible in here, but to make changes here, they have to touch all of the performance relevant aspects out here. And so that's like a lot of kind of mental overhead, and that's very, very hard for maintenance. But then also, what if another architecture gets added? So I mean, the hardware landscape of HPC is, in my opinion, super interesting these days, right? We started with CPUs, then we went to GPUs. Now we're already talking about FPGAs. There's a whole lot of really exotic things coming as well. So the Japanese Fugaku supercomputer, they use they're based on AMDs. That's another architecture. And then our German colleagues from the German Weather Service, DWD, they use so-called vector machines. And then also, I mean, there's possibly coming tensor processing units from the machine learning area. If you're able to run your weather model efficiently on that, you might all of a sudden get access to very cheap and very efficient hardware if you're able to use TPUs. And I mean, who knows? Maybe in 50 years we will do simulations on quantum computers, right? Who knows, right? But yeah, I mean, what if we want to add more hardware architectures to this code? I mean, we kind of have to add more directives. Things get more complicated with loop orders. I mean, Claw is a tool that kind of tries to address this this question is in one way, but there's also certain limitations. So we once wanted to, or currently we want to port a radiation scheme to a GPU, and it turns out the code is very difficult to make run fast on GPUs, even with OpenACC and Claw. There's just some kind of structural limitations in the code. And then, for example, maybe we want to add, we want to change the mesh library. So the mesh library is kind of in here all with all these indices. And if we change that, then we need to change all of them. And then probably also there's a lot of dependencies between those loops. So the code become really unmaintainable. And the reason for that is that the high level equations in here kind of, they're completely intertwined with all the optimization aspects for different hardware architectures. And it's just so tightly coupled that it's very difficult to make changes in one part without accidentally breaking another part. And that's kind of how Dusk and Dawn kind of try to answer this problem with the DSL approach. So I want to give you here a high level introduction. So Dusk is kind of the front end. And it will feed an intermediate representation to Dawn, and then Dawn will generate C++ files that we can compile with GCC or the NVIDIA CUDA compiler into a binary file, and then we can run this. So if we look a bit closer, Dusk produces an intermediate representation called SIR. This stands for Stencil Intermediate Representation. It's kind of an interface representation. It's kind of the interface IR to Dawn. So there exists other front ends that also produce SIR, and you can also add more front ends that produce SIR, and they will be compatible with the Dawn component. And Dawn is also split in two parts. So there's an optimization part, and then there's a code generation part, and they also communicate with some IR. And then we can generate the CPP file, and it goes a bit further. So kind of like I said, MeteoSwiss is interested in GPUs, so we can then run this binary file on the GPU by using our Icosahedral CUDA backend. But there also exists a CPU backend that produces also a CPP, C++ file that we can compile with GCC, and then the resulting binary, we can run this on CPU. So we're not really optimizing the CPU backend very heavily. This is more like a reference implementation, and also because it's kind of a lot easier to debug on the CPU than on the GPU. And then we have like a kind of a simpler reference implementation that doesn't do a huge amount of optimizations, and we can compare our GPU backend with that, and we kind of get a reference. But I mean, the whole idea is that you can also add more backends here. So in theory, you could also add, I don't know, vector machine backends, or you could even maybe add, like, for example, a Fortran backend that produces, or which would aim to produce human readable Fortran code. And that's kind of, this whole picture is kind of shows how we try to separate these concerns, right? We kind of have the high level equations, they get fed into the front end in a kind of pure form. And then the optimizations and the hardware backends, they're kind of completely separated at the end, right? So like the GPU, the aspects relevant for running this efficiently on GPU, they're completely separated in a separate module here that's with clean interfaces between them. And then we can separate these concerns and kind of untangle this highly coupled system again. And that's kind of is how we try to tackle this maintainability issue that we had. And once we can separate these concerns and have kind of this modular structure, the big hope is that we will be able to kind of get the, I don't know, let's say the golden vision where we write high level DSL code that kind of runs efficiently on whatever architecture you want it to run on. Whether this is going to work out perfectly in practice, I think that's a technical challenge, and that remains to be seen. And like I said, I mean, the hardware sector in HPC computing is super exciting these days, and I think it will only get more exciting as we move into the future. There's some really interesting stuff happening, but that's kind of like the answer to this kind of maintainability issue. So then a few words on Dusk. So Dusk is it's a Python embedded DSL. It transforms Python AST into this interface SIR, to this interface intermediate representation. It kind of does it in a fairly one-to-one forward way, straightforward way. Most of the cases, there are some cases where it needs to do some kind of small analysis, but it's kind of, the goal was to keep kind of lightweight, minimal. It uses a statically typed subset of Python, so it's a I would say a very heavy subset of Python. There's very strict rules about that, but kind of they work very well for the stencils that we want to express. And this has been development since May 2020, so it's very young. But it's also been really nice because it's the first frontend that allows to make use of Dawn's unstructured features, and it kind of was the last kind of missing piece for us to be able to write stencils targeting icon. And now that was a really nice experience that we could finally write stencils. And then now we can run them, we can verify them against icon, we can verify them against a manufactured solution with an analytical solution, and then we kind of, yeah, we can finally start writing more stencils in icon, and that's very exciting for us. So I want to give you a bit of an introduction to some important model that we use in Dusk. So like let's start off here with a mesh. So we kind of have this mesh consisting of triangles. And this mesh consists of vertices. So those are like the points connecting all these edges. And then there's these edges in here that are connected by points. And then lastly, we have these cells that are surrounded by edges and vertices. And those are kind of the three fundamental components of kind of any mesh that we are looking at. And those are kind of, we call them the location types, right? Those are the three location types that we have in our mesh. And then kind of naturally they have neighbors. So for example, if we have a vertex, then we already kind of looked at this. So most of our vertices will have 6 cells surrounding them. Very few of them will have only 5. But depending on what your mesh looks like, you can have more or less in there. And then we also have the number of edges will probably always be the same as the number of vertices. So in this case, we will have mostly 6 edges as well for each vertex. Then if we look at the edges, we have 2 neighboring cells. I think it's always going to be 2 because an edge kind of naturally divides cells. And then an edge is kind of always connected to exactly 2 vertices because that's kind of how an edge is defined. And then if we look at the cells, so for this cell here, we have 3 neighboring vertices. And I mean, this is kind of true for any triangular mesh, right? If we had rectangulars, then we would have 4 neighboring vertices. Or if you had hexagons, you would have maybe 6 neighboring vertices. And then with the number of edges, they kind of will correspond to the number of vertices. So in our case, it will be 3. So we have some kind of natural direct neighbor relationships. But we were thinking, well, you kind of have these 3 neighboring edges, they again have neighbors. So in our case, for example, they could have neighboring cells, and we can kind of transitively go through neighbors of neighbors. And in this case, then we get kind of these cells. And if we go then further, we can again look at the vertices that are neighboring to those cells. And kind of what we end up with is these 6 vertices. And what we started off with was kind of this initial cell here. And this is what we call a local neighborhood. These 6 vertices, that's a local neighborhood of this cell. There's 3 close and 3 farther away vertices. And this local neighborhood it's defined by this, what we call a location chain, by this chain of location types, which in this case we went from cell to edges to cell to vertices. So this location chain, it defined a local neighborhood, and in the case of this cell, it defined these vertices. And once we can define local neighborhoods, we can start writing stencils, because our local neighborhoods will then they will define our extent of stencil that we want to write. And that's kind of a generic way to look at neighborhoods. And I mean, one reason, or like one challenge with triangles is that in comparison to like Cartesian grids where you use rectangles, with rectangles you always have natural neighbors, which is top, down, left, right. But with triangles you kind of have that too, but it's not clear. You have like up-facing triangles and down-facing triangles, and we thought we can maybe distill this further down into more fundamental components, and that's kind of the concept that we came up with, these neighbors, and then we use neighbor chains to describe local neighborhoods. So here we're gonna go through an example stencil. So this is this Python subset, statically typed Python subset. You'll notice this probably looks quite similar to GT4Py, and that's definitely true. So GT4Py, that's coming from the Grid Tools ecosystem, and that's mainly developed at CSCS. They're very close collaborators of ours. You will see Grid Tools mentioned probably a few more times as well. And they do some really interesting stuff with GT4Py. And yeah, their syntax is fairly similar, and we'll see. Maybe in the future we might even converge, because we will probably collaborate more closely again. So this is our Python subset. It's a function that takes a bunch of parameters, and it has this stencil marker. This is tells the dusk that this is a stencil that we want to convert. And this stencil is kind of relevant for such a triangular mesh. And we're just going to go through this step by step. So we have two fields that they're defined on vertices. So these two fields A and B, they will have a value for each single vertex. They can have different values for each of those vertices. Then we have a field defined on edges. So this would be, for example, if you had a stencil with a staggered grid, you can define a field that is defined on these edges. So for every single edge, it can have a different value, this C field. And then basically this keyword with levels upwards basically says run the stencil over the whole domain. So level upwards kind of is meant here the vertical domain. So you start at the ground level and you work your way up towards the sky. And yeah, it can. And on the horizontal domain, we kind of run the stencil always parallel, because that's kind of how stencil computations work. So then we have here a neighbor chain where we say we start off an edge. So let's take this edge as an example. And then we go to the neighboring cells. And then once we are at the cells, we look at the neighboring vertices of these cells, and those are the ones that we get. And basically the whole neighbor chain tells us, well, for this edge here, the local neighborhood described by this location chain are those 4 vertices. So we call this the diamond shape, or the diamond on vertices, because it kind of looks like a diamond. And every single edge will have this local neighborhood defined by this location chain. And with this extent, then we can say, well, for each point in this neighborhood, we will compute a value, A plus B. So we will take the value of A at this location plus the value of B at this location. And here we take the value of A at this location of this right vertex plus the value of B at this location. And we can add them all up. So we can compute expressions on our local neighborhoods. And then we use this keyword sum over, where we just say, well, we take all these values and then we sum them all up and reduce them onto our edge here. And that's kind of how we do our stencil here. And so kind of the ingredients are kind of, we use this location chains to describe neighborhoods. And then we can compute values on those local neighborhoods. And then we can, for example, we can reduce them with a plus operation. There's some other operations we can use, such as max and min. And there's some other parameterizations that we can add to this whole model, such as, in some cases, we need weights. But I don't want to go too deep into this. But that's kind of the main idea that we're kind of using here, is to kind of use these local, these neighbor chains and these neighborhoods. And I mean, this is kind of a complicated system. But one motivation was kind of a bit the generality. So this model kind of works for any unstructured two-dimensional grid, so triangles, rectangles, hexagons, and in theory, it's kind of all it needs is a two-dimensional planar graph, and then it would still you would still get well-defined kind of neighborhoods. But I think a word of caution here: if the mesh is highly unstructured, then it probably is not reasonable to write stencils for such highly unstructured meshes. But I think for our use case, it's sufficiently general. So, for example, we can support rectangles and triangles, and I think most like numerical weather models or climate models will aim for fairly regularly structured meshes. So, for example, the Icon mesh, it's technically unstructured, but the vast majority of the parts will be very structured. And so, for these use cases, this model, I think it's general enough, and that's something we appreciate a lot. Okay, so I want to talk a little bit about Dawn. So that's kind of where the compilation happens. So Dawn is a compiler toolchain to enable generation of high-level DSLs for geophysical fluid dynamics models. Dawn has a bit of a longer history than Dusk, so it's been developed since 2017. I think it started off with a master's thesis at ETH, and it was initially conceptualized for handling finite differences on Cartesian grids, and it targeted the Cosmo model. So the Cosmo model is the predecessor of the Icon model. It used rectangles, and it had this pole problem where these singularities occurred, and that's kind of what we're running operationally at MeteoSwiss right now. It has a front end called GTClang, which is a DSL embedded in C++, and with this we could express all the stencils in Cosmo. So GTClang, it's aimed at structured at rectangular grids, right? Whereas Dusk kind of is aimed at these unstructured grids. So in GTClang you have this these top-down, left-right neighbors, and you can use the coordinates I and j, where you say j plus 1, I plus 1, and the neighbors are much easier. But the kind of the neighbor chains, that's what's happening in Dusk. And there's a wide array of optimizations implemented in Dawn for this for these rectangular meshes, and it has various backends. So there's a CUDA backend, there's a C++ naive backend, and then it also targets the grid tools framework with the multi-core and the GPU backend. Yeah, so grid tools kind of is a template meta programming C++ library that also can do some kind of stencil optimizations through template meta programming. There's some really crazy stuff happening there, and that's also been used for Cosmo at some point. So yeah, Dawn was used to translate the whole Cosmo die core. So the dynamical core of Cosmo was translated with Dawn. This is a fairly complicated. It's not a very trivial die core for sure. It contains an advection scheme, a diffusion, and a triagonal solver, and it outperforms previous efforts of translating the Cosmo die core using DSLs with much fewer lines of code. So then there is a paper that we published on this where we compared Dawn to Stella. So Stella was kind of the predecessor of grid tools. This was it used a bit of C++ template meta programming plus a bit of C++ macros. And the Cosmo die core was translated with Stella as well. That was the previous model that we ran operationally. And basically Dawn is kind of, yeah, gives better performance for every single stencil, or at least as good, mostly better than what Stella did. And it has some, I would say, also some really big advantages. So for example, because Stella was implemented with macros and template meta programming, error handling was very difficult to achieve. And I mean, I would argue that the error reporting was very poor. I'm not sure if you can say Dawn is high quality error reporting. I'm not sure if there's any compiler that has that, but I would say that it's definitely still an improvement. And it's also not fun to debug template meta programming in C++. So that was kind of a pretty big success. And now I want to also highlight a bit the current developments of Dawn. So the Cosmo model is at end of life. The last release 6.0 is being prepared right now, and I don't believe there will be any more releases aimed at. And basically most of the organizations that ran Cosmo, they are looking to migrate to Icon. And Dawn naturally then needs to adapt also to new models. So there's kind of two models that Dawn is kind of targeting right now. And one is this Icon model that I presented. And here kind of MeteoSwiss, we're taking the lead. when it comes to developing a Dawn for Icon. And then the other model is this FV3 model. It's based on finite volumes on rectangles. So they used a dice subdivision to avoid the pole problem. Here, the development efforts on Dawn are led by Vulcan. Those are our collaborators in the US. And they're targeting to use Dawn there and to do the demonstrator with Dawn. So some concluding words on Dawn. So Dawn is able to translate most of the icon stencils, and the number of line of codes. The line of codes, I would say, improved greatly, especially if we compare it to what we looked at initially. The code is kind of automatically parallel, and I think it's legitimate to say that there's a big potential for improvement in maintainability, especially once we're able to kind of separate the hardware optimizations from the model implementations. I think there's a very, very huge potential here. And then also the code emitted by Dawn is kind of able to compete with these OpenACC codes. So if the Fortran code is ported to GPUs with OpenACC by hand, then Dawn is still very much able to compete with that. So Dawn is not yet able to translate all of the features in the Icon Die core. There's some features that we cannot support yet. We do a lot of work to add features to Dawn and Dusk so that we can support that, and we kind of are steadily working our way step by step through more features. And Dawn by design requires existing climate model code to be rewritten. And I think this is also where we can really contrast this evolution versus revolution approaches. And I think this is I think there's a lot of advantages with this very kind of pure DSL approach. But at the end of the day, your DSL code has to live somewhere, and it's probably going to live in separate files, and it's probably, you cannot avoid kind of code clones in the worst case scenario, because you just have to write the model again in DSL. And I think, this is something where we can really contrast kind of these two approaches, and I think it's a drawback that needs to be mentioned, and people need to be aware of that. Nevertheless, I would say that this approach also gives a very, very big promise with respect to maintainability, and also being able to really kind of separate these different concerns apart from each other. And I think once you're able to kind of write in a high level DSL where we can really focus on the model code, I think there's just a huge benefit that this approach offers. But still, I think on a high level, it's very fair to contrast these two approaches. And I think it's just for sake of transparency, it's important to be aware of what are the pros and cons of these two approaches. So I think that's a really interesting and a very challenging kind of situation. And I think we'll have to see what the future brings. And I don't think I want to claim that one approach or the other is like ultimately the right or the wrong. But I think this will be a big question of how these two approaches develop, how they are being adopted. There's a lot of parties involved with very different interests and goals. So I think that's a very interesting point to kind of contrast this revolution versus evolution part. So here's a very preliminary result of Dawn. So basically, this is a single stencil. This is very preliminary, so please take this, enjoy this with caution. So if you look at the runtime of Icon ported with OpenACC or the runtime of a single stencil of Icon that has been ported with OpenACC, and we kind of compare this to what Dawn does without any optimizations, then Dawn is quite a bit slower. But once we enable optimizations, then Dawn kind of can catch up again. And there's actually two things I want to say this. So this is very preliminary, but it's kind of interesting. These kind of bars, please keep in mind that they can move, because Dawn, I think it has a lot of still potential for improvement. There's a lot of optimizations that we still would like to add to the unstructured, to the handling of the unstructured features. So I would think that this goes down a bit, but the same is true for OpenACC. There's this really interesting case where we recently upgraded the PGI compiler. So PGI supports OpenACC for Fortran. I think it's one of the only kind of compilers that does this. And PGI got an update, and all of a sudden we saw that in the Cosmo model, which was ported also with OpenACC, at least parts of it, we got a 5% improvement. So kind of this bar can also move, and it's kind of interesting how these kind of move over time, and it's not clear how exactly they will develop. I mean, OpenACC has a very big question mark as well, because it's really unclear whether NVIDIA will keep supporting OpenACC and PGI, or whether support will be dropped. So I think the future last I heard is fairly unclear. But yeah, kind of these two bars, they kind of compete with each other. But additionally, I would still say that Dawn kind of has one big edge over OpenACC, and that's that Dawn can work on a much higher level than OpenACC. Because in Dawn will get as input kind of the high-level stencil representation, whereas OpenACC will get pure Fortran loops, right? So it's just Fortran loops, and then OpenACC, if you want to kind of add more optimizations, you need to the OpenACC approach. In the OpenACC approach, the compiler would have to kind of do more involved analysis to figure out kind of to get the same information that kind of Dawn gets for free, because Dawn works at a much higher level. So I would say Dawn still kind of has an edge. Nevertheless, I think OpenACC, who knows, maybe it will catch up. But I would still, I'm not even sure if the performance benefits are the main benefits in this approach, because I think the main benefits is really this aspect of maintainability and being able to separate different components. And let me just kind of stress this. So last week there was the Icon developer meeting, and there's been some really good talks on many interesting topics, and there's some really interesting projects starting and ongoing. But one kind of big conversation point was always kind of, how do you support different hardware architectures? How do you maintain the code? How are you able to make things fast on different hardware architectures? Because we at MeteoSwiss, we have GPUs, and then in Germany there's vector machines, and then there's a lot of people still with CPUs, and then yeah, the hardware market it's super exciting these days, and I mean that's always been a really big discussion point. And I would argue that the performance benefits might not even be the biggest advantage of this approach. The biggest advantage might really be the kind of the maintainability, and that you're able to separate these concerns from one another. So I also want to say a few words on the interoperability. So the current workflow is that we process the stencils with Dusk, feed them to Dawn, and Dawn will give us a stencils CUDA file, and then we also add a C++ driver, and that's what we can feed to the NVIDIA CUDA compiler, and then we get a binary executable that can run on GPUs. And so Icon is this humongous Fortran code base, and how this all fits in here is that, again, we have Dusk that feeds its stencil to Dawn, and Dawn produces this these stencils CUDA code that we can get into a binary file. But then Dawn also produces an interface, a Fortran file. So this is it gives Fortran C ISO bindings, so that we can call from Fortran through this file. We can call the stencils in our object file that was produced by Dusk and then runs on the GPU. And this all kind of bundled up in an interoperability layer. And then the Icon Fortran code base, you can replace the calls to the stencils with a call to the stencil defined by your interface. And then Icon will kind of start these stencils through this interoperability layer. And then we also need some utilities. So we need to do some setup so we get the right Fortran arrays, for example, for neighbor connectivity, and then so we get the right pointers to the right fields. And then for our purposes, there's some verification utilities in here, so we can run our stencils and run it together with the Fortran stencils, and then we can ensure that our output verifies with respect to some thresholds to the Fortran version. And that's for us. And then here also I put some links in the slides if you want to know a bit more. There's been some workshops and some upcoming workshops, but this is really if you want to kind of know a bit more and find out a bit more about the Dusk and Dawn. And I think with this I'd like to conclude this presentation. And also thanks a lot for your time and attention. And I think now we have some time for questions. Thanks a lot, guys.
Thank you very much, Ben. We do have a question. Will you be working on an NEC backend?
An NEC backend. You mean the NEC?
Yes, the
okay. I think that's a very good question. I think the answer is no, because we at MeteoSwiss were mostly going to focus on GPUs, but we're very open to collaboration. And I think it would be really interesting if if we found someone that would be interested in creating an NEC backend. And I think that that would be really interesting, because I know the German Weather Service, they're very they use these vector machines, and I think that's a very interesting approach as well. So we're very, very open for collaboration here. I think it would be super interesting.
Fabio, I saw you unmuted yourself. You had a question?
Yeah, I raised my hand. I don't know if that was there. I see Sebastian has a question too. I don't know if it was me or him, the first one. Well, anyway, going on. Yeah, so thanks for the talk. It was really, really nice. So my question is, did you? So I saw that this is a fairly recent project. It started in May 2020. If I'm not mistaken. So I wonder whether, did you consider using other DSLs before embarking in this journey? So the first one that comes to my mind is OP2. There are going to be quite a few talks about OP2. Since you're dealing with unstructured meshes, and since OP2 has mechanisms to represent and iterate and apply kernels on unstructured meshes, I wonder whether you consider that. And if not, I'm sorry, if yes, why did you prefer to go down a different route?
Good question. We did consider them. We did quite a bigger evaluation where we looked for other frameworks where we could build a front end with. And I mean, OP2 was part of there. We also looked at DeVito, and I think we're going to see this in this workshop as well. And also Pymbolic, I had a look at this, and I think there's actually quite some other talks that are going to happen. And we looked at these tools, and unfortunately, that we couldn't really find a tool that convinced us, because I think our requirements were a bit different for two reasons. First of all, we kind of looked, so for Dusk, we really looked for a kind of a front-end tool, right? So kind of really, and the goal was kind of to have a very nice front end and kind of be able to have it integrated and give it kind of a nice look and feel. And I think a lot of these tools, they do have front ends, but they're also very focused on kind of the whole also compilation toolchain, and kind of Dawn, it existed since 2017. So we kind of had the backend already. We just needed like a front end that kind of gave, converted some textual representation, some syntax file into basically some SIR. And that was kind of, most of these tools didn't meet the requirements there. And then the other thing is kind of, some tools didn't really fit us that well. Maybe I can contrast this with DeVito, and I think DeVito is a very cool tool with this really cool approach where you kind of start off with the high level equation and then you continue lowering it down with symbolic solvers. And I think that's a really cool approach. But for example, in meteorological and climate simulations, you really don't benefit anything from that, because all of our schemes, for example, advection schemes, they've already been kind of lowered by hand in separate papers, right? I mean, for example, in Cosmo and Icon, there's huge components that implement many different advection schemes that have been developed by people by hand, and there's been the literature is very rich with these methods. So we kind of we already know what our stances look like on the very low level, and we already know very well how to optimize them, because we have quite a history with Cosmo, grid tools, Stella, and that's kind of why most tools really didn't fit into them. But it was really interesting to compare these tools, and I think there's some really cool things that they are out there.
Okay, thanks.
Thank you. Sebastian, try unmuting yourself. Yeah, go ahead.
Okay, thank you very much. So yeah, thanks for the nice talk. I really enjoyed that. I find your notion of this connectivity chaining very interesting. My question would be a bit more on the technical side. How much do you specialize that for your grid data structures? So do you generate specialized kernels for the unstructured parts of the grids and the structured parts of the grids, or is just everything handled as unstructured? How do you do that?
I mean, for historical reasons, kind of both like structured and unstructured, they live kind of next to each other, even though you probably you're not able to use both together. And all backends are right now basically either only structured or only unstructured. And I think this is kind of, yeah, just there's a bit of history in Dawn, let's say. And also I think in the future we're kind of we're probably going to look into how we can resolve this. And I mean, we've actually done some experiments, for example, with MLIR. And I mean, I think in the future there might be a rewrite coming up. But yeah, right now these things, they just live next to each other, but I don't think it's possible to use both of them at the same time.
Okay, thank you very much.
So I had a question. Do you make transformations or optimizations which would require changes in some of the underlying data structure? So things like structure of arrays and array of structs, which then would need some sort of things to happen in Icon.
Yeah, that's a very good question. So yeah, maybe I could have talked a bit more about this, but I mean, obviously the memory layout is very important, and I mean, a big question kind of for us and also with Cosmo has been like Cosmo and Icon, they're written in Fortran, right? So all the arrays, they exist in Fortran. Their memory layout is kind of written in Fortran. Maybe with ifdefs you can do some changes, but you kind of need to modify the Fortran code for that. So the question is, if you want to use it, well, the question is, do you want to use a different memory layout? If yes, how do you do that? If no, what are your expectations with respect to performance? So I can give you the example of Cosmo. And in Cosmo, basically what we do in every single time step, before we enter the die core, we transform all the Fortran arrays so that the memory layout is better. And then we run all the stencils, and then we transform back again. And this transformation, I don't know, if I remember correctly, I think the number I have in my head is it costs roughly 10% of the die core step, but we get a bit more than 10% performance improvement from that. So overall, it's really worth to do this transformation in every single time step, once at the beginning of the die core step and once at the end of the die core step, because we do get better performance, but it's not you know, like it's not super huge. I think it outweighs a bit, but it's not humongous. And now in Icon, we are again at the same question: how do we do this? And there we're right now aiming for a different approach, where basically instead of in Cosmo, where we had the whole die core was written in C++, the whole die core step was written in C++, we kind of want to have a more fine-grained integration approach, where basically we still leave the Fortran code in there, and then we take one stencil and we replace it with a call to a generated C++ file, right, with this interoperability layer. And what this means is that, well, if we wanted to really transform, we would have to transform a lot of times, right, for every single stencil. So right now we're aiming for integration where we do not do any transformation. So we just take over the memory layout that Icon gives us, and we kind of, yeah, I mean, this, and it's unclear whether this is going to have an performance impact, because we did there's a bit of history of looking at different memory layouts for unstructured grids, and the performance differences found so far are kind of fairly small. And I think one theory why that is because GPUs have become a lot better at kind of optimizing general code. You know, the newer architectures are much more lenient with respect to what are coalesced accesses. They have better caching mechanisms. They have bigger shared memories and so on and so forth. So I think with this approach, you will see a very small performance difference, but it's very well possible that this is within like 1% or less overall. And that's kind of what we're aiming for in Icon, where we do not do any transformations. And also, then we can basically just take this pointers right away. And I think, yeah, there's some optimizations then that we can, for example, do based on that. And I mean, I definitely, I think the memory layout is important for what transformations you want to do, right? If you have, so I can use it as a space filling curve. So you can't really do blocking. In Cosmo, where we did the memory transformation by hand, we could add padding, and we had very clear blocks, and we kind of knew which warp was going to access kind of which memory addresses and so on and so forth. And we don't do this with Icon anymore. And I think unstructured meshes are definitely a challenge here. But like I said, so previous performance evaluations kind of indicate that modern GPUs are give you a very it won't have a huge impact on modern GPUs. But I think there's definitely a point to be made that at least some performance transformations will be affected by the choice of your memory layout, and then the question is, do you want to be able to control this or not, and how do you integrate this then with your model? I hope that kind of gives an answer to your question.
Yeah, it does. Yeah, thank you. So somewhat related to this, as you convert the dynamical core, you'll have many stencil loops following one another. So will you be able to somehow combine them and as the optimization happens, do things like, I don't know, loop fusion or something? So optimize across loops.
Yeah, that's absolutely the goal. I mean, you kind of start off with, let's say, one stencil, and then you replace another stencil 5 lines above, and then you keep growing them, and then yeah, they should merge eventually, right? And I think in the ideal scenario, like our stencils, they keep growing, and all of a sudden they will be the whole die core, right? And once we have the whole die core, then we can think about maybe we still want to do the memory transformations or not. And then also the goal is really to be able to do optimizations across stencils. So, for example, one kind of really interesting opportunity here is that, let's say you compile different modules, and at compile time, for example, you can figure out, well, because this module is activated and this module is activated, and they run after each other and they use the same field, if we fuse those stencils, then we can keep this field in shared memory, or we can eliminate storing and writing this field completely by just recomputing it just on the fly as we need it. And that allows you to kind of replace a memory store and memory write by just computations, which is kind of the most attractive optimization that we're aiming for, because we're basically almost always completely memory bound. I mean, our floating point Newman units will be heavily underutilized, whereas our memory bandwidth will be almost always 100% unless we really mess up something. So such optimizations are super attractive, and that's kind of also how where we expect the highest performance gains. And I think once we keep growing, then being able to look at optimizations across several stencils, there could be some really big potential for optimizations.
Okay, very interesting. Fabio, you have a question?
Yeah, I just want to to follow on this last question, which was super interesting. So since you were Ben, since you were talking about the possibility of fusing many different stencils together, which I totally understand. My question is more about, where are those stencils coming from? I mean, are they coming from the same PDE? Are they coming from the same system of coupled PDEs? Or what sort of stencils are you talking about? So first, if you answer this, and then I can follow up.
Yeah. I mean, I'm not sure if I understand this fully, but basically, I mean, in meteorological and climate science, you kind of, yeah, you start off with equations, and then you start discretizing them, and they're being discretized by hand by scientists in papers over many years, and improved, and then like more tweaks added to previous ones, and kind of then you already kind of get the stencils, and then you maybe have a scheme with a bunch of stencils, and you run them one after the other, and yeah.
Because so here's a comment I'm going to make. Maybe it's not even a question. So for example, in the Vito, as you said before, we start from the PDEs. So we start from the partial differential equations. So we have the whole PDE or the whole system of coupled PDEs. And it's up to the compiler, if it wants to split the discretized PDEs into multiple stencils. So in our case, we start, as you also said before, from a much higher level, starting point than yours. So what it seems to me is that you are doing the opposite, and you start from, like, someone is handing you some code, so you know that there's a chain of stencils, which has to be that because it's been, you know, studied, analyzed, implemented, verified, and so on and so forth. And then you are doing the optimization on a much lower level of abstraction. But my feeling is that from a software engineering perspective, if you started from a higher level, things would be much simpler. So think about this. To fuse those stencils, I think you have to do things like overlapped tiling. So doing things like redundant computation at the halos and stuff like that. And to do that, you have to analyze these stencils. While in our case, pretty much all of these analysis is for free. It's not easy to explain with few words. You would have to show
absolutely.
stuff, but I don't know if I'm explaining.
Yeah, no, I think I already understand. And I mean, it's kind of interesting, right? Because you're right? You start at a much higher level where you have so much more information, right? Like we kind of start at a lower level, and we need to recover this through kind of analysis, right? And it's interesting because, I mean, if we compare, for example, our DSL approaches, I feel like we're already starting at a higher level, right? Because there's, for example, Claw starts at an even lower level where you have like Fortran loops, right? We don't have, we kind of remove loops, right? We're a bit higher level, but DeVito is like then even higher level. And I agree from a software engineering perspective, I think DeVito is a much purer, much clearer approach. And I mean, when I researched this, I was very inspired by this. I think it's really cool. But I think it's what I'm not sure is about how does that work with when you already know how your scheme is discretized, like how much, whether you're able to control DeVito enough to be able to get the equations that you kind of know you already want.
I mean, with DeVito, you can, I mean, all you need to know is the maths. So, I mean, once you know the maths that you want to solve, then you just, you know, write it in the DeVito DSL, and then you get a shared library, a shared object that you can link into your code. I mean, that's one of the execution model we are working on. But don't get me wrong, I totally understand your point. I mean, I totally understand that you your codes are huge, and they've gone through many years of development and improvements, and they are super sophisticated. So I understand why you are doing things that way. It makes complete sense to me. I just want to draw these, you know, the analogies and to make a comparison, which I think is useful to both parties.
Yeah, I absolutely agree, and I think it's a really interesting point to contrast these two approaches. Yeah.
Okay, guys. Sorry, I have to cut this a little bit. We have to move on. Thank you, Ben, again.
Thank you.
And next up, we have Bence Keömley-Horváth, who is a PhD student at Bálint Catholic University, and he is going to talk to us about a COVID simulator. So let me just set up the screen sharing. Yeah, you should be good to go.
So it's kind of like. So can you see the slides? If no, then tell me.
We can see them, but we see this view with like the next slide and the current slide.
Oh, okay. So the other is view. Share, yeah. It's only my view. Okay.
No, it's good.
So I will talk about a university project that we started in April when the COVID started hard in Europe. That's a large project. I will talk mostly about the programming aspect of this problem. Me and my supervisor did most of the programming part of this project, István Legulin and me. So it will be less of a DSL problem, it will be a HPC problem. So I don't think that I have to introduce the COVID to anyone. So the main problems here that we want to have with is the controlling the virus is not very trivial problem, because we have to So the decision makers have to weight the health risk and the economic risk due to the lockdowns and the other decisions. And most models are very high level, mostly deterministic differential equations or a bit more stochastic differential equations. And in these models, it's not that easy to introduce some kind of lockdowns or other decisions because mostly they just have a few constants that will change the amount of interaction between the people. Therefore, we want to introduce a more detailed model, which will be an agent-based model. The agent-based model, every paper is an actually represented agent in the model, which means that it has attributes like the age, sex, and the preconditions and a lot of others. They can move between different locations, so we can actually simulate what the people are doing in real life. Of course, the result of this model has to be comparable with other deterministic models, and because of this, it has to be comparable with the real life known data. But because it's an agent-based model, we can simulate actual decisions like quarantine rules, lockdowning locations, mass regulations, and so on. In this small figure, you can see that so here the orange is an actual deterministic model, and our blue line is a run from our simulations. So we could achieve that part that that the model in a non-lockdown situation can reach the other model. So that was our goal originally, but then we can introduce other rules. So what is our input data? So every agent has the already mentioned attributes, and it also has an agent type. So every person behaves a bit differently. But we can group them into different type of different agent types. So these agent types are like a school student, university student, adults with different kind of jobs, and old people with pensions. And for every agent type, there is a typical schedule. This schedule is quite stochastic because, of course, the same type people are not behave exactly the same, so it has some kind of stochasticity. And in the schedule, we just define what type of locations they are going, so like house or workplace or school. But the actual location for this is specific for every agent. And of course, we have locations based on what are we simulating. Every location has its type, coordinates. It can be open and closed, and it can have an infectiousness attributes, which defines, for example, if it's an open area, then the infection ratio is mostly lower than in a closed location. In the first step, we want to simulate Szeged. For the foreigners, it's a middle-sized city in southeast Hungary. I will not talk about how we gathered all the information for this because it's a different topic. But mostly we gather data from the Central Statistical Office of Hungary, from a National Institute, and from other sources, which are sometimes a bit specific to Szeged, but we always try to be general because later we want to simulate the entire country. So let's talk about the code. We want to make this model very flexible because there are a lot of different models to simulate different parts of the cost, like the movement of the agents, the infections at different locations, the testing, and the lockdowns of different locations. And we want to be able to change it later, not by changing the previous code, but maybe introducing a new class which will describe the movement or the infection in testing. For this, we use this maybe known policy pattern. Here is a very small example. For this, we can move my cursor, yeah. So let's say we have the simulation class, which we actually have in our code, which has a lot of different data. For example, this movement data in this small example. And we want to have different kind of movements. We want to be able to define it as a template. So depending on what kind of movement policy we give to this simulation, it will behave a little bit differently. So for example, so here is an example of movement policy. And we can just give it as a template to the simulation class. And the simulation can inherit from it. It has a nice signature because it's also a template of itself, which is a template of the policy. So it can be a bit ugly here. And because it inherits from it, it will see this, it's protected functions. So it can call from one of its member function. But in the movement policy, we might want to use the private data of this simulation class. Therefore, we have to make it a friend, and then we can cast this pointer to its non-type that we know from the template parameter, and then we can use the inner data. And we can do different stuff based on what type of policy are we using. We can change. So this is a combine time technique. So we have, so in the, for example, the main where we create this simulation class, we just define the template parameters of the policies. Sometimes we want to change it using a CMake. So the user can decide what type of simulation he wants to do in combine time. For the parallelization, we use a trust algorithm library. This makes the parallelization very portable because it can do it on CPU and also on GPU using OpenMP or CUDA. It provides us standard containers that can store the data on the device, for example, a standard vector. So this will be called the trust device vector. That's the most often used by us. And there are also implementation for the parallel implementation of the standard algorithms, most of them, or a lot of them. And of course, these algorithms mostly use some kind of lambdas, like this normal standard algorithms. And for this, we need a device lambda, or can be sometimes host lambda, depending on the usage. There can be some problems with it, which the trust mostly solves. For example, we have a device vector, which we create on the host. Inside the device vector, there can be a pointer on the actual data that can point to the device. But for example, in an algorithm, we want to use the data on the device to access another vector. We know somehow they index based on the device data, but we cannot access another device vector using this index directly because the device vector itself is on the host. Only the data that is pointing to is on the device. So it's not possible to do it directly, but the trust provides us different kind of iterators that can help us in different kind of situations. And I will talk about these kind of algorithms that how we can use it in practice. Few words about how we store the data. So every agent and location has a lot of attributes, but we don't store them in an object. We store them in the structures of arrays. So every attribute has its own array, and of course the same index will be connected together into one object. So and we do the same with the locations, and we store them in a singleton that we can access from anywhere. A first very easy example when the trust is working very easily. We want to update the state of every agent. So every agent has a state which is stored in the mentioned array. And this is an update function. Here we just use the trust for each function, where we just put the begin and the end iterator of this array, and we have a device lambda that we just call this update function. And if everything is stored on the device properly, and we store them properly on the device, then it can call this function. But often we have to do some bit more complicated stuff. The next problem, we want to calculate the infection ratio at every location. For this, the input is the number of infected people at a location, the number of people at a location, and this infectiousness parameter of the location. And from this, we want to calculate what percentage of the people will get infected in the next time step. So here we have a lot of different data. We want all of them together, so all these three data. And we want to do some kind of transformation because we have all this data. We want to output of this solution ratio into an output and the lambda function will do the calculations based on this data. And the trust provides us a zip iterator and maker functions for it. Here we can just put all the iterators together, so the iterators of these three vectors in a tuple. And in the lambda, we will get a tuple of these iterators. So the type of this tuple will be the reference type of the values of this tuple. And then we can do any calculation in it, and we can return the calculated ratio, and it will be pushed into the output. But sometimes it's so most in the 90% of the cases we can solve most problems with these iterator tricks. There are also other iterators like permutation, transform, and counting iterators. We can solve most of the problems with it, but there are some cases when it's not possible, or if it's possible, then it's will be either very ugly and maybe even slow, probably slow. An example for that is actually a calculation that is before the previous task. We want to calculate the number of infected people. It was the input of the previous algorithm, but because of I am going to this logic I mentioned later. For this, the input is we know the position of every agent in an array, which is the length of the number of agents. So here is in every position there is a location index which is connected to that agent. So where this agent is actually the moment. And we also know the state of the agent, but we will use it later. We need the state of the agent to know if it's actually infected. And from this, because we want to calculate it for every location, but here the locations are mixed in this array because so it's sorted by the agent's IDs. We want to sort it in a way that we store the agent IDs grouped by their location. So the agent IDs at the beginning will be at the location of 0 and in the location of 1 and so on. This part is even doable with it's just a sorting by key, because we know so we just ask the position of the agent, and we know its index, and we just put the index into this this agent. This is doable. It's a bit slow actually, so if we don't have big performance problem at the moment, but in the future we could solve it a bit better, because at the moment we have to solve this array in every time step, but most of the people are not moving in every time step, so this array will be almost sorted, so we could just optimize it in a way that we just sort it partially. So we just sort the change part, but we don't have a performance problem at the moment, so we didn't do it yet. But from this, we need an offset of the for the locations. So to iterate, so here we store the agent IDs. At base of the agent IDs, we want to know where is the border of the first location, where is the border of the second location, and so on. So for this, we need an offset for the locations. My cursor is sometimes diminishing. For this, it's a more problematic problem because we have an array where we need the index of the agent, and with that index we have to get the locations. So it's already a bit of problematic doing with iterators. So at this point we started to write kernel functions. So we get the pointer from the device vector, and using those pointer we do this calculation directly in a kernel function. So we cannot use this iterators techniques. And in the next step it's even more complicated, because even so, if we have this offset vector, we want to calculate how many person is infected at the location. But if we think about it, we have to go through every locations. So we have to go to this offset of the locations. Based on these indexes, we have to go through the other array where we know the index of the agent. And with this index, we have to index in the array of the states. And from that, we can get the infectionsness of, if it's this agent is infectious or not. So it's a very complicated to do with the iterators. So for this, we also had to write a kernel function. So let's talk about the performance. So it's a highly irregular problem because there are a lot of different kind of calculations where we just create different arrays, and it's not something like having the same data over and over and doing some calculations on it. So here the bandwidth, we don't really want to really calculate the bandwidth because it depends mostly on the kind of calculations that we are doing. So we have a lot of different kind of if conditions in the calculation. So it's a very irregular problem because we have to do a lot of different kind of stuff. But we measure the performance on the CPU parallelization, the GPU parallelization. So for I think a 21 weeks simulation for this Szeged city. On single core it was 180 seconds, and with 32 cores it went down to 33 seconds or something like that. So even at the 16 sets we get similar results. So this is the maximum kind of the maximum performance gain that we could gain. So kind of 6-time gain on CPU, and on GPU we achieved 19 sec runtime, which is almost a 10 times difference between the single core parallel and almost a 2 times difference with the maximum of maximum number of CPU parallelism. I will not talk much. I will not really talk about the results because it's not a biological conference. But here you can see a few results based on what type of quarantine policy are we using, quarantine rule are we using. It's a policy in that way. So the red line is when we don't have any type of quarantine. The green line is when we only put those persons in quarantines who tested positively. The blue is when we quarantine the family of the positively tested person, and the black is when we quarantine the entire workplace or school of the tested agent. And you can see that it makes quite a difference. You can see we can produce a lot of different outputs, like how many people are on the intensive care, how many testings we have to do, how many people are quarantined. Of course, it will be very high for the stronger quarantine rules. The number of positive tests, quarantine the infected person, and you can see this. So this is the power of our model, that you can introduce very detailed rules, and you can see that there are quite a big difference. So at the moment we are at this stage, we are still adding a few new features. There are a lot of other rules that I didn't show here an example, but I think that's what I only wanted to mention, and thank you for your attention. I don't know if there is any questions.
Thank you. Questions?
Yeah, a second.
Okay. So if you do have questions, let me know. Fabio, I'm not sure if your hand was left raised or you have a question now. So a question from me. Do we, or how do we expect this to scale from a city to a country or maybe even a continent?
Well, I'm not quite. So most of the calculations are depends on the number of locations and the number of agents, and maybe only the sorting algorithm that has a n times log n or on parallel is a bit better complexity, but I think it will be very close to linear dependence on the number of agents and locations.
In terms of how much data, how we get data.
How we get data? Well, that's a different group in the team. So those data that we could get from the Central Hungarian Statistical Office, it will be good for country level simulations. And we can also, so if you don't have a few types of data, we can also generate random data. So if you don't know someone's actual workplace, we can just randomize them, and it won't really affect the actual behavior. On continental level, it will be a bit more complicated because it depends on what kind of input data we can have. How many agents are there in the models at the moment? So Szeged is a middle-sized city compared to Hungary. It's a bit less than 200,000 agents. So yeah, Hungary is 10 million, so it will be, of course, much slower, but we are still talking about a few dozens of seconds of runtime. Yes, Kocsis.
So in your model, did you introduce any delay after the infection event, or the agents are becoming instantly infectious agents after?
Okay, so the question was, maybe you didn't hear it, is if I'm introducing any delay after the event of getting infectious, or is it instantly? So we have a so when an agent gets infected, it will get into a state, which is the first step of the infection, and then there is a graph that is also an input data that we can modify, which we describe from which state what chances are that it gets better or worse or some other state. So there is a tree that will so it's similar to the Markov chain where you have a state and there is a chance to go this and that position. So at the beginning, it get infectious, but to get infectious, there can be another state because every state has an infectious rate. So the second question, does the agent-based modeling prioritization would make a feasible estimation for 1 million agents in an artificial community? So we already made a lot of simulations with more agents, not just this 200,000, because we can generate totally random input data, kind of totally random. The user can also define some level of the randomness. We also run the model with 1 million or even with 10 million agents, and the prioritization worked pretty well. So it didn't run away, and the memory cost was also terrible. So Kalman has a question. Please speak up.
Yeah, actually trying to show myself to you. So my question is very similar to the previous one. Do you know any constraint that if you reach that constraint that this simulation won't work anymore? So let's say 1,000 of millions of people or so. So there is any known limitation?
So maybe the only algorithm in the entire model is the sorting that probably doesn't have an interlinear scaling. And the other problem is, of course, the memory. So at the moment, we didn't even really measure the memory usage because it was almost not relevant for 200,000 people. But of course, it's 100, a lot of agents, maybe the memory can be a problem. So maybe at that case, the GPUs are going to be a bit more expensive to run on a GPU. Then we can only run on CPU if we have enough memory there. But I don't know any other direct constraint. Any other questions? Because Fabio is still waving. Okay. If not, then there is lunch.
Okay, so we are gonna break for lunch. We'll be back in an hour at 2 o'clock our time.
Mert nem, és nem csinál semmit itt az oldalon.
De ez valami jobb gépnek tűnik.
Most hallak titeket.
Optikai. Akkor jó.
Köszönjük, elszállt a Zoom, azt most újra kellett.
Zoom. Én jelszómat kerestem egy órán keresztül.
Hello, everyone. Let us return from lunch and resume with our next talk. Gihan Mudalige from the University of Warwick is going to tell us about DSLs and our approach to doing it.
Hi, good afternoon. Good afternoon from Warwick. Yeah, thanks Istvan for the invite. I'm actually at Warwick today. I was teaching, a very social distance teaching, by the way. Can everyone hear me? It's the first time I'm doing one of these.
Yes, all good.
Yes. All good, right? Okay, so let me just full screen this. Okay, so the idea of today's talk is, so the people that know us, myself and Istvan, about using DSLs in high performance computing. Essentially, the talk today, most of the stuff that will be going through, people would have seen previously in our talks, but there's some new developments as well. So what I want to talk about is what has happened with the complexity that's been increasing ever since we've been moving into many-core or multi-core, massively parallel architectures. And this has significantly increased the complexity of how we program these devices. And so the problem really started to emerge, or indeed become really apparent about 10 years ago when we were looking at this. And then most of this work was coming from that time up to now. So the things I'm going to talk about is really a contribution of lots of people that have come before me and have initiated this idea of high-level domain-specific languages, especially at Oxford, Mike Giles, and then at Imperial, Professor Paul Kelly, who really started this work back in 2010. And then, so we basically continue on these DSLs. So it's really a lot of work coming together, and what I'm going to talk about is contributions from all of these guys here and many more. So let's just first look at why we are here. So essentially, many people must have seen this. We started the frequency scaling, or increasing the frequency of microprocessors, ended in 2004. It's more than a decade, about 15 or 16 years ago. And suddenly, the hardware vendors realized that because increasing the frequency will, increase the consumption of energy, the physical limits of silicon has come to its limit, and suddenly they got this requirement. Well, what are we going to do? What are we going to do to keep increasing performance at historical rates? So they threw up their hands in despair and said, okay, we are going to just put multiple cores on a single, on silicon, and leave the problem of programming them to someone else. And so David Patterson back in 2010 aptly put this as a Hail Mary pass, where the hardware vendors has basically assumed that this will be sorted out sometimes later. It's a very American term. I hope people understand what this means. It's basically you don't have a receiver at the end. The solution is still not there, and the hardware vendors simply threw the problem at someone else. And I suppose we are still trying to catch that ball that's still up in the air. And so more recently, the same graph was discussed in the Turing lecture by Patterson and Hennessy, who won the Turing award in 2018, where they laid out the previous graph with the different eras of microprocessor architectures, where we are actually, because now the hardware is really limited, the CMOS semiconductor technology is coming to an end of life, essentially. And so most of the tricks that you want to do to get higher performance, to continue increasing performance at historical rates, is down to how you program them. And so you've got this golden age, as they noted, a golden age of parallel computing, parallel software development age, where really you need to eke out as much performance as possible from the way you write your program. And so that has led to a diverse hardware landscape. People have seen lots of different types of architectures coming and going. So you have traditional CPUs, for example, with the usual vendors, the major vendors now, Intel, AMD, ARM coming into the playing field as well, and IBM. Traditional CPUs having more than 20 cores or more, and deep levels of memory hierarchies and long vector units, essentially, again, increasing parallelism, much more, more threads of execution, longer vector units, and so on, making things complicated to program them for performance. All right, and then some time ago, back in 2010, 2009, GPUs with NVIDIA's Tesla cards came into do numerical computing or high performance computing, and then that trend has continued with other vendors introducing GPUs that are able to do high performance calculations, supporting double precision computation. And so most recently, Intel has started developing their own GPUs for this domain. And they have much simpler cores, more than 1,000 usually. And these are single instruction, multiple thread cores. And then there's different types of cores coming up as well, CUDA cores and tensor cores for AI applications, for example. And then again, we've got levels of cache with stacked 3D RAM, 3D stacked RAM, and so on. Again, different memory spaces and so on. And we've seen things like Intel Xeon Phi come up and then really getting discontinued, and that is actually, if you look at it deeply, if you look at it, if you examine the reason for this continuity, I think it's simply because there was no easy way to program it to get good performance. And the thing, from the experiments we were doing with the Xeon Phi, it was apparent that a traditional CPU, Xeon CPU, could get almost the same performance as a Xeon Phi at that time. And so there was no real gain. So that was discontinued. And then we see things like heterogeneous processors, where you've got GPUs linked with high performance CPUs with high speed networks like NVLink. And then of course things like architectures such as FPGAs or reconfigurable hardware coming up. And then the main motivation being them giving significant energy savings. And then to program something like an FPGA, it's even more difficult because you have to completely, do something totally different to what you would have done in a traditional programming sense. programming these devices. And yeah, so so hardware keeps coming because we are at this end of the era with Moore's law and so on. Well, the Moore's law continues. Of course, we keep on doubling transistors, but then there's no real way of programming these devices, and that's the real problem. And so moving on to Exascale, really, so then we are really not sure what an Exascale system would look like, right? So Exascale would be realized as you would, understand from the recent purchases or recent procurement exercises of, DOE Labs machines for Exascale. There may be different ways. There's definitely going to be different architectural ways of realizing Exascale. But what's not really clear, then again, is how would you utilize these architectural, these different machines or different massively parallel machines. So in one sense, the diversity of hardware has also led to an even more diverse ways of programming them. So we keep getting these acronyms for new programming models and languages coming again and again. We've got OpenMP, we've got SIMD vectorization, CUDA, OpenCL, OpenMP4, and OpenACC. Latest in the line is OneAPI, which is based on SYCL, ROCm, MPI for distributed memory, and then PGAS, global partitioned global address space, way of programming. Then there's task-based, things like Legion from Stanford, and more. And what I've seen and what people have come to realize is that open standards, which are very good to have, because they are open and lots of consensus needs to be gained, they have not been agile enough to catch up with this changing hardware architecture landscape. So they've always had a bit of a lag going on, catching up with the latest hardware or giving the best performance on the latest of hardware. And then hardware vendors bringing new architectures will usually bring a new programming language with it. And a good example is something like CUDA or OpenACC. And so proprietary models such as these are restricted or narrow to a very narrow vendor-specific set of hardware. So I put OneAPI in that. I'll explain why maybe OneAPI would, because it's based on SYCL, being an open way of programming, it might turn out to be different. But then, the idea is the proprietary models is then very narrow and focused on a vendor-specific hardware. And then we see that there's different code paths or parallelization schemes that are required to get best performance. I'll show you an example later. And this means that even if you write with one model, you have to write different codes with the same model, right? So you would be writing CUDA or let's say SYCL, and then you have to do different things or write a different parallelization in SYCL to get the best performance on different hardware. And so that's, again, a huge stumbling block in trying to get a unified way of programming or an easier way of programming these devices that will, in turn, give a higher performance or the best performance capable from that device. And then we have legacy codes. I mean, goodness me, there's so much Fortran code out there that, if you look at the new languages coming up, the models, the programming models that come up, you see it's going to be really difficult to get all that Fortran code converted to the latest programming model that's coming out. And so that we need a way to handle these these legacy codes, because otherwise, people who have invested so much in developing these codes are going to instantly lose everything, instantly lose their software base, their production code base, if you cannot use these codes any longer on upcoming hardware or modern hardware. And so, so we have this moving target of trying to write software for emerging hardware with various different complexities in the hardware. And there's no real clear, we don't know what hardware approach is going to win in the long term. And so, people cannot be recoding their applications for each new type of architecture or parallel system every time something new is announced, right? Some new program or new programming model or new architecture is announced. You cannot be rewriting your 100,000 line or million line HPC code. And so there needs to be a way to future-proof your applications for continued performance and portability. And we call this as performance portability together, which essentially means that you need a way to write your program such that it can be executed on current novel architectures and emerging architectures without significant manual modifications. Yeah, so you need a way to future-proof your code so that you are, up to a certain level, you are confident that whatever that comes up next, there is a path forward to obtain the best performance from the upcoming, the new architectures. Otherwise, of course, you're going to have significant loss in investment, where the applications, as I said, overnight will be not usable on these new emerging architectures. So that's really the motivation of DSLs in HPC and the work that I've been doing with my colleagues over the past 10 years or so. And so the idea is to rise the level of abstraction. So this diagram is really taken from a very interesting talk given back in 2015 by Professor Paul Kelly at Imperial, who really taught us about compilers, being a compiler expert himself, where the traditional compiler, when you view a traditional compiler, a classical compiler would have these two halves, where you have an analysis phase, where the code that's written is analyzed in order to identify its structure and all the information that can be gathered. It checks for syntax, semantics, pointer analysis, and try and do as much analysis as possible. And then the other half is essentially spitting out code, spitting out better code, improved code, optimized code. And so what he said was that the higher you can get in your analysis, the bigger the space of code synthesis possibilities. So better optimizations, if you will, if you can get higher in your analysis. And so the problem here is that if you start at a lower level, like a general purpose language, let's say C, C++, or Fortran, climbing up or climbing this analysis hill is difficult. You need to, because compilers are essentially trying to be safe first, they are really conservative. It needs to be, it needs to analyze the code in such a way and figure out if it's going to do some optimizations, that these optimizations are safe for the code that is written. And if you start lower, this is really difficult, right? So it's going to be really difficult to get to a higher view of your program if you start at a lower abstraction level. And usually the problem, a majority of the problem, a significant problem, is the way people are writing their code. Most people, the way people are writing, it's not easy for a compiler to analyze. There's lots of issues that, lots of weird and problematic things that a user could do that can put off a compiler from applying that greatest optimization it wants to do. And so what we can do is, of course, start higher, start at a higher level. And so that is basically giving you a bigger space of code synthesis possibilities. And then, what we would like to see is that even if you start higher, you can get the same or better performance as code written by hand. And then if we start at a higher level, could that give us a view to target different parallel architectures, right? So this is the idea where we want to increase the abstraction, and by doing so, we would get a better view of what code needs to be generated for different architectures, right? And so even you may be able to go higher. So you might think currently you are at general purpose languages. We might look at it at a computation communication skeleton level, where what target of the what the motif is. So people might have heard of Seven Dwarfs by Phil Colella, an idea that almost the majority of HPC codes can be categorized into these seven dwarfs or motifs that keep on repeating every time you look at HPC codes. And since then, this has been extended to, I think, 13 or 14 dwarfs later on. But the traditional HPC codes can be fitted into these seven dwarfs, and maybe we want to start at that level, looking at codes at identifying which computation communication skeleton it falls down to. Or you can go up even higher, maybe look at the numerical method, and then look at how that numerical method can be implemented best on different architectures. And then maybe you can produce that, target those architectures, target the algorithms for those architectures somehow automatically, or even go higher, right? At which point you can simply specify the problem and leave the implementation to select different solutions, could be radically different solutions, to generate code for using different architectures or targeting different architectures. So this is the idea of getting higher up, and so with the work that I've been doing with my colleagues, we've really seen the benefits of going higher, and essentially it has enabled us to reuse a body of optimizations or code generation expertise for a given class of applications, a domain-specific set of codes, and then generate how you would know exactly the best way to generate for that class of applications for a given target set of architectures. And so that leads us to this idea of providing a API or application programming interface that is domain specific. And so what this means is that we are going to basically provide an API that establishes a contract with the user, and in this case the user would be some scientist or engineer who wants to write the program and then execute it on all these architectures. And so if you write your program at this higher level in some API, so then it is the job of the framework to target and generate the optimum code for different architectures. And this was really aptly the idea was put really clearly by Professor Mike Giles, who said that OP2 and OPS, the two libraries, the DSLs that we work on, are actually straitjackets. They're trying to restrict the user from writing bad code by providing this API, and then allowing us, the experts in generating code or generating optimized code for a target architecture, do the actual implementation, and not burden the user at the same time as not produce bad code or poorly executable code. And so, yeah, so the API is at a higher level, and then a lower level would then enable, experts to optimize these codes or target different architectures using the best possible optimizations. And so the idea is you declare the problem at a higher level without specifying its implementation, and then provide a lower level that can then use automated techniques. And this is a key point here. We want automatically ways of translating the higher level declaration down to a concrete optimized implementation. And that would mean that we can exploit domain knowledge, because we are restricted to a single class of applications, and we are not in a general purpose language anymore. We can exploit domain knowledge for better optimizations for a given hardware system. And so this is the optimization knowledge simply comes from people trying to write hand-tuned code for a given architecture, but we want to reuse that hand-tuning knowledge, the expertise of hand-tuning and getting eking out the most performance from a given architecture, but we want to implement that by automatically translating the higher level specification of the problem for that domain. Right. So one of the first DSLs that, we call it active library those days because we had a code generation step there. Essentially, so OP2 was for unstructured mesh applications, and when we were developing it, it came about as a embedded domain specific language where we embed this higher level API in a general purpose language, simply because this then would be much easier for someone to start using, because people have general purpose programming language knowledge. Scientists and engineers do programming in C and Fortran, and that's their sort of bread and butter. And so we didn't really want a new language introduced, because the cost of conversion of all these codes from old Fortran or C, C++ to a new language would be very, very difficult, prohibitive. And so if we embed this API in a language that people know, a general purpose language, we get something like OP2 and indeed OPS. So what we did earlier at that time in 2010 or so was target this class of applications known as unstructured mesh applications, where really the key difficulty in optimizing these codes, or the difficulty in parallelizing these codes, were the indirect increment that happens, because in unstructured mesh applications, the connectivity between elements are explicit. You've got explicit connectivity information that needs to be provided to the program, and these are what you call mapping tables. So, for example, if you have a mesh such as this, where you got sets such as edges and then vertices or nodes. In order to create the geometry, you will have to say what cells are connected to what vertices and what cells are connected to what edges and so on. So you have to provide these explicit mapping tables. And so what OP2 did at a higher level was to provide this API where a loop over the unstructured mesh can be declared at a higher level using this construct called a OP par loop, where you can provide the elemental operation that goes on at each point of the mesh. So say you're looping over the edges and you are doing some calculations such as this. And so if you declare this in this verbose API, later we can pick up this information and the elemental kernel and translate this into different parallelizations for different architectures. And so the key point here is, for unstructured mesh at least, was the mapping table and the indirection and how to handle this indirection. So you can really see that if you are, if I just skip over a couple of places, so yeah, hold on. If you skip over to the handling data races, where if you have an unstructured mesh such as this, there are different ways of handling the data races, where if you have multiple edges trying to update data on a node that is shared between the edges, then you are really at a point where you have to manage that data race. So this is exactly what we want to do. We want to figure out from the declaration what sets are involved in this, what sets and maps are involved in this, and then generate code appropriately for different architectures. And so, later on, we found out that we can do the same thing for stencil codes or structured mesh codes, which turned out to be much simpler, because now you don't have indirections, and now it's a matter of providing a cleaner API and then affecting the optimizations. And in this case, the compiler needs to be able to see the various connectivity with the stencils, which is really regular, and result in optimizations for different architectures again. And in this case, OPS came about from the need to not only do just single meshes, but a collection of blocks that are connected by block halos, where it's a collection of unstructured mesh collection, an unstructured collection of structured mesh blocks. And so, and I'm sure many people in this workshop itself has talked about stencil codes, and this is really a key motif, key motif for a lot of HPC codes out there. And so the thing we did for OP2 for unstructured mesh, we found we can do a similar thing for structured meshes as well. And so the whole idea of writing a program then became something like this, where an application, a user will have to only write, what happens now? Okay, write the code at a higher level using this API provided by OPS and OP2, which is actually embedded in a language like Fortran or C. And then that is the only thing that the user needs to write. And then you can apply a source-to-source translator, and that's the start of your automated techniques, where this higher level code can be translated down to platform-specific parallelizations, and then that platform-specific parallelizations could be compiled using conventional compilers, because again, we didn't want to go down into say IR level, like doing an actual proper compiler. We didn't want to go to an intermediate representation. We actually wanted to leverage the optimizations provided by traditional compilers, vendor-specific compilers. And so we went about doing this by translating the higher level code to an intermediate code that is actually human readable, which is basically CUDA or OpenCL or whatever new programming model that there is. We were able to translate that using source-to-source translation schemes. And then we were also able to factor out things into classical libraries that can be actually packaged into classical libraries and linked in traditional linking phase to provide the actual platform-specific parallel executable, which will then be running on the target hardware. So this is really the workflow that we thought would do the best agile way of developing code for upcoming HPC or upcoming architectures. And as you can see, it's really agile in the sense we are really leveraging what's out there, what's coming up. And if people come up with SYCL, then all we need to do is add a translator to our DSL, and then there we are. We can generate SYCL code. And the key thing, of course, is getting the abstraction right for that particular architecture. Right. Okay, so now once we have the loop level declaration, there are loads of synthesis possibilities or optimization possibilities, and we explored this over the years. We can automatically parallelize to different target parallelizations, which is as a given, we are going to do that. And then, of course, we can generate different code paths or parallelizations to handle, to do different things, right? And you will see this, especially in SYCL more recently when we were doing this, where we had to actually generate different code paths, different parallelizations with SYCL itself to get the best performance for different architectures. And then we can do things like different data layouts or data movement, all again automatically, things like SOA, conversion to AOS and SOA, distributed memory partitioning, block partitioning, local block partitioning, data movements where you have to have halo creation and exchange and so on. And of course, things like avoiding communication, which is a major source of time, with codes that are bandwidth limited. If you can eliminate communication or data movement, then you gain a lot in performance. And then load balancing and other things like we can even do automatic checkpointing based on the declaration of the loops. We can reason about the loops and figure out what data sets needs to be actually checkpointed at a given time. We can do things like visualization, although we haven't managed to implement this just yet. But if you look at other DSLs out there, things like PyFR from Imperial has done this in situ visualization, and things like uncertainty quantification can also be packaged into this whole DSL framework. And so you should be beginning to understand that now the complexity that Exascale will inevitably bring can be sort of managed, or there is a path forward to manage it, although it's highly still complex. At least there is a way to factor things out cleanly, and then go on to implement these other more exotic and more challenging aspects of getting your simulation code working on Exascale systems. Right, so so I alluded to this before. Key point is things like handling data races, where you have to do different things for different programming models. So if it's distributed memory parallelization, you would have to do something like an owner compute model, where you partition your mesh and then you have to have the, you can have the standard halo exchange method, but then you have to do redundant computation to keep the data on each side of the halo updated to keep things valid. And then if you go to single node and then you have multiple threads like OpenMP, and then you've got data races where multiple threads are going to write to the same memory location. You can do something like coloring. And if you have more threads, you can do, different levels of coloring. You can do a global coloring such as this, or indeed you can do a hierarchical coloring. And then, more recently, GPUs that used to be programmed with coloring got atomics, where you have hardware locks that are going to really give you high performance. And so now you have to write your code to generate hardware atomics code. So the whole point is to show the different things that you can do with different programming languages. And you cannot be rewriting this again and again for your 100,000 line code. So here's a good example taken from a mini app or a representative app developed at Warwick called MGCFT, where you will have your declaration at a higher level like this, where you have a flux edge calculation given by this elemental computation. And the loop declaration will look like this, where you've got indirect reads and then indirect increments on these data sets. And to implement this in simple sequential fashion, all you need to do is generate code like this, where you have use the mapping tables that are given here. So EN here is mapping, that's the explicit connectivity between edges and I think it's the nodes here, which are declaring flux, or where the flux array is declared. And so if you have your indirect accesses managed like so, then all you need to do is then call the elemental computation kernel in this fashion, and that would be a sequential execution. And then if you go to do something like SIMD vectorization, where you are trying to vectorize over the edges, so try to do 4 edges at a time. If you have a vector length of 4, then you have to generate explicit gather scatters, where part of the parallelization, the SIMD vectorization, can be done in SIMD lanes or using a SIMD loop. And of course, when you're applying your indirect increments, you will have to do something like this, where you essentially have to not do vectorization at that point. But again, you can gain a lot of performance by doing the first bits in SIMD or vectorized, while the last bit of the increment can be done serially. And that, again, this code is again automatically generated because we have the high level description to do this change or do this optimization easily. And if you look at something like CUDA, or now in this case it's SYCL, you can have a colored scheme generated where you have the global mesh colored and held in an array, and then you can loop over the colors such that because the coloring guarantees that no 2 edges of the same color will update the same memory location or the node, then we can do a colored execution and again get a good parallelization to get good performance, or indeed generate atomics. And again, you get different code paths. Right, so I will quickly jump through and show some of the results that we've seen from using these DSLs. What I want to demonstrate is that using these higher level abstractions doesn't really reduce performance from a hand-tuned optimized version, because we've been able to match the hand-tuned performance hand-tuned codes over and over again every time we do this type of domain-specific code generation for a given application. So the earliest one was for this large code called Hydra, Rolls-Royce's CFD code, which was written in Fortran over 20 years ago. It's really a massive beast and really difficult to handle. And as you can see, the O+ is essentially the older code, and then OP2 essentially, with MPI only, we were able to manage performance. Of course, the older code was only having MPI parallelization, and then with OP2, we were able to match the performance as well as improve the performance with other, different partitioners using different partitioning techniques, or indeed using things like CUDA to run things on a cluster of GPUs. And even we can do parallelizations on a hybrid machine where you've got computation going on both the CPUs and the GPUs, again, automatically generated. Then we got structured mesh. One of the earliest was this application called Cloverleaf. And you will see Cloverleaf being referred to again and again in various new hardware when AMD or ARM put out a new processor. You will see Cloverleaf being one of the applications that they benchmark. So it's really good. And so we were able to have a version of Cloverleaf developed with OPS. And again, we were able to show that you can match the hand-tuned performance of Cloverleaf with OPS itself. And the same goes to something like OpenSPLI, which I think tomorrow one of our collaborators is talking about. Again, a much higher level programming framework, OpenSPLI, that uses OPS to generate hardware-specific parallelizations. Yeah, so there's other techniques that we can do, cross-loop techniques, where you can do things like cache blocking tiling, where you avoid communication, and again, all these optimizations, without the change of a higher level specification, you can affect down and get the optimizations without having to rewrite your code completely. So some work by Istvan a couple of years ago on tiling on a structured mesh again, and then even tiling across MPI, where now you're not only cache blocking tiling on a single node, but you're extending it to MPI, where you can cut down on the communication at distributed memory level by only communicating a bigger and a less frequent message in your loop chain. So later today, one of my students will talk about tiling that were done using OP2 recently, using one of our collaborators for library called Slope. And this is for unstructured mesh, where you can say that structured mesh, there's a lot of literature that does or publication that does tiling for structured mesh, but there's relatively little on unstructured mesh. And again, the idea is, how would you apply these exotic optimizations? And the way I see it, the only way to do this is through something like a DSL that we have developed, like OP2, that can then provide provide the code that translate your code to these optimizations. Yeah, and you can do things like checkpointing, and then so over the years, various projects started using this on their production codes, and we have this a number of projects using these OP2 and OPS. One of the first was this code called Walnut for simulating tsunamis, where they use Walnut to actually validate their emulator code so that they can quickly inform of what happens, or flooding information based on an earthquake in the seabed. And then we've got OpenSPLI, one of the bigger codes that uses OPS developed at Southampton. And I think David Lasche is talking tomorrow, and he'll give more details of this. This is actually now an Archer benchmark. This Taylor Green vortex problem simulated here. Again, for explicit solvers, developing explicit solvers with OPS. And then more recently, we've been trying to move on and move the Rolls-Royce production code to production code base to use high-level abstractions, use DSLs, and OP2 being the key one here, where we again show that how we can get almost the same performance as the original, and even basically beat performance with using things like GPUs and different parallelizations. So I'll skip some of this, but what I wanted to come to is so Archie later on will Archie Powell, one of our students, again will talk about SYCL parallelization. So I will leave that to Archie. What I really wanted to talk very briefly is that the challenges still. So there's essentially no silver bullet still, but I think this is one of the most feasible ways, one of the most easiest paths that want to be taken if you want to move your code base and to Exascale. Now, the challenges, the problems with this is one, how would you convert code, a legacy code? And that is still a big hit. And the only silver lining there is that unlike converting to, say, CUDA or some new language, you will have to do this only once. And once you've converted it, the code generation techniques will take care of generating other parallelization. So it would be a hit, one-time hit. And then we keep on coming to this problem of how do you validate the code. So if you talk to industrial partners, they always have this reservation of the generated code. They're really scared of what is generated and how would you validate it? What code are you going to validate? And so to answer that, something like OP2 or OPS, we simply generate code that is human readable. And so you basically have to validate that code, which is basically CUDA or SIMD vectorized or SYCL or something like that. And so that should hopefully answer this problem. But it's still, we've seen that it's still difficult to convince users to use this new high-level way of programming, simply because they don't trust what's going on. And the easiest way to earn that trust is actually show the code that is generated, which I think we can do. And then we've got this, again, conversion process of the difficulties in conversion. And maybe a challenge would be coming up with an easier way of converting. So then we've got toolchain problems of generating code itself. So, we've been doing this with some things like Python so far, and then LLVMs, Clang, libtooling, toolchain. But we really have been struggling with things like Fortran. What sort of tools can be used to do this effectively? And then, at various levels, how would you, generate and modify your code based on this toolchain? And of course, things like FPGAs are even more difficult, which is a space that we are currently exploring. And then we've got the question of who maintains these DSLs and how many, since there's lots of DSLs, which one is to use? So the answer to that, I think currently, is that it would go along the way of traditional or classical libraries, and it would not be much different to what you would do for a classical library. All right. And so, so in future, so as future work, we've got this whole list of things, a wish list of things we want to do. Some of them much more longer term, and some of them already happening. Things like multi-diagonal solvers for OPS. And so there's a lot of, a golden age of parallel programming research going on. And this is just basically, only a little bit of things that we want to do in the future. Right, so some other work that have been going on in the space is, of course, there's a lot of DSLs that have come up, things like Firedrake for finite element, Phoenix, DeVito, which you will hear probably later, and then things like Cocos and Raja that are now becoming prominent. And the problem here with Cocos and Raja is, of course, C++, and the way you would want to handle Fortran. What are you going to do with Fortran? And so, so the DSL space is active and really live, and it's a rich space of research currently going on. Okay, so what I want to do is end here and really, to say that you shouldn't be afraid of high-level abstractions because we've seen time and time again that you can generate better code similar to hand-tuned code if you know what you want to generate. And if you know what parallelization or optimization you want to do, because compilers are conservative, you want to force it to do it. And you want to write your DSL. If you're developing a new DSL, you want to write it in a way that it will force, tell the compiler what you want to do, and exploit the domain knowledge that is out there that can really generate better code for you. And yeah, so I think this is the way, as the Mandalorian would say, this is the way to go for Exascale, and you see that there is a lot of traction in this area of research currently coming along. Right, so if you would like to try some of this work, everything is open source. Well, mostly open source in the sense, except for the proprietary codes like Hydra. But you can download OP2 and OPS in these links. And yeah, do come and talk to us, do email us, and we'll be really happy to have you working. And I think that's all I can say at the moment. Thank you very much for the invitation. Thanks. Thank you.
Thank you, Gihan. We have time maybe for a quick question. Anyone? I'm not sure if Fabio's hand is still up.
Yeah, I'm here. I'm listening.
Yeah.
I mean, I'd have questions again, but I don't even know where to start. So, for example, like this is the third talk today that mentions FPGAs.
Yes.
One of the topics we've stayed away from. I'd be super curious to know what's your actual plan with that, like
for FPGAs.
Yeah.
Right. So FPGAs are difficult. So we had I should send you the paper that we did recently, although it's still under review. So we tried to do this for structured mesh codes for OPS, although we can't code generate yet. So the key thing we wanted to do was understand how to generate the best code for FPGAs, and it's really restricted. You can really only do single precision to start with at the moment, and that just throws out all these, CFD codes or everything that relies on double precision. As soon as you want to do double precision, you run into requiring a lot of resources on the FPGA, which cannot be done. And so we only managed to do a very, very narrow set of applications. And one application in particular, this RTM application, which we got from, I think you guys also did this in your DeVito codes. Again, really narrow, and the motivation was something like financial computing. And you can't do big codes. So you have to just forget about it and just only fight the battles that you can actually have some resemblance of winning. And so we did get, some good performance compared to a V100. And then the winnings come not really in runtime, not the time to solution. It is the energy consumption as well. So you want to look at it in an energy consumption view compared to GPU, and then you can see some gains, and you can imagine someone would be using, but it's still really early days. We haven't come across an easier way to code generate, or we haven't exploded. We are simply trying to get the best optimization down there, down on an FPGA. Does that?
Yeah, that answers my question. If I have time, I'd ask another one. Which is
sorry, guys, we are a bit over time, so I to cut this short.
Okay.
But yeah, I'm sure we could talk about this for a long time. So thank you, Gihan.
Thanks so much.
Next up, we have Walter Scheirer from the University of Notre Dame, who is going to talk to us about open set recognition. Can you try and share your screen? Yeah. Okay.
Can everybody see this? Is this good?
Yep.
Yeah, that's okay.
It's in presenter mode. All right.
Yes. Thanks.
All right. Thank you for that introduction. I'm happy to be here. Actually, wait, let me just adjust one thing on my Zoom. There we go. Zoom has a habit of taking over your screen with its own sub-panels, so I think we're okay now. All right, thank you again for that introduction. I'm excited to be here talking about some machine learning work that's happening in my laboratory. I am Walter Scheirer. I'm at the University of Notre Dame, and I lead a very large research group looking at some advanced topics in artificial intelligence, especially ones that have a direct application to real-world problems, especially the difficult ones. So this talk is going to be on statistical methods for what we call open set recognition. So to begin, we can ask this question: what exactly is open set recognition, especially in a machine learning context? As I mentioned, right, my lab is very interested in real applications. There are a number of stumbling blocks that have appeared in recent history, especially with respect to things like autonomous systems. So this is self-driving cars, autonomous drones, areas where these systems have to interface with aspects of the environment, especially dynamic environments. This becomes incredibly challenging for the state-of-the-art in machine learning because new things can appear, right? The world is changing. New objects, right, if we're thinking about computer vision, can appear in a scene. And what implications does that have then for these systems, which are largely trained in a supervised manner? Meaning, right, we've collected a lot of examples of what we want to train the system with. We've labeled those examples, but that only reflects a subsampling of everything we could possibly see in the real world. And so that becomes our challenge. And so with that in mind, we can talk a little bit more in detail about what exactly the problem framing is that we need to formalize in order to be able to tackle this from a machine learning algorithm perspective. So thinking about where we're at right now in not just computer vision, but machine learning in general, we have a number of benchmarks that are out there, right? These data sets that have been collected. This is the dominant way that we evaluate our algorithms in 2020. It's the dominant way we also develop and train our algorithms in 2020. And this is good for a number of reasons, right? It gives us a common footing in terms of evaluation, right? Everybody is operating with the same pool of data. That means when we publish papers, there's some consistency in the reporting of those results, which is great. It also gives us a lot of data. We need to train our systems. We need some basis from which to work from. when we're developing these learning-based systems. And again, for comparison purposes, it's great when models are trained using the same training data, because that gives us another point of common comparison. But what is perhaps a little bit limiting when we think about how these data sets are organized is the following setup. We assume that we have examples from all of the classes. So this is just an example of the Places 2 data set, which is part of the ImageNet ecosystem of computer vision data sets. At training time, we typically know what we're going to see at testing time. We have these discrete categories that have been labeled. Here, right, we have different types of places like airfield, campsite, gas station, water park, and mountain. And at testing time, we wouldn't expect to see anything other than these categories, right? We know exactly what we're going to see. Now, this is good in that it's a tractable problem for machine learning, but it's bad because it's not necessarily the problem we need to solve if we're trying to move into real environments and interact with environments in which unknown things can appear, things that we'll have to deal with, right, that an agent's going to have to perceive, identify, and then somehow manage, because that's life, right? That's exactly what we're going to see in a real setup. So what does the real world look like? Well, it look like anything, right? Imagine we have a self-driving car. Imagine, right, for safety purposes, this car has to identify other cars on the road. That is important, but the car is going to see other things in the scene. And most of those things are sort of irrelevant for safe driving, right? The car is going to have to reject things like trees, signs, telephone poles, things on the side of the road that may not matter for safely keeping a lane and avoiding obstacles within the road. Now, this may seem easy, but it's not, because new objects can appear in the world, right? Just, think about life maybe, 2 decades ago. I never saw this cell phone object, right, back then, but now I do all of the time, right? This is a new object that appeared in my frame of reference that I have to identify going forward. And right, of course, right, as technology progresses, we're going to see new objects. There are different levels of what we could call a novelty hierarchy. For instance, right, new models of car will appear each year, right, as car manufacturers release new offerings into the marketplace. I would have to know something about that instance level novelty. Perhaps the design of cars evolves and different attributes of the cars change over time, right? A car from the 1920s doesn't look much like a car in the 2020s. So there's going to be novel aspects of the design. And so that's important to understand. Maybe in the far future, we'll have things like flying cars, right? Novel technological innovations that we'll have to resolve with these systems. So we know then we're going to have to learn over time as well, right? That's another aspect of this. So taken together, this becomes a really challenging problem. So coming back then to open set recognition, we can define this then more precisely as incomplete knowledge of the world that is present at training time, where unknown classes can be submitted to an algorithm during its operation. That's the key distinction from normal supervised settings, which are more or less closed set these days in areas like computer vision, natural language processing, other areas of signal processing. Okay, so we still need to dig into this problem a little bit more to understand what exactly we're dealing with when we break the data down into different categories. So I like to refer back to Donald Rumsfeld, who served as Secretary of Defense here in the United States back in the George W. Bush presidency. This, of course, was the era of the 9/11 attacks when there were serious national security concerns here in the US and abroad. And a lot of thinkers in that space were thinking about risk, right? And what you'd have to plan for in the future. And Rumsfeld is remembered today for a speech he made in this context, which began, "There are known knowns." And Rumsfeld went on to describe different scenarios that policymakers have to account for and the difficulty in planning for things that may happen unexpectedly. And at the time he gave this speech, it was panned initially because he kept talking about things like unknown unknowns, right? Things we don't know that we don't know, and how these things are dangerous, right? It seems sort of absurd if you didn't think about it. But upon reflection, a lot of people got it. And this speech is now fondly remembered as being very, very insightful. And incidentally, it maps really, really well to machine learning settings that we're interested in when it comes to open set recognition. So in machine learning, we have things like known knowns, right? We have known classes. These are the classes with distinctly labeled positive training examples, which also serve as negative examples for other known classes. We have known unknown classes. These are labeled negative examples that are not necessarily grouped into meaningful categories, right? So they're distinct from the known classes in that we've just bin together a bunch of different things, but we know that we're not interested in these things. These aren't the classes of interest. And then we have the dangerous category, right? As Rumsfeld warned us about, this applies to machine learning as well, the unknown classes. These are the classes that are unseen in training that we're going to have to figure out are novel at testing time and perhaps do something with. And these, again, can have drastic consequences for not just the training regime, but also, again, an agent in operation in the world if they somehow influence the decision-making and behavior of that agent as it's interacting with the environment. And so when it comes to open set recognition, this is the key piece that we have to address, right, in our algorithm design. How are we going to handle those unknown unknowns? How are we going to mitigate the risk of the unknown? Because that can cause us problems when these systems are deployed. So again, I'm a computer vision person fundamentally, so I'm going to use the running example of computer vision throughout the rest of this talk. And we can break vision problems down into different orders of openness just by reasoning through these different problems. So we can imagine a closed set scenario at one end of the spectrum where we have a traditional problem like multi-class classification. Here I have some set of known classes, and my training and testing samples are going to come from these known classes. I don't expect to see anything else, right? This is basically how we're still operating in machine learning in 2020, which is a little bit disappointing. And again, this is, again, a key stumbling block as to why we don't have better autonomous systems. But there are other areas of computer vision where we do start to see open set recognition play a role. A classic case that comes before the drive towards autonomy is face recognition. Different modes of face recognition exist. A basic mode is face verification. This is just one-to-one matching. I have a claimed identity, and then I have perhaps an enrollment in the system, right, which is that same identity. That means we can do proper authentication if those people are the same. But there's also a possibility for imposters. What if someone is trying to impersonate the person who is enrolled in the authentication system? That becomes an open set problem, right? Because anybody can walk up perhaps to the terminal and try to make a claim that there's somebody else. Moving beyond that problem, we come to detection, which is another classic problem within computer vision. Here we typically have a limited number of classes, or really just one class in many cases, and everything else in the world is a negative. So it's nice in the sense that we don't have to worry about too many things at training time, right? You know, in many cases, it's just one class. Think about things like face detection, pedestrian detection. It's just one class of interest. But a face or pedestrian could appear in many different scenes, right? Where many different things can appear in the background, and those things would have to be rejected. And then finally, we come to the setting that we're really interested in, which is open set recognition, where we have multiple known classes and many unknown classes. And this is basically, again, just agent interfacing with the world in general. So are there any existing formalizations out there in machine learning that can help us with this problem? Maybe, maybe not. So if we're thinking about this problem, we're probably thinking about it in a classification context, right? I need to identify things I'm interested in and then reject things I'm not interested in, right? That's a decision-making process. And that leads us to things like, say, SVMs, right, which have been commonly used for these purposes for many years. And if you dig into the machine learning literature, you can find risk formulations like this one, which again are usually tied to things like SVMs, kernel learning, etc. Here we have a notion of ideal risk, which we're trying to minimize, right? Because we want the least risky solution when we train our system in a learning-based context. And ideal risk is usually composed of integrating over a loss function and a joint distribution. Now here's where we run into trouble when it comes to open set recognition. If we look at the terms here. In our loss function, right, we're assigning penalties for misclassification, given some set of known samples and their corresponding labels, so we can check the answer. This assumes that we know everything in that set, right? There is nothing that is unknown. So that means it's just reducing to the closed set problem, which is not helpful for open set recognition. Same goes for this joint distribution, right? I again have my feature vectors X and my labels Y, but this is assuming I know what that joint distribution should be given the knowledge of the complete space of classes. So if we're going to use some notion of risk, it has to be reformulated because this assumes closed set operation, right? So undefined for open set recognition, not good. And if we're thinking about things like classifiers, we have to think hard about what that risk should be, right? Because we need to recontextualize that. Just thinking in general about linear discriminants, which are very, very common for classification. I can imagine a simple binary classifier, right? Where my positive class of interest, dogs, right? Friendly, happy dogs and puppies. And then I can imagine a negative class on the other side, which is just a bunch of other random animals, things that are not dogs. And then I solve some optimization problem to draw the best decision boundary between these two classes. Now, that may work fine for just the classes that we see here in this diagram, but what about the unknowns in open set recognition? A giant problem with these linear discriminants when it comes to problems where I have a defined feature space and I have a half space on either side of this decision boundary, which extends into infinity. What happens if I start adding new classes? And what happens if in feature space, they are very far away from the support of the known feature vectors that I had at training time? For instance, what if I have this class raccoon, right? I have this new data point which appears, which is now falling on the positive plane. It's not close to the positive samples of dogs in feature space, but it just happens to land in feature space on that side of the decision boundary. This becomes a huge problem because all of that open space extending into infinity is very, very risky the farther away I get from the known training data. And you can demonstrate this with really simple data sets, which is interesting. So something we did a number of years ago, which I still think is kind of mind-blowing, is take a basic data set like MNIST, right? So it's just handwritten digits, right? Classic machine learning benchmark. Considered obviously to be a solved data set, in the present day, and has been solved for many years. If you do the normal closed set evaluation on MNIST with even a basic classifier like a 1 versus rest SVM, the accuracy is basically perfect, right? There's only a handful of digits which are very, very ambiguous that any learning system will get wrong. So not very interesting in the grand scheme of things, just used usually as a sanity check to make sure that a learning algorithm is working. But what if you repartition this data set and change it up such that you leave some digits out at training time? So imagine we train that same 1 versus rest SVM with just the digits 0 through 5, right? We have 6 training classes. And then bring them back at testing time. And we can do this incrementally too. So if we look at the plot on the right here, we see the open set testing regime for MNIST. If you look at the blue curve, which is again 1 versus rest SVM, with a threshold attempting to account for these unknowns with a simple rejection mechanism. Closed set, right, performance is where it's at originally. As we start adding these classes into the testing, again, just having this model that only knows the 6 classes that were present at training time, we can see that the performance degrades drastically. And again, that's not terribly surprising because these are unknown things. But it's sort of surprising if you think about it, because MNIST is such a simple data set, right? I can't imagine that we weren't able to generalize and you know, even using a rejection mechanism, be able to sort these things out between novel and known classes. And so the simple mechanisms just do not work. And so that means we need to look at some alternative algorithms, right, and change up the formulations. So if you look at the red curve, this is an open set specific algorithm called a PySVM, which is able to handle unknowns in a more intelligent way. And while its performance degrades, it degrades more gracefully. So we want to understand how we can change these formulations to do things like this, to be able to handle these unknowns. And again, starting in a simple place like these open set MNIST benchmarks. Now you may be thinking, hold on a second, it's 2020. Hasn't deep learning solved this? Isn't it just a matter of doing really good feature learning over large data sets? Well, no. So let's figure out why deep learning doesn't really help us out of the box with this. So what does deep learning help us with, number one? Well, we know we need a feature space, right? Because if we just use raw pixels and vision problems, everything just gets jumbled together, right? There is too much noise dominating the signal. And if we're trying to do something very simple, like separate two identities in a face recognition task, the pixel space is not going to let us draw an effective separating hyperplane, right? If we're thinking about classifiers, like this is just not going to work, right? So this is a tangled space. This is why we use features, right? So for many years, computer vision was looking at features which are more or less equivalent to visual area V1 in the visual cortex, where we can basically identify oriented edges and separate that space, filter out a lot of that noise. And this helps us somewhat, but it's not great, right? And so enter deep learning, which gets us, you know, to better representations of whatever objects of interest we're dealing with, right, in a vision problem, and separating that space such that, right, there is ideally perfect separation, right, a void between the two. And then it's very easy to draw a separating hyperplane. We get this untangled space. So thinking about linear separation of CNN feature representations, right, this is exactly what we'd want, right? If we can pull these feature spaces apart, we're able to solve this simple face recognition problem. But the trouble is the same trouble we had before with linear classifiers, right, and half spaces. An unknown individual, right, in this feature space can appear on either side, right, of the binary problem because it's only labeled as individual 1 or individual 2, right? Unknown individuals will happily be placed somewhere in that feature space and then labeled accordingly based on what was known, right? So this really is a classifier problem and again, then a subsequent labeling problem, not a feature space problem inherently. So that means if we're thinking in a deep learning context, we can just consider the readout layer, right? Which is, you know, the right thing to do. But of course, I think we would probably start with the basic readouts and try to figure out, can we use them out of the box to solve this problem? Is there anything out there that we can just use to solve this? So the first thing you would probably do is just try to do this with softmax, right? Is there something we can do with softmax? Well, just using softmax doesn't solve this problem because there's a summation over all of the classes, which implies we would have to know what all of the classes are to do accurate classification. Yes, we could add a threshold over this. That is the hack to make this work in open set recognition. But then that's kind of ad hoc, right? The best we could do using softmax is to estimate a threshold over the scores using a validation set during training. And it turns out in practice, that's not a very good strategy. Linear SVM, we already saw why that's a problem, right? We only have known positive or known negative data in this learning formulation. And of course, right, the half spaces are then dangerous because they will happily label whatever we want based on the knowns. Maybe cosine similarity helps us here because, right, we have to apply a threshold because it's just a similarity measure. But that's the same thing I just talked about with softmax in that we need to do some estimation of this given known data, which may be tricky, right? Just relying on our validation set. So all of these things are really insufficient. Though with thresholding, you could do it. In fact, that's what most people do when they come to open set problems. Let's think about solving this half space problem as our first solution here. And to do that, let's start again with a formalization that makes more sense for our problem. So instead of ideal risk, let's think about open space risk, because we know that's the problem with these classifiers. And we can define open space risk as the relative measure of open space to the full space. We have this expression here of what this risk should be, where on the top here of this fraction, we have open space, and on the bottom, we have open space plus positive training examples. All right, so the smaller the open space is, and the larger the positive training example space is, the less risk we're going to have inherently. And this is, again, what we want to minimize, right? I want to minimize the amount of open space because I know the more of it I have, the riskier it is it's going to be when I move this over to a feature space and try to solve my problem. So the open set recognition problem can be distilled into these components. A space of positive class data, which we'll call P, a space of other known class data, the known negatives, which we'll call K, the positive training data, which we'll call V hat, which is a set of samples that are going to be drawn from P, the negative training data, which we'll call K hat, which are going to be drawn from K. That's the training setup, right? Then when we move into testing, we can have unknown negatives appearing in testing coming from a set U. And then that means the testing data is going to come from the knowns and the unknowns. And then for open set recognition evaluation, we're going to assume that the problem openness is greater than 0, right? 0 would imply that the problem is closed set, which may be a good starting point, and we can incrementally open it. But we don't want to simply fixate on that for the problems I've already described. So that means we can formalize the open set recognition problem as follows. Minimize open set risk. So this is going to include the open space risk associated with the unknowns at testing time, a regularization constant, and then an empirical risk function, which is going to account for the output of a trained classifier as we're proceeding through training, which is going to have knowledge of known knowns and known negatives, right? So known positives and known negatives, the union of those two. And then we can proceed, right, with minimizing both of these pieces. Okay, so working towards an algorithm that accounts for this new expression of risk, what do? So if we're thinking about linear classifiers, we can move towards something that looks like this slab model, where we have two separating decision boundaries. The original one, which we had, right, which is labeled alpha here, separating the known positives from the known negatives. And then a second one labeled omega here on the back side of the positives, which is limiting the open space risk, right? So that solves our problem when it comes to a raccoon appearing far away in the feature space, but still ending up on the wrong side, quote unquote, of the original decision boundary. And so how does this algorithm work, right? How do we optimize both of those planes? So this algorithm we introduced a few years ago, it's called the one versus set machine. It does use two separating planes, a near plane, which we labeled alpha, which is going to separate the known positives and the known negatives, and then a back plane labeled omega, which is going to reduce our open set risk, knowing that unknowns can appear behind the known training data as well. And this becomes tricky because we need to generalize, right? Knowing that we don't want to overfit our training data, knowing that new positive examples that don't quite look exactly the same as our known training data are going to appear in operation. We need to make sure that we account, right, give some flexibility and account for that possibility. We also need to not overgeneralize, though, because we know the more generalization we have, the more risk, right, of open space we're going to open up as we push towards, say, some other class that may appear in operation, right? So that becomes an issue. Notice, right, there's a void in the backplane area, right, between the known positives and then some other class, which we've labeled 3 here. If I get too close, right, to 3, I'm probably in 3's feature space, which is dangerous. Conversely, right, specialization is also an issue, especially if I didn't get good separation in my feature space. We often make an assumption that deep learning works perfectly, right? I always get perfect separation in feature space. That's not true if you start visualizing where some of these things fall, especially at classification time. So we can imagine needing to specialize, right? Knowing that I'm not going to get perfect recall of whatever the known positive class is, but I'm still minimizing my misclassifications, right? Trying to get better precision, which may be acceptable and perhaps desirable for certain applications. That's another consideration. Okay, so with an algorithm like that, how well does it work? We tried this out in an open set recognition context. We designed a new classification benchmark, which accounted for open set recognition. So this involved a cross dataset methodology, which is very, very useful for open set recognition problems. We looked at a feature set, which was just basic hog features, because this was sort of right before deep learning took off. So our training set involved the use of Caltech 256 for the known classes, very standard, very basic computer vision benchmark, and then Caltech 256 plus ImageNet, a more recent data set, and a very standard one for deep learning applications these days to bring in some unknowns as well. And then we formulated an open universe of 88 classes, which typically was 1 positive class for each classifier we trained, and then n training classes in total, which we could vary to adjust the openness of the problem, and then 87 negative testing classes. And so this is a very, very large test of over 500,000 images. Here we can see the top 25 classes for the open universe of 88 classes, and we're doing a comparison here between which has been proposed in the literature as being a suitable solution for open set recognition because it just considers 1 class. We don't have to consider known negatives at all. We can sort of eschew that and move just towards what we want, which is a known positive. Unfortunately, that tends to just overfit the positive class in practice. You get better generalization when it comes to having some accounting for negatives in a binary context. And what you can see here, so if you compare the red curve to the blue curve, in basically every single class example, this one versus set machine, which is trying to minimize the risk of all that open space in a linear context, is doing much better, even in this simple feature space. And we still saw some gains too, using the same strategy for a 1 class classifier. It's just not as good. So we definitely recommend if you have some negative examples, use no negatives. It's going to help you. Moving beyond just object recognition, we also looked at face verification, looking at labeled faces in the wild, which is a very, very standard face data set, and one considered to be very, very easy these days. So again, trying to recontextualize it, so it's a little bit more difficult in terms of the organization of genuine pairs versus imposter pairs. So here we had gallery classes, 12 people with at least 50 images, and then a lot of imposter classes, right? So these would be the sort of unknowns in operation, 82 other people in labeled faces in the wild. This left us with 1,316 test images across all classes. And again, this is sort of in a pre-deep learning era, so LBP-like features and Gabor features, Gabor wavelets were used. We saw the same basic effect that we saw in the object recognition experiments, in that the 1 versus set machine formulation, again, was superior, especially in terms of its graceful degradation as we continue to increase the openness of the problem, which for face recognition in this context meant we were adding more unknowns at testing time. Okay, so take 2. The formulation that we have here with the 1 versus set machine is pretty simple, right? We added this backplane which reduced our open space risk, but it wasn't perfect, right? And in fact, the risk is really just a relative, a sort of relative reduction of what's happening in terms of that open space, because it's linear, right? We still have infinite extent between the slabs, right, in the formulation, which isn't great. So could we get better bounds on the open space? Is there a better way to do that? So what was missing from our definition of open space risk? Well, okay, so here's what we have again. We've got our open space on the top, and we've got our open space plus positive training examples on the bottom. But what I didn't tell you, right, initially here was that the definition doesn't tell us how to define, right, what is the open space? Is there some way to define that? Okay, so let's think about this more rigorously. And let's think about it in probabilistic terms. We want to perhaps define what could be considered to be an abating process. We want the model-enforced decay of probability away from supporting evidence, right? This is going to help us then get a better handle on where the positive data are and where we start to enter open space. So we can imagine having some collection of positive training data points. And what we want, right, is some function that monotonically decreases probabilistically, which we can then set a threshold on, a hard threshold. And perhaps, right, if we have good probabilistic modeling here, we can do a lot better than what we had with that one versus set machine formulation. So what we can do is fit a model to the tail of the positive side of the decision boundary if we're thinking about modeling this abating process for just the positive data. Okay, so first question, why the tail? Why are we interested in that? And not perhaps, the average of all of these data points? Well, if we're thinking about classifiers, we're thinking about decision boundaries. And it turns out that the tail of these distributions is very, very consequential for drawing where that boundary should fall. And that's because the mean, right, the central tendency of this distribution can be very, very misleading in a probabilistic sense. If we model the average thing, that means a lot of the data points out in the tail are going to have a very, very low probability, even though they are perfectly consistent with whatever this class is. So that becomes a very, very important consideration. So that means we need a probabilistic model that's going to assign us higher probability out there in the tail region compared to the probability we get with a central tendency model like a Gaussian, right, which is going to put, right, the emphasis in the center of the distribution. Again, for some problems that may be fine, but again, for a lot of classification problems in machine learning, it's not good at all. We're going to lose a lot of the positive samples, which we need to get good recall for whatever our problem is. So we found that a Weibull fit, so the Weibull comes from the extreme value theory family of distributions, is going to help us out with this. And this Weibull can be defined by 3 different parameters, shape, scale, and location. And so we can fit this distribution just like we can fit a Gaussian, right? Instead of looking at all of the data, we're going to define a tail size, right? And treat that tail size as a hyperparameter in our formulation, and then create a distributional fitting based on this. And so this is then going to give us a good indication of how this decay should proceed for the abating model. So taking this further, defining a compact abating model, what we want here is perhaps a probability from a kernel machine that varies locally with distance to training points. We can take these scores, right, probabilistically calibrate them, and then put a threshold over those probability scores, defining a compact region, which is where the positive data will be assumed to exist. And then anything outside of this probabilistically defined region we'll simply reject as being unknown data. And so we call this a compact abating probability thresholded region or a cap region. So we can see here, coming back to our example of MNIST with handwritten digits, if our positive class is 3, right? So given some handwritten sample, If the probability is over our threshold, we can say this belongs to this class. If it is below threshold, it's some other unknown, and we can safely reject it. Now, getting good probabilistic modeling is tricky for these problems. And so if we have additional evidence, that can help us as well. So it turns out if we're thinking about binary decisions, right, because we're dealing with something like a binary SVM, we have access to the negative side of the decision boundary as well, which is also interesting for probabilistic modeling. So what if we do a reverse Weibull fit on the non-match data? So this gives us a probability of not being in the non-match class, right? So that's additional evidence that we can use to figure out whether or not we're on the positive side of the decision boundary. And so we have found that this dual tail fitting model is even better than just the positive model. Okay, so how does this stack up compared to other models that are out there that could be used conceivably for these open set recognition problems? So the dual tail model, which I just described, is labeled here WSVM for Weibull SVM. That is the best model out of this entire set. For that same benchmark I talked about for object recognition, for the one versus set machine earlier. So we can see here, right, in terms of this plot, we're looking at F measure as our measure of performance, and we're looking at increasing, right, incrementally the openness of the problem. We can see that the one versus set machine is the second best approach, but it's not nearly as good as the WSVM with this better probabilistic calibration. And better bounds around, right, the data that we know about reducing open space risk. Looking at other things we could potentially use, again, the standard toolkit of thresholded SVMs. In all cases, all those are not great. You can look at probabilistically calibrated SVMs as well. In fact, that's the worst approach here. That's that blue line at the bottom, marked with squares for the data points. We can even look at other extreme value theory-based calibration approaches, just not using the same formulation we are for the WSVM, just applying simple thresholding. And that's what this multi-attribute spaces or MAS curve is showing. And that one is also not very good, right? So putting the elements together in the right way gets us something that's a bit more resilient in the face of unknowns compared to a bunch of other different approaches. All right, one more thing I'll mention before we get to the Q&A here. Take 3, incremental learning. What would be really useful for an agent in the world would be perhaps an ability to not only identify that something is novel, something is an unknown sample, instead of just discarding it, moving along, right, just giving it a label. What if we could incorporate that information back into the model? Right, so we can use that then to identify whatever this thing is in the future. That seems to me to be a very critical missing piece of a lot of applications right now, especially in the world of autonomy, where sometimes we do need to identify something on the street, label it as something new, but knowing that it has a major influence on the world, on the environment, and how this agent is now interacting with the environment. So you have to know about it at future time points. That's going to require then a model that can handle incremental learning. Everything I've talked about thus far is train it and then use it, right? We don't go back and try to adjust things. Why is that? Well, if we're thinking about basically any classifier in machine learning that's popular, it's expensive to go back and retrain. Not quite as expensive as training, you know, some feature learning based model for feature extraction, right? Some deep net. But still expensive, right? Especially depending on the dimensionality of the feature vectors, depending on how many data points you have, and also depending on what the algorithm is, right? A lot of algorithms are not really that efficient computationally, which becomes a huge constraint. So this becomes a really interesting research question, right? Is there some way to efficiently train on the fly, do incremental learning, knowing that you want to do this because you have all of these unknowns circulating, which are interesting to learn in the future? So a model that we've proposed recently to do this is called the extreme value machine. This is another extreme value theory-based model, and one that basically is a drop-in replacement for algorithms like support vector machines. The approaches I talked about up to this point really relied on a post hoc calibration of scores coming from existing classifiers to get the job done in terms of open set recognition. This is a model that's built or an algorithm that's built ground up. So you can train models using a formulation which is, instead of looking at something like a support vector to define the decision boundary, it looks at something called an extreme vector, which is using a distance model based on extreme value theory-based probabilistic modeling of points versus other points. And we found that this is nice as just a classifier, but it also gives us an efficient path forward to add new classes into the classifier, so we can, again, take our unknowns, put them back in, and then we're able to learn classes. And what's neat about this model, it will also, on the fly, adjust the decision boundaries for all of the known classes we had before, right? So as we get evidence for new classes, we can adjust all of the decision boundaries accordingly in order to continue to reduce our open space risk, but also accurately classify what is now known. And it turns out that this model works really well. Moving forward, again, this is one of our more recent models in a deep feature space. This works really well against other incremental learning-based models, yielding good performance, reducing the risk of the unknown, and letting us add classes on the fly. Okay, so I will stop here and then answer questions folks may have about any of this. Happy to answer questions. I think we've got about 10 minutes or so should leave plenty of time.
Yeah, approximately 10 minutes is remaining. Thank you for this presentation, Walter. I'm Kalman, if you didn't recognize my voice.
Yeah, no, I recognize your voice. You're a known, not an unknown.
I can't send my webcam. I have no idea why it is this situation. So I always wanted to ask you whether have you ever considered other kind of distribution than the variable, like Rayleigh or so?
Oh yes, that's a great question. The answer is yes. We have considered a number of different distributions. We've always liked the Weibull because in terms of its formal definition, it matches the way the data are bounded for classification problems, right? Either above or below. And that's exactly why we chose the Weibull and the reverse Weibull for the dual fitting for a binary classifier, because it just formally makes sense for that problem. That said, I mean, a number of these other EVT distributions approximately apply. If you look at the recent literature in open set recognition, you'll find folks have achieved success using Pareto modeling. Specifically, Vishal Patel's group at Johns Hopkins has achieved a lot of success with those models. A colleague of mine, Victor Fregoso at Microsoft Research, has looked at other extreme value distributions, including Raleigh, and it has worked out for some problems. So yeah, I mean, I think the space of distributions has been explored. That said, again, I think you want to be careful and make sure that you don't violate all of the assumptions when you go into your problem. Really look at the boundedness and then choose the right distribution. But again, check the literature. There's a bunch of stuff out there on other distributions.
Okay, thank you. Is there any question other than mine?
I do have one. So you already kind of alluded to this, but so in reality, we usually have very different machines we use for training these models and then for, well, inference. So using them, particularly if we look at things like cars and stuff like that. Mm-hmm. So how realistic, or can you sort of expand on this idea of these machines which are primarily there for inference doing some of this learning that you mentioned?
Yeah, so I think so. This is an interesting question. It's like, in operation, you want to continue learning. So there are a few aspects of this, right? Like, number one, like especially in autonomous systems, like the hardware itself is a consideration, right? Because it can be expensive to learn on the fly. All right, this is usually, it's like in the laboratory, you train a model and then you put it on the system and then it's locked down, right? It doesn't change until you get a software update. But that is not great because if you see new things, you can't really do anything with those new things, right? The best you could probably hope for is to reject them. So that brings us then to an algorithm like the EVM, which can do incremental learning. So then the question is it efficient enough, right, to do incremental learning on limited hardware? In our experience, that answer can be yes, depending on the setting, though. I mean, we get good incremental learning performance on CPUs, in more limited circumstances. If we have a lot of classes we're dealing with, we have an implementation of the EVM that works on GPUs, right? We can scale it up. But that doesn't really jive well, right, with a system with power consumption issues, right? It's like got to be low power, a system that has more limited hardware. So I think probably something that needs more attention is the algorithmic efficiency question. I mean, the EVM was designed with that in mind, but it's still, I'd say, like kind of a heavy algorithm compared to lighter weight classifiers you could conceive of. But those, again, aren't sufficient for the problem, right? So you end up in this dilemma. So I think, again, like where our work is heading to now, like especially working on a lot of autonomous systems, looking at lighter weight solutions across the board, and trying to get, again, agents that are agile enough to work in limited environments, but still able to learn in an incremental fashion. Because, again, I think that's really necessary, right? I think realistically, all of these autonomous systems need to do that in some capacity. Did that answer your question? I think that's sort of what you were asking.
Yes, I think so. We have two more questions here. They are good.
Yeah.
Hi, thanks. So my question is, when you showed us this WSVM model, this double tail Weibull distribution model, it was basically the best in this in its class, but it had like an F-score of 25% or something like that, which is doesn't look exactly great. My question is this this is a really hard problem, I assume, but is there maybe, like the F-score tends to emphasize raw accuracy, which might not always be relevant. Do you also usually test with or compute other measures or other losses like MCC or something like that, which might be more relevant and maybe better?
Yeah, so this is a great question. Very insightful question. You were paying attention. So yes, so let me go back to that plot. The concern here is that the F measures are very low. So the answer is yes, they are low. And that's because the problem is really, really hard. So I will definitely emphasize that this is not a solved problem. We didn't create these algorithms and declare victory and move on. We're still very much working on this problem. In fact, like the entire field, right, is thinking hard about this these days because these problems do pop up. So we need to do a lot better in terms of accuracy, accuracy not used as the summary statistic, but just in general, right? We need the performance to go up somehow. So yes, we have considered other performance metrics. So thinking about accuracy as a summary statistic, it often overinflates performance. We've seen cases, right, where you can have something like a no classifier that has huge accuracy on an open set recognition problem, right? Because so many unknowns or negatives, right? It sort of just cheats. So that's not a great metric, but reviewers often ask us to report it, and we dutifully do. We've looked at breaking out precision and recall, right? And you can do that. There's lots of other metrics. A lot of folks have used area under the curve. I don't think there is consensus on what a good metric is. So I think my position on this is we're still thinking about what a good open set metric should be. And no one has a good solution thus far. I mean, we like F measure, right? Because it's this nice like harmonic, right? Combination of precision and recall. And those things are certainly important, right? When we think about open set recognition, because it's not just about, getting back everything we're looking for. It's also about the quality of those retrievals, right? If mostly we're retrieving things, right, that are irrelevant because they're unknowns that got confused, that's not good. And F measure does bake that in, right? And it gives us one score as opposed to two. It's not precision and recall, right? It's one particular score. But again, this is kind of an open question, right? Like what is the evaluation measure, right? We just don't have that yet as a standard.
Okay, thank you.
One for the extreme value, I think was its name. Can you show me the slide, please?
So wait, which
The extreme value.
But which slide are you looking for?
Extreme value.
This one?
No, text 3 or text 2. Text 3, text 3. Extreme
Oh,
value.
the EVM, the extreme value machine. Yeah.
Yeah. I was asking, how do you consider it's a new class? For example, there is a certain boundary, certain, I don't know, number of elements, something like this. How do you identify as a new class in this case?
Good question. So the algorithm, I will point out, is complicated. So the paper will explain exactly how this works. But in a rough sense, what we're doing is looking at distances, right? How far away is this data point from all of the known data points, right? Which I already have class boundaries for, right? If I'm too far away, right, across some threshold, then I consider it a new point. Does that make sense, right? And of course, right, like the distance space is all probabilistically calibrated using extreme value theory. And that's the way in general all these algorithms work, right? It's all about distance. Do I have the right distance measure, and can I figure out that I'm far enough away from what I know that it's something new?
Okay, thank you. We have another question here.
Hello. As you said, in the pixel space, the classes are tangled and very hard to distinguish, so we have to transfer them to a feature space. But those feature extractors usually should also be trained. So in the case of extreme value machine, how do you get the feature vectors?
Okay, so this is a great question, and I'll give you a two-part answer. So the simple answer for the extreme value machine is it doesn't do any feature extraction. It just expects feature vectors, right? It's like analogous to something like an SVM in terms of classification operation. So that means you could go to your favorite deep model, right, and just read out features, right, from the penultimate layer. You could use some handcrafted features. You can do whatever you want. As long as you give it a feature representation, it can deal with it. So it's feature agnostic. Now, that may not be the smartest thing, right? Because as you pointed out, right, like the feature space may be messy. Is there some way to deal with that, especially when it comes to open set recognition? The answer is yes. So there is work from Terry Bolt at the University of Colorado on open set deep nets, right? Doing feature learning, building in an open set recognition risk mitigation formulation. So we had a paper at NeurIPS, I want to say 2 or 3 years ago. And it has a funny name too. It's like reducing network like agnostophobia, I think. And it basically tries to do feature learning accounting for unknowns. And so you can imagine coupling that with something like the EVM and getting much better performance. And in fact, we do that in practice.
Okay, thank you. That was very interesting. Any other questions before we go on break? Okay, then. Thank you very much, Walter.
Great. Thanks, everybody.
We're going to take a short 10-minute break and we'll resume at 10 past. Sorry, everyone, I misread my own schedule. We are resuming at 4:30, so not at 10 past. Okay, hello everyone. Let us resume. Next up, we are going to have Archie Powell from the University of Warwick tell us about the aforementioned SYCL programming model. Archie, you should be able to share your screen now.
Sure. Can you see my video?
Yes, the video.
All right, let's just share the screen. Okay. So I'm going to talk about a kind of performance analysis we did with SYCL on the CFD code, Unstructured-mesh CFD code, using the OP2 DSL that Gihan was talking about earlier. So it's the same code that's kind of based on this Hydra large-scale production code. So before that, I want to kind of get into where we are in the kind of computing landscape, because if you go back 15 years ago, the kind of landscape is much more simple, right? You have the emergence of kind of early multi-core CPUs, Opteron and early Xeons, and you have power as well. That's kind of where you are in your codes, and some SIMD stuff as well. So really, in terms of applying parallel programming to your codes, you didn't really have to worry too much about performance portability, because you could just use something like MPI and it run generally across all of your systems. These days, it's a lot more fragmented. We have a much higher focus on heterogeneous computing. We have a much more hardware available. So on the CPU side, not only do we have x86 and Powell, we have ARM and emerging RISC-V ISAs. On the GPU side, that is technology really that wasn't being used back 15 years ago. And we now have GPUs from NVIDIA, the most popular, but also from AMD, Radeon, and the upcoming Intel Xe graphics for the data center. And we also have FPGAs. And so we have very much increasing performance, because these things have the specialized hardware have very, very high speed memory. They're very impressive compute performance in both float and int. But we start to get into an issue where it's becoming more and more difficult to have a sort of a one code solution that can run even at all, let alone run well on all these devices. And so it becomes more and more difficult to program a single code, because you have to write lots and lots of different code paths for all of these pieces of hardware. And it may not be that you actually get much performance uplift once you've done a complete rewrite. So there's a kind of double, what do you go for? Do you go for a proprietary solution, or do you go for an open solution to try and to program on these devices? If you have a proprietary solution, then you have very good documentation and it will be up to speed and compatible with the latest hardware from the vendor. But that is it, you are locked with that vendor. And so if some other competitor comes along with a cheaper product, a more powerful product, or a new core design or a new instruction set or something like that, which will better fit your application in the HPC space, then you're screwed, really. You're going to have to do a complete rewrite. On the other hand, you can try and avoid that with an open solution, so MPI and OpenMP4, but you have slow hardware adoption and the documentation is quite poor in comparison to the proprietary solutions. So maybe the best way forward to this, to try and ensure we have more performance portability for all these different hardware devices, to have a kind of hybrid approach. So that's kind of where SYCL comes into play. So it's based on OpenCL, the parallel programming solution, but it's designed to be a lot more easy to program and kind of further away from hardware in terms of what the programmer has to do, but still maintain that low level capability. So the point with SYCL is that it's an open standard, yes, but it's a central part of Intel's One API programming model. So of course, Intel's really trying to push into the heterogeneous space with Xeon. Of course, they've had that for a while, but also with XC GPU hardware and FPGA, which used to be Altera. So is this maybe a solution to kind of this problem, having this open standard which can have the kind of better documentation support and hardware support from a major vendor? So this research is basically looking to see it, with a SYCL implementation of an unstructured in a unstructured mesh CFD code, what kind of performance is there across devices, and does it really solve the problem that current open standards have, like OpenMP? So in terms of the hardware and software you're using to test this code, we've got a variety of setups. So there's a dual socket Xeon Silver. It's two 12-core CPUs, and the software side we're using the Intel 2018 compiler update 2. The SYCL, we're using the Intel SYCL LLVM, which is Lang 10, and then a variety of other programming models. We've got an ARM setup, a Marble Thunder X2, which is running well, a Cray compiler, but now it's an ARM client, but now they're kind of just based on the same kind of thing. So, and also Hipsical is the SYCL solution we're using on ARM and also on GPUs, because there is no hardware-specific SYCL implementation like there is on Intel. So it's important to note that Intel's SYCL solution is very much based, it's much more bare metal than Hipsical. Hipsical is really a translation layer which takes the SYCL code and kind of runs it in an OpenCL kind of framework, whereas the Intel solution uses it's kind of SYCL and OpenCL drivers to have a kind of a lot more bare metal approach. And we're also testing 3 GPUs. There's the V100, the P100, and the Radeon 7 from AMD. So the application that we use to test SYCL is MGCFD, and I know Gihan, there'll be some similarities with what is in here and what Gihan was talking about earlier. So I kind of, that had a more sort of technical focus, whereas this is really focused on the SYCL side. But just as an overview, it's an Eulerian in a flow multi-grid solver unstructured mesh written in C++. It uses OP2 DSL, which again Gihan talked about earlier. And it's basically a proxy app which is replicating flux routines of the Hydra code. And yeah, it's based on the Corrigan et al. CFD application, which is in the Rodinia benchmark suite. So the actual mesh we're using to test this is a kind of very standard NASA Road 37 ATEM edges, and we're running for 25 multi-grid cycles. That's the kind of setup and context we're running in for this for our SYCL test. Now, the challenge with an unstructured mesh, as Gihan again was talking about earlier, is that you don't really have a kind of uniform access patterns. If you have a structured mesh, it's very nice because you can just run a stencil through it and you know exactly where where you're writing to and where you're reading from in the kind of process, and therefore handling data traces is very easy. That is not the case with an unstructured mesh because the edges are explicitly defined, so the access patterns are all over the place. So depending on the implementation, there's a few ways to avoid this. So if you have SIMD, you can basically pack a vector with all of your edges across the cells, and then iterate over them, and then essentially make a note of any indirect links, and then iterate over those using gather scatter operations. So that's quite efficient. If you have certain hardware, so NVIDIA GPUs, have hardware atomics, so it has hardware locks on the actual core, and therefore you don't really need to worry about data races or sort of having kind of pre-processing element. It kind of handles it for you. If your hardware does not have atomics, then you have to do some pre-processing. So the kind of technique that we're using here in SYCL and with OpenMP is to use coloring. So essentially you color all the edges, and then when you're doing the updates, you make sure no two edges are the same color are updating at the same time. But this has a kind of setup cost. Now, in the context of fairness, in the results for these tests, we have not included the setup cost there. The reason is that we are using only 25 multi-grid cycles, which is not a lot. And the setup cost is fixed. So if you have 100, 200, 500 cycles, if you were to maybe do it on a bigger mesh, then you have the fixed setup cost and then the runtime. So we haven't included it, but it is important to note that it is there. Now with MPI, you can use an explicit partitioner like Parmetis or PT Scotch, other kind of two we have played around with. And because essentially it's splitting the work up, therefore the only kind of communication between MPI ranks is at the boundary. And because you're only overlapping with like one other rank and the overlap's not that big compared to the whole mesh, there's not very much of an overhead. So these are kind of the results that we had. Now, I put a big disclaimer on because we have done more testing since these results were compiled that show kind of different results. And I'm going to talk about that. Let's see how we're doing for time. Okay, that's fine. So on the left in the blue, we have our Skylake system, the 2-socket, 12 cores, the 24 threads and hyper-threading. We've got the ARM system, Thunder X2. And we have the GPUs. So what do we see in this application? Looking at the programming models. Firstly, MPI is generally faster than OpenMP or the hybrid, and GPUs are much faster than CPUs. That's, I think most people will expect that these days. Now, SYCL is providing acceptable performance across the board. Okay, there's a particularly good result for the Intel system, but as I kind of talk about in a second, we're not really that happy with verifying that result because the Intel drivers are very, very difficult to set up correctly. And testing with a different Intel system, a Cascade Lake system, shows that the performance was not very good in comparison to this. And we know that setup is working because it's in a Docker container and it's working correctly. Having said that, even with looking at performance and kind of being hesitant at that SYCL result, the performance is okay. You notice there's no pure OpenMP results on this graph. The reason is that they're not very good. And really, that is the platform that can run well, as in it's not that difficult to get running across all these different platforms, right? That is the programming model that really SYCL is kind of comparing itself to. And it is faster, generally, than an equivalent OpenMP setup. And on the GPU side is where we see the results being very solid. Again, just the Radeon 7 results, we did some retests and some testing the runtime in a slightly different way, and it's not as fast as that, unfortunately, but it is still very good performance for the GPUs and kind of acceptable performance for the CPUs. This is good. However, there is the problem that the SYCL drivers for the Intel side are very, very difficult to get working correctly. We managed to get this result a while ago, and then we could not retest to make sure it was valid and working correctly. And we've really spent months with multiple members of the Warwick team trying to get this working on this system, and it's very, very difficult to do from a kind of bare metal operating system level. So that isn't great. So in terms of the takeaways from our results, we do have good performance, particularly on GPUs, and we have, I would say, acceptable performance considering the performance portability that SYCL brings on the CPUs. But there's definitely improvements still to make on the CPU side. I would say it's good that the GPU performance is as we see, because we have a lot of GPU products arriving from different vendors. You have the big Intel Xe kind of platforms coming out over the next few years. You know, later in the year, MI100, the AMD Radeon, the big accelerator from them. So it's good to really focus. It's good to have, you know, strong GPU performance, because I think this is maybe a direction that more and more codes are going to follow. But yes, Intel's implementation, which is a lower level than Hipsical, which is kind of a sort of conversion layer, is very difficult to install. And that is a problem because, you know, it is not anywhere near as mature as other standards. So while the performance may be good, the stability is not there yet. There just is not the software support, and you have to have faith in this kind of thing. If you're going to, if you're a developer and you're going to implement this new parallel programming model in your code, and right at the moment there is not there. It's not there. And also, this is an important point that we still have to write different parallelization paths, whether it's atomics or coloring, for the different for SYCL, right? And so if this is supposed to be a unifying API, but you're still having to write hardware specific parallelization paths, how much of a unifying API really is it? The idea that you write the code, you abstract away everything, it's not realistic to kind of get good performance from all hardware implementations. And so you then ask the question, why just not use OpenMP and focus on optimizing that rather than focusing on SYCL? Because they can all run, they can both run on the same devices. And it's also an important point to mention that, you know, currently SYCL is working really because it's backed by Intel. But Intel, you know, are not unfamiliar to the concept of canceling all of their internal projects. For example, Larrabee never materialized. Many integrated core like Xeon Phi again appeared, very useful, but again now it's been discontinued. So yes, yeah, that's fine. And so you have to question whether if Intel pulls support for Xe in the future, maybe the performance isn't as good, or they face more competition from AMD and NVIDIA and that kind of thing. If they pull support for this, can SYCL really survive on its own? And I'm not sure whether that is going to be the case. I think what Gihan was saying earlier was correct in that really the best way to approach things is to have a general DSL structure for what you're doing, and then build on top of that with your application, and then let the DSL spin out into these new code generation standards. Because if you have to be, you know, if you've got an application that requires complete rewrite, then even if the standard is excellent, which SYCL currently is not in a state which would be described excellent, even if the performance is good, a developer that has to do a rewrite is not going to do that. They're not going to take that plunge. And so ultimately, I think really the direction is to go into a kind of to use these domain-specific languages in order to that can do the code generation and look at these new programming models, and then you just write the application using the DSL. So I think SYCL is an interesting concept, and it'll be interesting to see where it goes and how the performance improves over time, because I'm sure it will. I'm sure Intel will at the moment put a lot of resources into this as they try and ramp as they ramp up Xe. But I'm not sure whether it's really a unifying API that kind of enables this super performance portability where you don't have to worry about any hardware-based optimizations, and it's all abstracted away. So that's about it for me. I'm going to open it up to questions.
Thank you, Archie. Quick question from me. So,
sure.
How well do you think the SYCL parallel model, this either completely flat or two-level parallelism, fits for the CPUs where you need to generate vector instructions as opposed to GPUs where you need to generate scalar instructions and the vectorization is done by the hardware?
Yeah, I think that's a very good question. In that, I mean, you can clearly see from the results, because it's an OpenCL-like language, it has, you know, it's much closer to GPU vendor-specific codes like ROCm or CUDA in terms of performance than it is to CPU codes which can use SIMD and that kind of thing. And I think as well, a lot of people are not really sure as to the direction SIMD is going to go in from the CPU side. Like, are we just going to have bigger and bigger SIMD units? Where are we going to go from here? If we're basically having explicit, we're basically packing in explicit vectors, then as these get bigger and bigger, you kind of question why this hardware is going to be, why we're putting this kind of space on the die to have these bigger and bigger SIMD operations, when if we can do massive parallel processing on a GPU or on a FPGA, then does it really make sense to do it? And I think Intel clearly are really pushing into the GPU space, and it makes sense to why they've chosen a GPU compute-focused API to be part of their one API suite. But it definitely does, you know, it leaves a lot to be desired from the CPU side, because it really doesn't seem to be taking advantage of those features.
So I am not so sure about Intel GPUs, what their architecture is. Does anybody know here whether they will require SIMD instructions, or they will be more like CUDA GPUs where you have scalar instructions and then the parallelization or the vectorization is implicit in hardware?
I mean, from what I understand, the Intel GPU platform is an extension of their current work with like Iris graphics, which it works in a very similar way to traditional GPUs. So unlike with the mini integrated core, where it is basically a CPU that's designed in a way that's like a GPU, these really are GPUs, and they act like a Radeon or an NVIDIA card.
Okay, thank you. Any other questions? Okay, then thank you, Archie. Yeah.
Thanks.
And we are going to move on to Suneth Ekanayake from the University of Warwick, who is going to tell us about tiling unstructured mesh computations, actually using a library developed by one of our speakers, Fabio Luporini.
Hi, can you all hear me?
Yes, thank you.
Yes, give me a second. So let me switch on my video. Give me a second, please. Right. Hi, sorry for the disturbance. So I'm Suneth Ekanayake, and I'm from University of Warwick, and I'm currently attached to the computer science department as a PhD student. And our research is mainly focused on communication avoidance in unstructured mesh-based CFD applications. So our work is supported by Fabio, Istvan, and Andrew, and it's supervised by Dr. Gihan Mudalige. So I think I'm audible now and the screen is viewable. Hello, I think you can hear me. Istvan, is it?
Yes.
Yeah, no, it's all working.
Yeah.
Yes, yes.
Okay, yeah, sure. Thank you.
You can see and hear everything.
Yeah, okay, fine. So as you all know, the frequency scaling of processors now has come to a saturated level due to the increasing level of energy consumption. So now the modern developments are mainly towards massively parallel architectures, basically multi-core, many-core, and heterogeneous process architectures. So in these architectures, the main culprit for energy consumption and runtime of the application is the data movement, which is the data movement between levels of memory or between multiple processors over a network. So hence, the communication avoidance or the minimizing data movement has come into play when considering the increase in the performance of applications. So we see many applications which use same data over and over again in a single runtime. So in such applications, the best way to enhance the performance of those applications, which are running in modern CPU architectures with large memory hierarchies, is exploiting the data locality through techniques such as cache blocking tiling. When we talk about cache blocking tiling in brief, so it has a very rich literature developed over past few years. Basically, this work is extensively focused on structured mesh-based applications. But when we consider the unstructured mesh-based applications related with cache blocking tiling, so the work is relatively low when compared to the cache blocking tiling work with related to structured mesh applications. So when we consider the previous work which was done related to cache blocking tiling in structured meshes, we can mention Pluto, Poly, Poshua, I think I pronounced it correctly, as keywords in that field. When we search for the research work in the unstructured mesh-based applications, we see Slope, which was developed by Fabio and others from Imperial College and various other universities. So he's also in this webinar at the moment. So it has some promising results. Actually, they have proven that this Slope library is able to give performance to unstructured mesh-based applications through cache blocking tiling. And the developers have proved by using this application, this library, that it can be gained the performance up to 28% in seismological applications. So the research work is mainly focused on seismological applications, and this unstructured mesh-based cache blocking tiling library was able to gain that much of performance in that area. The main reason that we see for the lacking of literature based on the unstructured mesh-based work is due to the increasing accesses, increasing of indirect memory accesses, as Archie and Gihan mentioned previously. The information of unstructured meshes related to nodes, cells, and edges, those are given in structures, so that we have to do a lot of indirect memory accesses to have those information for our calculations. Because of that, the performance that we can gain using unstructured mesh-based application is relatively low. So we have to carefully exploit the data locality of those applications. So Slope is capable of doing that. So the developers have initially proven that, and when we are carrying out our work, we also try to replicate the results of the developers, the previous developers had obtained. So when we talk about the Slope library in brief, so I think Fabius is here. He can correct me if I'm mentioning something wrong. So when talking about the Slope library, it is basically an unstructured mesh-based cache blocking tiling library. So we can merge the loops of an application into a chain using this library. Actually, not to a particular chain, but to multiple chains as well, depending on the scenario. So the library changes the way that the loops are executed based on the dependencies among the loops and by exploiting the data locality, but by not changing the semantics of the application. In our work, we are investigating the capabilities of this Slope library with the intention of integrating this into the OP2 DSL so that it can automatically generate code to obtain optimized parallelization with cache blocking tiling in unstructured mesh-based applications. So I'm not going to explain in-depth details of the Slope library. I have mentioned the references as well. So when moving on to the work that we have done, so initially we wanted to replicate the results that was presented by the initial developers of the Slope library. Going with that, we chose two applications. One is the airfoil, which is a simple representative CFD application benchmark, and it is based on a 2D mesh. You can see the mesh in the slide here. By using the Slope library, we were able to gain up to 26 to 30% speed up of the slopified version of the airfoil application over the OP2 version of the airfoil application. So you have heard about the OP2 DSL previously. So we have an optimized version of the OP2 version of airfoil application, and we used the Slope application, Slope library on top of the vanilla airfoil application, so that we were able to compare the performance gain that we can have using the Slope library over the OP2 library, over the OP2 version of Slope library. So our ultimate goal is to incorporate Slope library into the OP2. So we are basically gaining the performance gain in a CPU-based architectures, CPU architectures. So you can see the mesh that is shown here as named as 280K airfoil mesh, which we have used MeteoSwiss partitioning to partition that airfoil mesh. So it has 6 colors. So there are two partitioners that is attached to the slope library. One is MeteoSwiss and the other one is the normal chunk partitioning. We used MeteoSwiss partitioning to gain this result for this airfoil application. Yes. You can see colored tiles there. So this is partition. So the tiles are available with six colors. So that the iterations are assigned to those tiles. The tiles with the same color, the iteration which are assigned to the tiles with the same color executed parallelly. So we can have a performance gain by using that. So when we are building up this inspector scheme, which is available in the slope library, we consider the data dependencies among the loops when we are building the loop chain. So you can see in the right side, we have done a roofline test. We have 4 major kernels in the airfoil application. So you can see the blue colored dots represents the OP2 version of the airfoil, and the green colored dots represents the slope version of the airfoil. More the dot is higher, and to the left side of the graph, it's better. So you can see out of the 4 kernels, 3 kernels have received a gain using the slope library. So that is why we were able to gain that much of a speed up using the slope library in the airfoil application. Yeah. So moving on, we need to prove the results more. So the capabilities of the slope library. So we use another application, which is MGCFD. You have heard this before as well in the presentations. So it's a mini application that represents a geometric multi-grid unstructured CFD code. And it is based on a 3D mesh. And we were able to gain up to 14% speed up at the moment by using the slope library. We are exploring more to gain even more speed ups using the slope library by changing the nature of the loop chain that we have built in the slope in the MDCFD, and by using various partitioners. We were able to gain this much of speed up by using the chunk partitioning, but we were not able to gain that much of speed up using the MeteoSwiss partitioning. So we are exploring what are the reasons behind that. So we need to have a clean partitioning so that the iterations are assigned nicely, that it will exploit the data locality of the particular application. In the right side, you can see the roofline graph that we have plotted for the MGCFD application. We have, when compared to the airfoil application, we created 2 loop chains for the MGCFD application. So we were not able to, by that, we were able to gain 14% speed up here. You can see the green colored dots represents the slope version of the MGCFD. So those are moved upwards, and that's why we were able to gain that much of a gain here. So in memory bound applications like airfoil, Hydra, when we're considering the industrial level applications, we are expecting to have more gains using the slope library. So as future work, we are expecting to embed this slope library into OP2 DSL. Yes, and we need to have tile parallelization into embed OP2 DSL so that we can automatically generate tile parallelizations for multi-threaded CPU applications. And we are trying to investigate the benefits of tiling with hybrid OpenMP and MPI parallelizations. And when we talk about the gains that we received using the slope library, so we can mention 3 things. So the performance gain mainly depends on how the unstructured mesh is partitioned and the size of a partition, and also the way the loops are fused by using the slope library. We identified those three things as kind of tuning parameters there. So by tuning those parameters, we can have we can improve the gain that we can have with the slope library. So the tile size is kind of a parameter that user has to give, but we are trying to automate those things in time to come when we are integrating the slope library into the OP2 DSL. And our ultimate goal is to apply these to industry-grade applications like Hydra, which is used by the Rolls-Royce for the simulation of next-generation jet engine components. And when we talk about further about the gains that we had in the airfoil and MGCFD, we need to prove more the performance gains that we can have using the slope library. So we are experimenting with Volna, which is used to analyze, which is an application that is used to analyze tsunami waves, and we are hoping to use Lulesh as one of the applications that can be used to analyze the performance gain that can be gained using the slope library. So all in all, Slope is a library which is based on unstructured mesh-based cache blocking tiling. So we were able to gain up to this moment 26 to 30% from airfoil application and up to 14% in the MGCFD application, which is a 3D mesh. So thank you, and that's my research based on unstructured mesh-based tiling. Thank you. Any questions or I would like to answer?
Thank you, Suneth. Any questions? So I have one. Can you speculate about why the chunk partitioning may be better for MGCFD?
Actually, we were trying to analyze what are the reasons behind the performance difference that we observed by using different partitioners like Metis and Chunk. According to the as far as we have experimented so far, we see we can imagine we can think that there may be more indirect memory accesses that can be caused by using Metis partitioning than the chunk partitioning. So in airfoil, we were able to gain almost similar gains by using the two different partitioners, MGCF, Metis and the chunk. But for the MGCFD, we were not able to gain that much of a gain using Metis partitioning because it's a 3D mesh, which is different to the plain airfoil application. So we think there may be a lot of indirect memory accesses that may be causing this performance lag when we are using Metis for the partitioning than the chunk partitioning. That's what we think at the moment. So we are experimenting more on that.
So probably, yeah, great talk, Suneth. But this is Fabio. So probably one of the, I mean, did you check, because this is a very good question. So did you check the numbering of the underlying meshes? Because if I remember correctly, there's typically a relationship between the numbering of the underlying mesh and the kind of partitioning that you should use to get the best performance out of it. So for example, you use chunk partitioning when the underlying mesh is fairly regular and the numbering of the mesh sort of matches the numbering of the chunk partitioning. Do you see what I mean?
Yes, I see.
So can you move to the picture with the MGCFD partitioning?
Yeah, it's with chunk partitioning actually.
Yes.
Yeah. And this is using Metis partitioning. This is using chunk partitioning here. Yeah, actually, as Fabio said, we have. I looked into the iterations that were assigned to the tiles when we are using Metis and Chunk. So we can see there's a regular kind of sequence of the iterations are assigned sequentially when we are using chunk partitioning, but not with the Metis partitioning. I think the nature of the mesh will cause this difference here. That's what we think at the moment.
Because that kind of that tiling that you have with MG-CFD, that it could potentially be much better, because there, I mean, we should see the section of the mesh, but it feels like that the diameter of those tiles is pretty huge.
Yeah.
And the smaller the diameter, the better in theory, because then you are communicating less data.
Right.
So for example, one of the big things that we're missing with in my work with Firedrake and Slope was essentially plumbing a space filling curve inside the code. Because if you have a suitable, so if you're using a space filling curve, then if you are using a suitable space filling curve, then you could get blobby tiles, like cubic tiles, something like that, where the diameter really shrinks, and then the communication gets better and better, and then improve performance. So I remember once we did it very hackily with a colleague of mine with airfall. So we renumbered the mesh with some sort of space filling curves to get essentially perfect blobby tiles. Maybe it wasn't airfall, maybe it was Volna. I don't remember. And we were indeed getting much better performance.
Right.
So
and you can
OP2 has this capability to renumber.
Renumber, yes. And MG-CFD, just before the partitioning, the renumbering happens in MG-CFD as well. So after the renumbering, then we are using the partitioning. Then we are doing the partitioning there in MG-CFD. Yes.
So I think we could hack OP2's renumbering method to use the Metis partitioning as a basis for this renumbering. And we will get nice contiguous numbering inside of those partitions.
Right.
Yeah, maybe something to explore.
Yeah, thank you.
But basically, I think that, I mean, long story short, one of the objectives should be to obtain blobby tiles, cubic tiles, something like that.
Yeah, which is very similar to the Hilbert curve, space filling curve that you have mentioned in your paper.
Exactly.
Yes.
And of course, the underlying storage layout, the underlying data storage layout should follow that number.
Yeah, and you have mentioned in your paper that seismological application that you have experimented in that also you gain the better gain using chunk partitioning than the Metis there. So we are using Metis as a kind of an alternative to the Hilbert partitioning in our SOAP library at the moment. I think I'm correct.
Yeah. Good.
Okay, thank you. Very interesting stuff, and I think pointing in a very good direction. So with that, we are going to move to Bálint Siklósi, who is going to tell us about reproducibility in unstructured mesh computations.
Thank you.
Yep, we are gonna share the screen locally.
We can see it right now.
And then So hello.
Maybe you can turn some lights on if you want to be visible.
No chance.
Okay, don't mind.
I will send a photo to you later if you want. So
I find.
Okay. So hello everyone. I'm Bálint Siklósi, a PhD student at Pázmány Péter Catholic University. In the next few minutes, I would like to share some of our work about how we achieve bitwise reproducibility over unstructured mesh applications. First of all, I will introduce the problem, or at least the source of the problem that we want to solve here. Then also I extended with some motivation that why is it useful to solve that problem. Then I'm not sure for how many times today, but I will introduce again the OP2 DSL because this is where we implemented our work. And then I will show some of the strategies that we applied. And at the end, I will show some numbers as well about the performance. So all of the problem come from the IEEE 754 standard for floating point representation. This standard defines a correct behavior for all of the operations within, but for some operations, it also introduces some roundings, thus some non-associativity. With other words, the order of calculations affects the final result. Here is a simple and stupid example for that. I just used Google's built-in calculator. I added 0.001 to 1 billion, and again, added 0.001, and I done this 10 times for the first time. The second time, I added the small numbers first, times the 0.001, and then I added 1 billion, and I received two different outputs. They are pretty close to each other, but they are different. So this is just a stupid example, but in many high-performance applications, this is really frequent thing which can happen. There is some strange noise, but never mind. So where I was, yeah. So far, we already use these applications, and we trusted their results. What we did so far, that we ran the application, we received the final output. But with those applications, we also received an error bound too. So when we have the final output, that will be within the error bound interval of the real answer of a problem. In this case, this error bound might be 0.001 or something. Both of the answers are within the same interval. But there are some applications. So we already done this, it was working. The IEEE 754 is one of the most popular floating point representation. And we use those this way, but there are some applications where exact reproducibility is really important. In some industries, like in aircraft turbine design or in algorithm trading, reproducibility is really important. Sometimes it is checked by regulators frequently. But from the developer side, it can be also important, mainly for debugging program. If we have a really rare error, we run the application, we run into an error. Sometimes we want to reproduce it with the as much detail as much as it is possible. Another useful case, which we've done so far too, if we want to parallelize an application, what we do at the end, we run a trustworthy sequential version, and we run the parallelized version. And if the two outputs are similar or same within the error bound, then we can say that probably our parallelization technique is working. But still, we had to think about whether this is just a representation error or some other type of bug in the code. If the two outputs are exactly the same, then we can be sure that our method is correct. There are some already existing solutions for this problem. For example, the reproducible projects
they introduced a whole new number representation, so-called bin representation. And there is a work also in the Lulas application. But all of these approaches come with some price. Reploblas, this price is 5 to 9 times floating point operation overhead, which is pretty big. Although their method is really general. You can apply it really easily for almost every applications, but the overhead is pretty big. In Lulas, their method can be applied only for boundary or hello values. In our solution, we created a reproducible ordering for indirect increments. Soon I will tell what is this increment stuff, how does it come into the picture. Also, we created a method for reductions, so it became reproducible. And these are also true when we run the application on different number of ampere processes. This is really nice, but also our method has its price too. It must fit into the domain of our language. By the end of this day, you can easily guess what is the domain. Of course, grids. We have structured and unstructured grids. Structured grids are really simple. There is a logical indexing with implicit connectivity. It is really simple to parallelize, mainly for GPUs because of the similar architectures. This was presented today many times. But there are some applications where structured grids cannot be used. We must use unstructured grids. In unstructured grids, we have a collection of different elements in sets like nodes, edges, cells, and so on, with an explicit connection between those. Such a connection can be a mapping table, which defines that there is an edge which connects these two nodes, for example, or there is an edge and on both two sides of it there are this cell and the other cell. It is much more difficult to parallelize than a structured grid, because if we calculate one part of the grid, we have no idea where are we in the whole mesh. In a structured one, it is really useful if we can calculate which one will be the next one, which we want to execute and so on. So it is really difficult to parallelize, but it is useful. We must rely on them also. But these partial differential equations usually created, or these applications are usually created by physicists, chemists, biologists, or any other type of scientists. And no one expects them to be able to write efficient code for different architectures. For this, we introduced some high-level, domain-specific high-level abstractions. The user must declare the problem that they want to compute by using some specific constructs in the declaration, but they do not need to specify the implementation. And then they can apply some automated techniques, and as a result, they will receive an optimized implementation for different hardware architectures with different software platforms, with different parallelization techniques, and so on. In this research group, we developed this OP2 library, which is a library that I just described, an open source project based on OPLUS, Oxford Parallel Library for Unstructured Solvers. It looks like a conventional library, but uses code transformations. So the code that the user writes can be compiled, can be run sequentially, but from that in C++ and Fortran too, but the user can transform it also to C++ or Fortran code, which can use different techniques. Here is a simple example how to use the OP2. The user must define a kernel function, in this case, this res function, which is can be defined on an edge. And what it does, it just increments the cells values next to the edge with the value of the edge. And then what the user must do is call an OP par loop, defining that he wants to use the stress kernel function with a fancy name for fancy outputs. Then they must define the set of elements on which the user wants to call this kernel function, and then some arguments with other details, for example, the mapping, how to access the data, other access parameters, and so on. And then the user can generate a code. In this example, we can see MPI parallelization techniques already applied on it. We keep the kernel function. We prepare some of the arguments. We do some hello exchanges, because if we split it into different computes, nodes, even into different memories, within the application, we must exchange some data, and from that we can calculate the execution size within one process, and then we can iterate through only on those elements which are within the process, and then we must prepare some of the accesses with the mappings, and then finally the kernel call must be done with the correct parameters. All of this was presented today with much more details in a better way, for example, by Gihan. So I will skip the rest of it. I will turn back to the reproducibility problem. Again, here is a simple example. We run an application 2 times. First time, still we want to increment the value in a cell from the edges around it. First time, the edge on the top increments the cell's value, then from the right side, and from the bottom, and from the left side. But next time, there is no guarantee that the IDs of the edges will be the same. The general idea is that we calculate the edges, that edge first, which has the lowest ID, and second time the edge which has the second lowest ID, and so on. This can be an approach in this case. So next time when we partition our graph in a different way, we might have different IDs. Thus, the order of execution can be different. In this case, the edge from the right side increments first, then from the left side, and so on. So the final output can be different. What we do with this is we kind of swap the iteration. First, we iterate through the edges like we did before. We calculate the incrementing values from each edges, but we do not add them to the cell. We just store them in a temporary array for the first time. And then we iterate through all the cells, and from the cell, we gather these increments from the neighboring cells, neighboring edges, which values are stored in this temporary array. But what we can do here, and that is really important, that we can sort these temporary values in a way that so what we know each time and what will be the same each time, no matter how we partition the graph, is the global original indexes of all elements. That will be the same. And within OP2, we can ask for this information from the backend. And with these global indexing, we can order the increments. And thus, we will have a fixed order how we will apply the increments into the cells value. And this will be always the same. Another problem which had to be solved is reduction over MPI. For many of the applications, it is really important. In this example, we want to add up the same number of data, but first time we partitioned it into 3 parts. Next time we partitioned into 2 parts. I do not want to go really into the details. Probably you can see we can receive different outputs because we add the data in different orders together. What we have done here, we didn't invent something really new. We just used this representation from the Reproblast library. They have a function where we can, as an input, we can add normal double typed variables. Then it will add it together already in a binned representation. And they have also a function. They also have a function for MPI reduction in binned version with binned representation. From that, we were able to generate a normal double value at the end. Another problem which came up during this process is that there are some applications with read-write accesses where we must execute the kernel on every element because we want to read previously executed or previously calculated data, and so from that we want to calculate something new and so on. So temporary storage is not enough. We must execute it. For that, we apply a regular coloring scheme to define the order. If someone doesn't know it, that is a simple way how to get rid of race conditions. We color the elements that we want to execute, and no neighboring elements can have the same colors, and we can run parallel those elements which have the same colors. But how can we achieve that the same color will be always each time? So how can we fix the order? Again, this is the question. But there are 2 approaches for that. First one is not the nicest solution. Before we run our application on multiple processes, first we have to run it only on one process. The OP2 reads in the whole mesh, applies a coloring algorithm, even simple greedy coloring algorithm can work here. And then it saves these color values, color IDs to this file system. And next time, when it is run on multiple processes, then when the distribution happens, we can distribute these colored data in the same way, color IDs the same way. This works nice. It is really efficient, but there is the price that we first need to run it on one process, and also the mesh has to fit into the memory. That can be a bound also. The second solution, if we can develop an algorithm which generates the same colors, even if it is run from, even if the algorithm is started from different parts of the graph, and the number of where it started can be different because we can run it on different number of processes. Then if it can generate the same colors, then we can use that and we will be okay again. For this, we are sure that there is a trivial solution. As a color, we can assign the global ID of each element. It will work. There won't be 2 neighboring elements with the same IDs, with the same color. And this color will be the same always because the global IDs for every element are the same. But if we have as many colors, as many elements, we cannot parallelize it. So this is a pretty stupid solution, but at least we know there exists one. The question is that is there a better one? Sadly, I'm not a mathematician. I cannot prove whether there is a better one, whether there isn't. If there is an application, I cannot prove, if there is an algorithm, I cannot prove whether it really does work. If any of you have an idea about this, if you have experience with graph colorings and so on. I'm really open for suggestions, open to work together. I hope that after this workshop, we can find some solution for this problem. It would be really nice. Yeah, we tested these methods in multiple environments and multiple applications. CPU-related environment consists of 4 Intel CPUs, altogether 64 processes. And in the GPU-related environment consists of 1 DGX station with 4 NVIDIA V100 GPUs. We used 3 applications, mini applications, airfoil, which is a simple standard finite volume computational fluid dynamics benchmark code. We used it with 3 mesh sizes. Arrow, which is a bit more complex, 2D nonlinear steady potential flow simulation, also with 3 mesh sizes, and MGCFD, which was introduced multiple times today, which is a multi-grid finite volume CFD mini application, and we tested with 2 mesh sizes. And here we can see the slowdown effects of this method. We must have a slowdown compared to an original run because we introduced some extra calculations, some extra things to do. What we can see here is that, for example, if the application is more computationally intensive, then the overhead is much smaller. So in Arrow, the overhead is smaller than in airfoil because we spend more time within the canal call itself. And on the GPU version, we can see a pretty, well, a not really good slowdown effect. This is still in progress, the development. We have a few ideas how to make it more efficient. But at least we can say that we have fully reproducibility even under GPUs and in many core CPU systems. So that is what I wanted to share with you. If you want to contact us, again, the well-known links are here, or you can message me anytime. And I'm also open for questions if there are any.
Thank you, Bálint. If anyone has a question, please let us know. I will ask one in the meantime. Do you have a notion for how expensive the construction of these extra data structures for the temp arrays and the colorings are? How much time it takes?
I didn't measure it yet. But compared to the whole runtime of the application, it is not really bad. So we need to calculate these colors, for example, only once, and we need to read it in next time, which is really quick.
Could we potentially parallelize some of these? The construction of this data structure?
Probably yes. There are some coloring methods, coloring algorithms which can be parallelized easily. Yes. What we implemented here is simple single-threaded greedy algorithm, but can be more efficient, of course.
Okay, thank you. Anyone else with a question? Okay, so it seems we finished right on time then. So thank you for everyone who participated today. We are going to resume tomorrow at 9 a.m. local time. That will be 8 in the UK, with another number of very interesting talks. So looking forward to seeing or hearing you again tomorrow. Thank you, everyone.
Thanks. Bye-bye.
Thank you. Bye-bye.